Every time Netflix recommends a show, Google detects spam, banks flag fraud, or an app predicts what you might click next, machine learning is working quietly in the background. And the best part is, you don't need to start with complex theory, you can learn it practically using Python. Welcome to this Machine Learning Using Python course by Simplilearn. In this course, we will start from the basics and understand what machine learning really means, how it fits under artificial intelligence, and how it is different from deep learning. We'll look at how machines learn from data, identify patterns, and make predictions without being manually programmed for every single task. Then we'll move into the major types of machine learning, especially supervised learning and unsupervised learning. You will understand how supervised learning works when the data already has answers and how unsupervised learning help find hidden patterns in data. After that, we will be exploring two very important areas of supervised learning, which is regression and classification. Now, in regression, we will learn how to predict continuous values like salary, sales, house prices, and rainfall. In classifications, we will understand how models predict categories like spam or not spam, pass or fail, yes or no, fraud or not fraud. Then we'll go deeper into regression models such as simple linear regression, multiple linear regression, polynomial regression, ridge regression, lasso regression, elastic net. And you'll also learn how to evaluate regression models using metrics like R-square, MAE, MSE, RMSE. Next, we'll also cover important model improvement techniques like cross-validation, regularization, hyperparameter tuning, grid search CV, and randomized search CV. So you will understand how to make your machine learning models more reliable and accurate. We'll also focus on data pre-processing and feature engineering, where you will be learning how to handle missing values, encode categorical data, normalize and standardize data, and use pipelines to keep your machine learning workflow clean and organized. We'll move into classification algorithms as well, like logistic regression, naive Bayes, K nearest neighbors, decision tree, random forest, and many more. You'll learn and understand how to evaluate classification models using confusion matrix, accuracy, precision, recall, ROC curve, and AUC. Finally, you'll explore powerful Ensemble learning techniques like bagging boosting, hard voting, soft voting, adder boost, gradient boosting, XGBoost, and cat boost. Now, these methods help combine multiple models to improve prediction performance. And by the end of this course, you will be understanding how machine learning models are built, trained, tested, improved, and applied using Python. So let's get started. Also, if you're interested in mastering the future of technology, then the professional certificate course in generative AI and machine learning is the perfect choice for you. This is offered in collaboration with the ENICET Academy, IIT Kanpur, and this 11-month live and interactive program provides you hands-on expertise in cutting-edge areas like generative AI, machine learning, tools like ChatGPT, DALL-E 2, and even Hugging Face. You will be gaining experience through 15 plus projects, integrated labs, and live masterclasses delivered by esteemed IIT Kanpur faculty. Alongside earning a prestigious certificate from IIT Kanpur, you will receive official Microsoft badges for Azure AI courses and career support through Simplilearn's Job Assist program. So hurry up and enroll now. The course link is mentioned below. Now, before we get started, here's a quick quiz question for you. Which type of machine learning is used when the model learns from labeled data? Unsupervised learning, supervised learning, reinforcement learning, or deep learning? Let me know your answers in the comment section below. Areas like generative AI, machine learning, tools like ChatGPT, DALL-E 2, and even Hugging Face. You will be gaining experience through 15 plus projects, integrated labs, and live masterclasses delivered by esteemed IIT Kanpur faculty. Alongside earning a prestigious certificate from IIT Kanpur, you will receive official Microsoft badges for Azure AI courses and career support through Simplilearn's Job Assist program. So hurry up and enroll now. The course link is mentioned below. Now, before we get started, here's a quick quiz question for you. Which type of machine learning is used when the model learns from labeled data? Unsupervised learning, supervised learning, reinforcement learning, or deep learning? Let me know your answers in the comment section below.
So let's talk about machine learning. This particular term has been, I think, the most used term for past decade now. It has changed its meaning throughout the journey. So when I started my journey into data science field 10 years ago, this particular field was not known as AI. It was not even known as data science. It was at that time known as big data analytics. Okay. So at the time when I started this particular journey, this name was not even there. So what exactly happened at the first place? So it was the information boom, which we already know. The computers started working from 1980s to 1990s. Internet boom started from late 90s to early 2000s. Then the smartphones came, then your smartwatches came. Now everything is smart right now, apart from us humans. Okay, we are trying to be smart, we are trying to catch up to them. So what exactly happened at the time? First of all, let's go back to the time where people used to do all the calculations by hand. Okay, the smart thing which first came along was a calculator. What exactly calculator was doing? Doing all the very big calculations in the matter of seconds. At that time, it started helping humans, right? Afterwards, what happened? We started using calculators and started using it for statistics calculation, like ANOVA testing. Uh, you can say pi test, chi-square test, any type of test were there. Calculators were very much useful. Okay, that was good. But what if my data became thousands of rows of data, maybe more? Okay. At that time, a small section of computers started coming up. They were like kilobytes of space. They were handling like thousands of rows of data, which was very good. It was still a very much good leap from that point of on. But now, what happened? Internet age came, smartphone age came. Now the data is coming from all the parts of world. If you see Netflix, your data is being collected. If you go to Facebook, your data is getting collected. Instagram data is getting collected. Your smartphones, your smartwatch, every single thing is giving out data so much that now the analyst, whatever they were called at that time, we will get to that point. They started thinking how exactly can we utilize this information and make a sensible information out of it. At that point of time, advanced statistical tools came into place, and those were called as machine learning. Okay, so machines started seeing the algorithms. They started doing the same calculations which were doing from pen or paper to calculator to Excel to this particular formulas, which works on a lot more sophistication. Okay, that is what machine learning is there for. So let's talk about introduction now. Okay. So by the end of this particular session, you will be able to analyze the distinction and application of machine learning, deep learning, and artificial intelligence. We are going to talk about all these three topics, differentiate among the various learning models, and explore how each model learns from the data to predict the outcome. Okay. Explore the Python libraries for effective data manipulation visualization. Okay. So what is machine learning? Let's talk about it. So machine learning is a subset of AI. We are going to talk about AI bit more in further classes or sessions that assist the systems to learn, improve automatically from experience without being explicitly programmed. Okay. So think about it this way. In 1950s or 1960s, the machines which were created with a mindset like, okay, this machine is going to pick apple from A and going to drop it at B. So it was specifically designed for this thing. There was nothing beyond this. A to B. Okay, my machine is going to pick something from A and going to drop at B location. But this has certain caveats. What if I wanted to pick it from A and drop it at C, or pick it from B or drop it at A? That means you have to make another machine who is programmed specifically for that thing. Now, it is quite inconvenient, right? That's why, what if I can make a system through which I can train it? I don't have to make a hardware specifically for it, but at the software level, I can train it certain way that it can do the work according to what kind of data I am providing. Suppose a machine is there to give me the answer whether the student is going to pass the exam or fail the exam. On another scenario, a machine is trained to give me the result whether the stock is going to go up or go down. Similarly, gold price is going to go up or go down. This cricket team is going to win or lose, so on and so forth. So what exactly is happening? I'm not making very task specific tools now. I'm making task specific learnings now. I'm giving it a data of similar type of scenarios. I'm saying, okay, this is the historical data. This is what is going to look like. You have to predict the future of this particular event. So in short, at the software level, I am doing some tweaking so that I don't have to reinvent the wheel altogether. Okay. So coming back to the PPT, it enables programs to learn automatically, making computers more intelligent without human intervention. Okay. So let's talk about the traditional approach and the machine learning approach. So first one, we can see that use of predefined rules, okay, and algorithms explicitly programmed by human developers. Just like I told you, if I create a machine to pick from point A and going to point B, that is an explicit type of thing which I'm doing. I have this thing in mind. But what if in future I want the reverse out of it? Okay, I want it from B to A, then it is going to fail. Okay. On the other hand, machine learning learns from the data. Okay, it learns from the data to make the prediction action without explicitly programmed. Okay. Now coming to again tradition, it relies explicitly on the defined logic rules to perform the task. Okay. And to counter this, it uses statistical techniques. So please bear this in mind. Machine learning is not a rocket science. It is still same statistical algorithms which we are going to use, but at scale. Okay. And optimization of algorithms to learn patterns and make decisions. So this is what exactly is happening over here. Okay. We are using statistical techniques and optimization to make the decisions. Now, what exactly in traditional requires manual feature engineering where relevant features must be identified and extracted by humans. Okay, so a lot of human intervention is there over here. But on the other side, it is automatically learns from the features from the raw data and reduces the need of manual feature engineering, which is good. What is the challenge which traditional type of approach faces? Faces challenge of handling complex and unstructured data. So if you are trying to feed a very similar data, it is going to work fine, but certain times the data gets disturbed, the machine stops responding correctly. Okay. On the other hand, it handles the complex data, unstructured data, and such that the images, audio, and video, everything can be learned from. Okay. Performance depends on the accuracy and completeness of the predefined rules. Performance improves with more data and learning iterations, enhancing the accuracy in generalization. Okay, so this is the difference between what exactly is machine learning and how exactly we can use it. Okay, Shivananda, good question. So statistical technique. The thing is, all the algorithms work on different statistical techniques. Whichever algorithm which we are going to go through, I'm going to talk about that particular technique. Okay, so it is something like we are going to take it in the further sessions. Okay, so don't worry about it. We are going to cover it all. So if we move forward, now if you look at this particular graph, machine learning comes somewhere in between. Okay, it comes in between AI and the deep learning. Okay, so deep learning is the root type of a root of this particular block. Okay, and machine learning is something which is complex thing derived from deep learning. Okay, and then if you make it much more advanced like 100x, you are going to reach to the artificial intelligence where currently the GPT models, all the type of models which you are working on works. So once you go into the deep learning model, once you go into the GPT module, you're going to see how exactly a simple idea coming from the deep learning to the machine learning to artificial intelligence actually took place throughout the decades of research. Okay. So what is artificial intelligence giving us? Like self-driving cars, very advanced chatbots, okay, etc. What exactly is machine learning giving us? Amazon Excel, okay, Alexa, sorry. There are a lot more scenarios in which machine learning works, like Netflix, like Google, etc. Deep learning, handwriting recognition, number plate recognition, face recognition. A lot of things are coming from these different algorithms. We are going to go through each one of them one by one. Okay. So machine learning example, AI uses machine learning to figure out if the opponent is beginner, intermediate, or advanced player. So I don't know if you have played certain games on your computer or PlayStation, but if you have played like chess is a very good example, but Call of Duty, Dota, GTA, all of them works on mathematics only. Okay. If you talk about Call of Duty, if you're playing with bots, and if you start performing very good, if you are killing the players or the bots frequently, it is itself going to learn that we have to increase the difficulty for the player to win this particular game. So this is how machine learning is learning all the time and reinforcing its learning throughout. We are going to talk more about it in future modules as well. Okay. So the AI decides its next move against the opponent using complex neural network that learns various features and patterns from the data. So all the data, if you drop it down to mathematics, can be dealt with in certain way. So games are nothing but complex mathematic equations running behind you. Okay. So what are the applications of machine learning? Let's talk about them. First of all, uh, I don't know if you have seen this particular scenario in your Gmail or something, but there are a lot of times that spam mails are directly inverted towards the spam folder. Okay. How exactly it is done? It is done by nothing but flagging the spam emails in which the Gmail learns, okay, these type of emails are spam, like suppose any type of mail starting with hi sir, uh, there is a loan offer for you. Okay. Whatever type of information which is starting with certain kind of thing can be named as spam. Suppose I'm giving you a very simple example. Okay. Similarly, social media analysis. Okay, let's talk about this. So social media, like what kind of post you are giving. Okay, if you have a public account, you get information like how many age, like suppose how many people from the age of 14 to 18 viewed your video. Okay, how many from 19 to 21 viewed, something like this. How many from India viewed your video, how many from outside India, how many of them are male, how many of them are female, etc. Okay, these are nothing but social media analysis. Customer service chatbots, I think it's self-explanatory how exactly chatbot works. It learns from the queries and it gives you kind of a FAQs. Okay, you can just go through those, click on them, and you are going to get the result for it. Okay, online recommendation system. Okay, let's see who can answer uh, online recommendation system day-to-day example. Any guesses? Okay, ads. Very good. Netflix. Somebody also said Amazon. Exactly, guys. So in short, we all know already how or where these use cases are. The only thing which we are going to learn is how exactly these use cases are using the algorithms at the backend. Okay. Finally, sentiment analysis. Now, again, if you look at Amazon, if you look at Flipkart, if you look at any the online platform, if you go to a certain product and if you go to the review section, okay, today's review section looks very advanced. 70% people find this product good. 20% people found that this product didn't last for more than 2 months. 10% people returned it because of the defect, everything. So these kind of analytics is going automatically throughout everything. How? They are looking through the comments or the, shall I say, customer reviews and trying to analyze what kind of sentiment is there in this particular sentence. Okay. And from that, they were able to identify a certain type of analytics. That's where you land. Okay. This is what you're going to do if you land a certain type of roles in these kind of firms. Okay. So what exactly machine learning algorithm is doing? Okay. So if you break it down, what exactly machine learning does? It helps you predict any type of outcome. Outcome can be what kind of rainfall, okay, uh, stock price, etc. Okay. Classify the target. If you want to classify the target, like is the picture contains a cat or a dog? Okay. Is the student going to pass or fail? Okay. Um, what is the what else? Is this stock is going to go up or go down? Something like this. Okay. Or is this cricket team going to win the game or lose the game? Okay. Improve the performance. So improve the performance by, can I give enough data so that my self-driving car can handle any type of crowd, any type of road, etc. So okay, improving the performance. So there are going to be numerous type of examples over here, but I'm going to give you very simple, very easy to understand one. Okay. So okay. So data and machine learning, how exactly these two are correlated? Just like I told you, as soon as our requirement rose in terms of doing simple paper level calculation to calculator to computers, our algorithms become more sophisticated. Okay. Now, if we have terabytes or petabytes of data, okay, so how exactly these kind of things are handled depends on a lot of things. Okay. So as much as data we are getting, the performance also improves, and quality of the data is a very important factor. What if my data has certain missing values? Okay. Maybe there is a data drift. Okay. Maybe there is date in format. Okay. Or maybe there are certain type of errors which are making my data quality low. Okay. So as a data analyst, you should do the first thing, which is exploratory data analysis. Afterwards, you go to feature engineering. These two are going to improve. These two are going to improve your data quality. And you can see the red line and the blue dotted line. If you can improve the quality of data, so Pragati, data drift means if your data has shifted its origin from when it started calculating. Suppose uh, I have a t-shirt brand. Okay. When I started my t-shirt company, I took a survey and I found that most of the t-shirt designs which I'm going to sell were attracted by 18 to 21 years of college students. Okay. But I started marketing to them only. All the only market Instagram ads of the people who are in the age bracket of 18 to 21, because this is where my product is being bought very much frequently. But after certain time, the shift changed, and it turned out now my clothing lineup is now more focused on people who are from 21 to 25. Okay. 18 to 21 have changed their taste. They are liking something else. Now this is a data drift issue. Okay. Now I have to reattune my data, or you have to realign my marketing strategy. So data drift is a very big term. We are going to go more on detail, but as of now, there are a lot of things which makes our data quality low. So there are a lot of things which we can do as a data analyst to make the quality better, so that we can rise from this red line to this particular blue line. Okay. Means higher quality data is going to give you better machine learning results. Okay. Let's move forward. So by the term high quality data, it means my data is free from a lot of issues which you generally find. So guys, can you recall your learnings from your Python basics, in which you might have done some exploratory data analysis? Those can be, I didn't want to start it this way, but since this question is very good, let's talk about what can be the high quality data. High quality data can be further drilled down, data with no outliers. Okay. Uh, Data with no missing values. Um, Anything else? Data with proper date format. Okay. By proper date format, I mean there are times in which data a date is written as DD, MM, YYYY, but in certain rows it is like MM, DD, YYYY. In this kind of scenario, we can make a very grievous mistake. That's why data quality should be very high and date format should be kept correct. Okay. Your, your data should not have any missing values. You might find that in the gender column, certain rows have values, but certain has missing. Now, this data is missing. How can you treat it? Okay, then you go to missing value treatment, something like this. No outliers. Suppose There's age column. Okay. In age column, there are age like 20, 18. Then out of nowhere, there is 101. Means these are outliers. Outliers can be by mistake. Okay. So you have to remove them or you have to compute them. Okay. So this allows your data to get into high quality where these errors are all absent. Okay. I hope I was able to answer your question. Yes, if you want to simply put data that requires no modification. Correct. So what are the different types of machine learning? Let's talk about them now. Okay. So machine learning can be divided into majorly three parts, but you can see there are four parts over here. But let's to say, simply put, it should be divided into three parts. Okay. So let's talk about different types of machine learning. First of all, let's talk about the easiest one to understand. Okay. That can be easily divided into two parts. One is called as supervised machine learning, and one is called as unsupervised machine learning. So what exactly is the difference stems from what kind of data are we dealing with? Okay. Now, if I take one example in which I have students IQ and students result. Okay. And the scenario is that I want to predict whether the certain new students who adds up into this particular list with the IQ of suppose 70, is that student going to pass or is it going to fail? So I'm going to train my model. I'm going to train the model in which I have students data with IQ and students result, and then I'm going to predict the output. Means I already have the result. Means I have a uh, labeled data. So this comes from a labeled data. Wherever we have a labeled data, okay, that particular problem becomes a supervised machine learning problem in which I'm going to give the whole data. I'm also giving it the result, learn from this thing. And then if I give you out of time data, the new data in which you have not learned anything, you are able to predict whether that thing is yes or no, true or false, pass or fail. Okay. So if you just go back over here, this is how a supervised machine learning looks like. I have a label data. Okay. So suppose I am giving different shapes. Okay. I am calling that this is circle. This is a square and this is a rectangle. Okay. Learn from it. And I give a very out of train time in data in which that particular model has never learned or never seen. Okay. Then I say, okay, predict which kind of shape it is. So it is going to go back and go through its learning. And then it is going to predict that, okay, this one is a square and this one is a rectangle, whatever it is, triangle. So this is the whole thing. Wherever the labeling is done is called as a supervised data or supervised learning. Okay. I need few more confirmations before we can move forward. So in simple words, any data which has a labeled target is known as supervised data. This should be a very simple thing to understand, okay? And supervised data has further drilled down, like what kind of target is there, okay? So the question becomes, what are you trying to predict, okay? Your answer can be between two things. It can be something in a continuous fashion or it can be something discrete. Okay. So your answer can be I'm predicting something which is continuous in nature, or I'm predicting something which is discrete in nature. Okay. So continuous means suppose I'm trying to predict rainfall for tomorrow. Yesterday it was 100 centimeter. Next day it can be 100.5, 99.5, something like this. Okay. So 70.5, 80.7, 100.1 centimeter, something like this. Okay. Oh, sorry, millimeter, centimeter. Okay. So, or I'm trying to predict the stock price. Okay. Or I'm trying to predict someone's salary. Okay. Or I'm trying to predict a house price. So can you see what type of predicting, or shall I say dependent target it is? It is something which is continuous. 0 0.1, 0.1, 0.2, 0.3, it can be anything, a decimal type of thing. Okay. Uh, so that is going to fall into a continuous type of feature. I'm trying to predict a certain number which is continuous in nature. Okay. But if I have certain type of feature which is discrete, like I want to predict a cat slash dog, pass slash fail. Okay. Uh, win slash loss, or yes or no. So this is nothing but a type of problem in which I have differential categories. Okay. Let's make it a cat, dog, or horse. Okay. In this, we are trying to make a certain different type of problems. So over here, wherever I have continuous type of equations or continuous type of problem, that comes under regression techniques. Okay. Wherever I have these discrete type, these come under classification. Fluctuates with time becomes a time series problem, but yeah, you can say any type of number or any type of prediction which is continuous in nature. Okay. So Shibananda says, so is it like numbers involved means regression? So both of them can be numbers. Okay. This can be 0, 1, 2. Okay. 0, 1, and 2. If I'm trying to predict something between 0 and 1, 0 or 2, something like this. Okay. At the end, we are trying to make our data work as zeros and ones always, because that is machine's language, right? So anything which is discrete means it is not 0.01, 0.2, 0.3. No, it is 0, 1, or 2. This can have decimal values. It can have multiple values in between. That is a regression problem. So from our school time, a number which is continuous becomes a regression problem. A number which is discrete becomes a discrete problem. Okay. Now is it clear? So we have a lot more students today. So I would really encourage each one of you to interact and just let me know wherever there are any queries. Okay. So now talking about the supervised machine learning, there are different type of algorithms which are present. Okay. Uh, Let me go back over here. So we have linear regression problem, we have decision tree, we have logistic regression, we have support vectors. But in regression, we can see there's linear regression. Rest of them do work with regression techniques, but majorly focuses on the classification part of the supervised learning. Okay. We are going to go through each one of them. Today, our only focus is going to be linear regression. Okay. So just like I told you, what are the different types of examples? Okay. In unsupervised machine learning, we are going to talk about it now. So this was nothing but any type of data which has certain labeled target. But now let's talk about what exactly falls under unsupervised machine learning. Now let's take a certain scenario. Okay, you are a data scientist and certain manager. Suppose your manager comes to you like, okay, guys, uh, this is my company. I'm trying to sell car to customers. Okay. I don't know who to sell my car to. Okay. This is the data. My data contains people who came to the showroom, people who bought my car, and people who didn't bought my car. So there are certain columns like name of the customer, okay, age of the customer, gender of the customer, maybe there's a salary of the customer also, and there's finally certain things like bought or not bought. Okay. Now, can you help me decide which demographic of people are buying the most, or which demographic shall I consider? So for now, let's just forget about this thing. Okay. Let's only talk about these 4 or 5 topics. Okay. Now the thing is, I don't have any label data. I don't know what to predict. I have nothing right now. Okay. This is the only data I have. And they are saying who are the most people who are coming to me and how can I make them buy our cars. Okay. So what you're going to do is you're going to drop this particular thing down and let the computer decide what exactly it is trying to figure it out. Okay. So suppose let's take the gender, sorry, age and salary. Okay. Let me try to predict it over here. Suppose this is the graph. Okay. This is the age and this is the salary. And suppose there are certain points. Okay. Over here, over here, over here, and over here. So this tells us people who are less in age have less salaries, or sorry, more in age and less salaries. These are falling over here. Less in age and more in salaries falling over here. And medium age salary high over here. Very old age salary is over here. So I am able to segment these things. Okay. And then I'm going to do some target marketing. Okay. The very easy example is always look at the ads which you are going which you are getting in your YouTube compared to your parents or your kids. Okay. You are going to see tremendous difference in between them. How exactly are they able to do this? This is called as the classification. Sorry. Yeah. This is called as the clustering problem. Make a cluster and target the market differently. Okay. So suppose uh, less salary or less age, more salary, try to show a roadie type of friends. Okay, they are going on a Ladakh trip. Okay, and they are enjoying in your car. They are going to buy this product. Okay, more age, more salary. Try to show them perks of the car. Maybe show ventilated seats. Maybe show uh, recliner seats, something like this, massaging seats, anything. uh, More in age, less salary, maybe should show zero cost EMI plans. Okay. So this is how the target marketing works, where you don't know how to exactly segment it and you just give unlabeled data. So over here, the data becomes unlabeled. You don't know what to predict and you let the algorithm decide how do you make the cluster out of it. And then your business knowledge is going to help drive the innovation or drive the analysis. Okay. So semi-supervised is a type of algorithm which is hardly used, but it's like giving most of the data as labeled, some of the data is unlabeled, and then work on it. It's like a blend. Okay. And finally, there's a reinforcement type of data. Let me just show you that also. Reinforcement is like a type of algorithm which is used in your cars. Okay. Autonomous cars, how exactly self-driving cars work. Okay. If they go into certain pothole, are they able to reattune their algorithm quickly enough that they can help the car get away from the pothole, something like this. So there are a lot more advanced type of algorithms which are working over here. We are going to look at them one by one. Okay. For now, only introduction is going to be there, what exactly is happening. Okay. So reinforcement learning is a type of machine learning where algorithms learns from the environment by performing actions and receive either a reward or penalty. Okay. If you are doing correctly, you are going to get rewarded. The machine learning algorithm is going to work fine. If you did something wrong, it is going to give the penalty and the machine learning algorithm is going to learn again and then deliver the answer. That is what reinforcement learning is. It is going to be a cyclic event. Okay. So this is the environment. This is the input data. If the answer is correct, you are going to reward it. If the answer is incorrect, it is going to penalize it, and then it is going to give the out. Okay. We are going to talk more about it further, but very good example of reinforcement learning is anybody of you uses YouTube Premium Music or maybe Spotify or maybe any type of music app. Have you seen that you're listening to certain music and then once the music ended, different music start or different song starts, but you immediately change the music? What happens that the algorithms learn, okay, so the user is not liking this genre or this particular music, let's give it different genre. Okay, then a certain different type of genre comes up. If you start listening to it, it is going to stick to that genre until unless you change it. So as soon as you skip the song, it penalizes the algorithm. It gives certain different answer, and once you are playing the song without interruption, it is like a reward. So reinforcement learning is a very good, shall I say, a product in terms of recommendation systems. Okay. Any questions so far? So with this, reinforcement learning are games. If you're trying to play very good, the bots are going to become very difficult. If you're playing very bad, the bots are going to become easy to target. Self-driving cars, autocorrect tools, search recommendation engines. Okay. So with this, guys, I gave you a very quick and very brief introduction of what all you are going to learn throughout this particular module. Okay, I hope you're feeling excited about it, and we can get started from the very first algorithm from our session today. Okay, so first of all, let's talk about all the packages which we are going to use in Python for this particular module. Okay, I hope you already have heard about NumPy. NumPy is a numerical Python library. Majority of its code is written in C. That's why it's very quick in sequential calculations. Okay. Matplotlib is for what? Let's see. I think it's already given over there. Sorry, I can't ask you this question. So Matplotlib is used for data visualization. Pandas is used for all the data manipulations like handling missing values, handling outliers, pivoting, group buys, etc. Okay. Now, these two are going to be very new algorithms for you, or shall I say new libraries for you. One is SciPy and other is Scikit-learn. So SciPy solves the mathematical equations and process algorithms, whereas Scikit-learn offers efficient versions of common algorithms. Okay, we are going to use them very diligently and very deeply so that nothing becomes overwhelming for you. So don't worry about it. Okay. Okay. So now let's deep dive into the first part of today's topic, which is going to be supervised machine learning. So guys, just like I told you, any data which is coming with a label or coming with an answer and you have to learn from it is going to come into supervised machine learning. You have a supervised data. Okay. So supervised data is a type of machine learning where the algorithms learn from the label data. Okay. So let me just copy this particular and paste it over here. Let's see if I can paste it. And let's paint it white. Okay. Okay. So let's see this particular supervised learning is a type of machine learning where algorithms learns from the labeled data. Okay. Consists of input output pair. In supervised learning, you train the algorithm on data set that includes input feature. Okay. It includes input feature and corresponding correct output label. Okay. The goal of the algorithm is to learn the mapping relationship between the input feature and the output feature. This is a theoretical answer what exactly supervised machine learning. Okay, let's try to understand this. Okay, let's first, for the first example, example number one, we are going to take as house price prediction. To predict house prices, there are certain columns. Suppose size of house, number of rooms, number of washrooms, mm, number of hospitals nearby, and maybe let's say city it is in. Finally, we will have, uh, my bad, let me just make it a bit more straight. Price of the house, right? So suppose the size of the house is 1200 square feet. It has 3 rooms, 2 washrooms. There is one hospital nearby and it is in Indore. Okay. And the price of the house is somewhere around 70 lakhs. Okay. Similarly, the house is 1500 square feet. It is 3 rooms, 2 washroom, 3 hospitals nearby. It is in Delhi. This particular is like 2 CR, 2 crore. Similarly, there's a 2500 square feet, 4 rooms, 4 washrooms, 5 hospitals, and this is in New York. It is somewhere around, I don't know, maybe $2 million, something like this, right? So what exactly is happening over here, guys? All these features over here, these are the independent features. Okay. And over here, sorry, this also, city also. And the final one, which is price. Price is your dependent feature. Okay. Your price depends on all of these things. So if I train my data or train my model and I get a new data, my house is 1700 square feet. It is containing 3 rooms, 2 washrooms. There are 2 hospitals nearby and it is in Ahmedabad. What is going to be the price of the house? Okay. So what exactly happened? This is my label data in which price is my labeling, or which is also called as your dependent data. All the other features are the independent data. If there are no questions, please feel free to drop in no questions in the chat window. All right, let's take one more example then. This time we will take an example of uh, students data. Okay. In this data, let's talk about 2 to 3 columns. First of all, we have IQ of the student. We have number of hours student studied. Okay. And then we have pass slash fail. Okay. Where 1 equals to pass and 0 means fail. This is my data. Okay. Over here, one of the student is at 90 IQ. He or she studied for 5 hours and the answer is 1. Means they studied well. One student with IQ of 120 studied barely for 2 hours, still passed. One student with IQ of 75 studied for 1 hour, fail. Okay. Similarly, one student IQ of 100 studied 0 hours, obviously failed. Okay. Now, what exactly is the independent feature and the dependent feature? Can anybody tell me? So if I say X is my independent and Y is my dependent, so these two become these two become my x's, x1 and x2. This becomes my y. Okay. Wherever the y, or shall I say the dependent feature is there, which I want to predict, then it becomes a supervised machine learning problem. Over here, I was trying to predict something continuous. This became my regression problem. Okay. Over here, I was trying to predict something as discrete, pass or fail. This becomes my classification problem. I hope beyond this, there's no need to like make you understand how exactly regression or classification or supervised machine learning works. Is there any question? Do let me. So in the first exam, you made price as labeled, and the second, so always label will always put in the outcome. That is correct, Shivananda. So there is one good image which is going to even help you. Okay, so suppose, okay, this. Let me just try to just take this much snapshot and paste it over here. Guys, yeah, you are a data scientist. Okay. In one location over here, you're trying to predict the weather. Okay, what is going to be tomorrow's weather? This is what you are going to predict. Over here, you are going to predict, is it going to be cold or hot? Can anybody tell me which one is a regression type of problem? Which one is a classification type of problem? And why? Are you sure? Need more answers over here? So first one is regression. Very good. Just like we told you. Anywhere which we are trying to predict something continuous becomes a classification problem. And anywhere where is a discrete type of prediction, then it becomes a classification problem. So continuous becomes your regression, sorry, becomes your regression problem. Discrete becomes your classification problem. Okay, good guys, good. So now what exactly is happening? I'm going to give you a very brief introduction of all the algorithms, but you are going to go a bit more deep dive in future as well. Okay. So what we have learned so far is something this, like this is a regression problem. This is a classification problem. But now why not talk about what kind of algorithms handle different kind of scenarios? Suppose I give one team regression problem. You have to answer what will be the temperature tomorrow. So you are going to deep dive into the different type of things like what is the purpose? Predict a continuous value. Okay. Example, predicting exact temperature for tomorrow. Variation of thermostat ranging from this. What will the temperature tomorrow? But if my problem becomes what kind of weather it is going to be, is it going to be hot or is it going to be cold? Then it becomes a classification problem. So there are different type of applications for different type of scenarios like HR operation. Imagine you are a recruiter finding the best candidate for the job vacancy. Supervised machine learning can help you shortlist the resume. Okay. And accept or reject the certain customer. Finance, or sorry, emails. It can be spam or not. Manufacturing, right or not. Maritime industries. These are all working around with these kind of machine learning algorithms. But there are certain different algorithms for different scenarios. Just like if there's a continuous type of problem, you can always use a linear regression equation. If there's a logistic regression, oh sorry, if there's a classification problem, you can use different algorithms like logistic regression, naive bayes, k nearest neighbors, decision tree. All of them come under, shall I just take a snapshot and take it over here. So if I just zoom it out and bring it over here. So, okay, the first question is going to be, what kind of problem is, what kind of supervised machine learning problem are we looking at? Okay, if you answer this correctly, okay, so suppose you say this is a regression problem. Okay, so over here I have multiple algorithms, but regression problems best friend is linear regression. Today we are going to cover this thing. In linear regression we are going to talk about simple linear regression, uh, then we have multilinear regression, we have polynomial, and then we have further enhancement which we are going to cover tomorrow, like L1, L2, and elastic net. So these are all the algorithms which you are going to use for the classification problems. Okay, any classification, sorry, regression problems, any continuous one. So all these algorithms can be used. Depends on what kind of problem you are dealing with, or you can use each one of them and then you can pick the best model performing. Okay, if you have the classification problem, like whether tomorrow's weather is going to be hot or cold, then you can either use these algorithms: logistic regression, naive bayes, k nearest neighbor, decision tree, random forest, svm. There are even more algorithms, but these are what you are going to go cover in the classification scenario. Okay, so first question is, what is your label data, continuous or discrete? And according to that, you are going to pick up the particular algorithm. Okay, so why not start with our first simple type of algorithm, which is called as simple linear regression. So to understand that, I'm going to take a very good scenario: simple linear regression. Suppose there is one data. This particular data has your years of experience and your salary. Okay, this is your x-axis, and this is your y-axis. So this particular firm has collected all the data of different employees which work in their firm. Okay, and what do you think, or how do you think the data is going to look like? Is it going to look somewhere like upwards, or it is going to look somewhere like downwards? Obviously, as your years of experience grow, your salary grows, right? So the data is going to look something like this, right? Something like this. I just made a very random thing. So we can say, right, if my years of experience increases, definitely my salary is going to increase, right? But what if I take one more scenario in which this is my marks and this is my number of hours uh, TV watched. What kind of data is it going to be, positive or negative? As the number of hours increases by a student who's watching TV, it is going to be something like this, right? So if we try to make a relationship, it is going to look something like this, downward. Similarly, if I try to make a relationship, it is going to look something like this, upward. So over here, I can say that number of hours of TV watched increases, my marks are going to decrease. So this becomes a very good example of positive linear relationship. And the below one becomes negative linear relationship. So guys, I think in your 8th standard, 9th standard, maybe 10th standard, you might have seen this kind of graph. And uh, this particular type of relationship between two features is called as your linear relationship, right? If certain thing is increasing, other is also increasing, or certain thing is decreasing, other is increasing. Okay, so positive or negative. Now this particular line is called as a relationship line between these two features. Okay, can anybody tell me, we in our school time learned this particular equation? If we can equate, what was that particular algorithm, or shall I say formula? Very good. Y is equal to mx plus c, where your c becomes your constant. It is also known as intercept, and m becomes your slope, or it is also called as coefficient of variable x. I hope each one of you are trying to like recall this. It's a nostalgic type of moment. People are looking at this particular equation. Y is equal to mx plus c. So this particular algorithm is used to give the relationship. So this gives us relationship between x and y. Okay. If the relationship is positive, this equation is going to be positive. If the relationship is negative, this is going to look negative. This particular algorithm was like this particular formula, which we saw y is equal to mx plus c, was something which we used in our school time. Okay. But if now that you are a working professional or trying to enter this particular data science field, this particular algorithm is actually written as z is equal to, shall I say, no, this one is still advanced for you. Easiest will be this. Y is equal to beta 0 plus beta 1 x. Okay, where beta 0 becomes your constant or slope, and beta 1 x becomes your intercept. Okay, or shall I say slope. All you need to do over here is to find this relationship all the time. Okay, but in real scenario, a salary can't only be predicted from years of experience, right? That's like only giving credit to people who are senior, but nothing else. In real world scenario, the algorithm might look something like this, or the table might look something like this. There's like years of experience. Okay, what kind of college a student is coming from, um, what kind of experience, relevant experience. Okay, previous package. So this becomes a very big scenario, and then we can say salary. Okay, so all of these four becomes the independent features, and this one becomes your dependent feature. As this time, if we try to make a certain type of algorithm, it is going to look something like this. Y is equal to, let's, for the ease of this equation, I'll call this as x1, x2, x3, x4, and this is called as y. So this becomes y is equal to m1 x1 plus m2 x2 plus m3 x3 plus m4 x4. Okay, plus the C. Okay. This becomes a very good example of multi-linear regression equation. Any questions so far, guys? I hope it's easy to understand. Perfect. So with this, what I'm going to do is give you guys a simple type of data. Let me try to upload it over here. Let's see, can I upload it over here? File. Please download it and do let me know if it is downloaded at your end. Okay. For the class, I'm giving it this way only, but um, I'm going to upload it and you can easily download it from your LMS portal in future. So first of all, try to download it. And if you're not able to download, just let me know. Okay. Were you able to download it, guys? And once you have downloaded, I will recommend you guys to open up your Jupyter notebook. Okay. Even I will do so. Okay, let's see. So this is nothing but session 1. What is the date today? It's 2803 2026. Okay. So guys, let's recall what we have learned so far in Python. Okay. So let's first of all import the necessary libraries. Okay. Let's go with import pandas as PD, import NumPy as NP, import matplotlib.pyplot as PLT, import cbon as SNS. Now I will import the data. Okay, data equals to read underscores and I will just copy the data where exactly the data is. Once I download, oh sorry, once I read this, I can do data.head. Murali, I just shared it on the chat window. Just scroll up. I have shared tv.sales.csv. So guys, this particular data set is nothing but a type of data which talks about uh, a certain product. Okay. Certain products TV advertisement corresponding to its sales. Okay. Suppose it's like $230,000 of advertisement was done and the sales corresponding to it was 22.1. Similarly, $44,000 advertisement was done, then it only constituted 10 sales. So if you just read through it, the data set contains information of relationship between TV advertisement expenditure and the product sale. Okay, each represents single observation with TV means the amount of spend on TV advertisement. Sales means resulting sales volume. Okay. So this is a very simple linear regression equation. Okay. Simple linear means there's only one independent and one dependent. So I hope people know what is simple linear equation. If you open up the Excel, this is how the data looks like. So this tells us how much budget was spent on the TV advertisement and how much sales were corresponding to that much marketing spend. Okay. Can you help me upload the CSV? Murali, at this point, please use ChatGPT on how to upload it because my Jupyter Lab is not working. I use Jupyter Notebook over here. I believe you are coming from Python background, guys. Okay, so coming back over here, we have TV spends and the sales. What kind of problem is it? Is it a multilinear regression problem or simple linear regression problem? Murali, I feel it's okay. Yeah, it's a simple linear problem, right? So what exactly is happening over here? We are trying to find a linear relationship between the TV spends and we have the sales. Okay, this is what we are trying to find out. This is becomes our X and this becomes our Y. What we're trying to do is trying to find a Y is equal to mx plus c. If we are able to create this particular equation, any type of spends comes up. Suppose $200,000 are spent. How much sales are going to be there can be answered through it. Okay, because m value is going to be somewhere around 0.1, and if x value becomes 200 and c is 3, so it's nothing but 0.1 into 200 plus 3, that is 20 plus 3, which is 23. These are going to be the conversion. Okay, so this is how it is going to help us make the predictions. Okay, and if I just go back over here, do you know what can be the equation for uh, calculating this thing? What can be the equation to know how we get the value of m or how we get the value of c? For that, you might have gone through like in school time as well. This is the equation. Let me just copy it and paste it over here. Bring it over here. And this is the equation where a is nothing but our c and b is nothing but our m. Okay. So this is how our equation looks like. Okay. Any questions so far? You don't have to learn this equation. All you have to do is call this particular formula in Python and it is going to do everything for you. Okay. What I'm going to do is I'm going to first go back over here and my first step is going to be something like this. My flow is going to look something like this. First, separate your independent and dependent features. Okay. So independent being your X and dependent be your Y. Okay. Second, split the data into training and test set. Okay. So why exactly we are trying to split the data? Because with the training data, the model is going to be trained. With the test data, the train model is going to try and predict the test data. Okay. And it is going to give a certain output. And then that output is going to be compared with the actual value. This is how we are going to do the whole equation. Okay. Are these two steps clear? Just let me know. We are going to do these two steps in Python. Okay, then let's try to do that step first. Okay, so the first step is going to be split the data how we can do it. There are many ways which you can achieve this thing. You can use as simple as your drop feature. You can use values feature, so anything. Okay. So over here, what I'm going to use is I'm going to use a ilock feature. I'm going to give capital X equals to data dot ilock. Okay. And I'm going to use 0 dot values. Okay. So this is going to give me an array of feature. Similarly, on the same notion, I'm going to copy this and I'm going to say y equals to, but this time as 1. So what exactly is happening? It is going to split the data into train and test set. Now, if I look at x, this is the whole value. Okay. So I'm going to take a pause. You can copy this code. We don't want to, oh, Ritesh, we are going to split the data in train and set later, but as of now, we are splitting the data between the independent features, which are going to use to predict the dependent feature. Okay. So for now, first we have just split it between X and Y. Then we are going to split the rows. So this is just a step 1. Okay. Any questions so far, guys? Or anything which is not clear? Perfect. So before going to step 2, let's go for a break first. Okay, it's been 2 hours which we have been studying. Okay, take a break. And for the students who were not able to open up their Jupyter Lab, try to figure it out. I think we can comfortably go for 20 minutes break. Okay, so in 20 minutes you can take a break, or you can just figure it out how to open up Jupyter Labs. So it's a prerequisite, guys. I don't want to be very much blunt, but since you are coming machine, it's a prerequisite that you are well aware of how to use Jupyter Notebook or Jupyter Labs at the minimum. Okay. Okay. All right, guys. So as of now, uh, we started with our simple linear regression problem, right? And in this, what we're trying to do is to make an equation between the amount which is spent on the telemarketing, which is corresponding to the amount of sales it was able to do. Got it, right? And we were able to, first of all, distinguish, or shall I say, divide between the independent and the dependent feature. X being the independent feature, Y being the dependent feature. Okay. This was the step 1 over here, to separate the independent dependent feature. Second is to split the data into training and test set. We are trying to split the data into training and test set so that we can train on the training part, and then we can test the model on the test part. So guys, what are we trying to do is we're trying to create the equation. So I'm recapping. We are trying to make y is equal to mx plus c. This equation is going to be prepared. Okay. Suppose if I take this particular Excel, okay, and this is going to be my sales, and let me call it as predicted. Okay. After certain scenario. So this is going to be maybe 20.2, 22.2. Okay. So this is going to be predicted and this is going to be actual. So that's why we are going to use the test data in which we already have y, and we are going to see the y hat. Y hat is nothing but the predicted value. Okay. And we are going to see how far or how good or how close the actual value and the predicted value is. The closer the actual value is to the predicted, the better our model is performing. Correct? Why? Because we are trying to be as close to. Okay. So what we have to do is we have to go back over here and we have to now import a certain library. Okay. First of all, I'm going to click over here. The library name is from sklearn dot model selection import train test split. Okay. After this, I'm going to do one thing. Let's just import it first. Okay. Now I have two things, X and Y. Okay. So suppose this is my data and suppose this much I want to make as the training part. This much I want to keep it as the test part. I already have divided between X and Y, right? This is nothing but my X. This is nothing but my Y. Let me try to add over here. This is going to be nothing but my X. This is nothing but my Y. So now I have to divide the X into two parts and the Y into two parts. Okay. So the X division is going to be called as X underscore train, X underscore test. Similarly, the Y part correspondingly becomes Y underscore train and Y underscore test. Okay. So this is going to be how I'm going to write it. So how do I do it in Python? So it is going to be X underscore train, comma, X underscore test, Y underscore train, comma, Y underscore test equals to, I'm going to call this function, which is called as train test split. Okay. And I'm going to push the X and Y, which I created over here. X and Y, which I created over here. Okay. Then I'm going to say the test size, how big the test size should be. Suppose I have 100 rows. How many rows shall I keep for the test and how many rows shall I keep for the training part? Okay. So over here, we call it as test size. If I give it 0.3, that means 30% of my data is going to be holded for the testing purposes. The model is going to be trained on the rest of the 70% of data. Okay. Finally, there's a random state. Okay, which can be any number of your choice, any number. But over here, I am keeping as 42 and I will recommend that you should also keep it as 42. Why? Let me just talk about it now. Suppose my data has, this one has 200 rows. Okay. Now, if this particular data needs to be broken down into train and test set, my algorithm, what it does, it is going to take these two as the training part, train, train, test, train, test. But on your system, it does something very different. It does something random. Test, train, test, train, test. What do you think is going to be the problem? This is my system. Your your trainer, like system X, like any system or system A. And on system B, now what exactly happens is that system A model and system B model are trained on completely different data because the training and test division was done very much randomly. Okay. That is going to give slightly different results in both the systems, system A and system B. But what if I want the same type of division, which is done on system A to be present on system B as well? In that scenario, I have to put a certain column, which is random state. This number can be anything, anything. But as long as your system random state number is same as my system, both of our division is going to be same. The column A, sorry, row A is going to be maybe training, row B maybe going to be test, and it is going to be same for both of us. Okay. That's why it's very good or very important to have the random state in your equation. So let me put a comment over here. Okay. Rakshita, no, it can be any number as long as your code number and my code number are same, it is going to work perfectly. You give me a number, I'll put it over here, and I will recommend everybody to put it the same number so that this division will occur same. Okay. So test size is nothing but, suppose you have 100 rows. Okay. How much rows do you want to hold for the training part and how much rows you want to hold for the test part? So let me also write it over here. Test size is the amount of rows, or shall I say amount of percentage of rows. Okay. Whatever you are comfortable with, rows which you want to keep aside for testing of model performance. Okay. Suppose I have 100 rows and I'm saying 0.3 means 30%. Okay. So it's from 0 to 1. Okay. 0.3 means 30% of data I'm keeping aside so that on 70% train the model and on 30% test the model's performance. That's it. Okay. You're welcome. So as soon as I run this code, guys, okay, let's see xtrain, how exactly xtrain is looking like. So you will see this is the xtrain. And if I say y train, this is how the y train is looking like. So let me just zoom out. This is X train and this is Y train. Any question so far, or shall I move forward? If you want to, if you haven't copied it, the code yet, I have also pasted in the chat window. Shall we move forward? I need few more confirmations. Only got one. Sure, Ravi, I can do that as well. There you go. Uh, just a second. Let me try to find a code share for you guys. But I think it needs login setup. It's okay. I will just copy paste it. Uh, shall I move forward, guys? Now both of these things are done. I miss splitting part. Ravi, this is the splitting part. Let me just copy it again, paste it over here. Okay. This is how you split the data. Okay. And just before your message, I uh, wrote down the library which you have to import. Okay. So let me just show it over here again. See, first of all, you import this before the break. Okay. You have to split the data into dependent and independent feature. Let me just copy this and paste it as well. Perfect. So guys, what we have done so far is we have completed these two tasks. We have separated the independent dependent feature. We have separated the data into train and test. Now, what do you think is going to be the next part? Next part is nothing but train the model on X train and Y train. So X train becomes your independent feature. Y train becomes your label, or we can also call it the dependent feature. Okay. How do you do it? Let's find it out. We go down, we go from sklearn dot linear model underscore model import linear. Please look at the alphabet, shall I say, the capital letter. Okay. L is capital over here, linear, and R is capital, regression, linear regression. Okay. Once you do this, you will first create a variable. Let me call it as LR. LR, or shall I call as LINREG equals to, I will call this function. Okay. All I need to do is copy this dot fit. In this, I'm going to give X train and Y train. That's it. Let me just copy this code and paste on the chat window as well. So let's see, there's some value error. Let me see why exactly this value error is coming. Okay, there's some value error which is coming. Let's see what exactly is the problem. Okay, what if I, instead of doing this, if I give it like this. Okay, so guys, there's a small change which you need to do. Let me just paste this one. The earlier the code was this. What I'm doing is adding this thing. Okay, this way this becomes a one-dimensional, two-dimensional data. Okay, let me just copy just this row. Okay, update your the way you were um, splitting the data between independent dependent feature. Okay, only the X value needs to be updated. Y was same. Okay, once this is done, rerun the code where you are splitting the data into test and train. Once you run this as well, if you just go down, it should work now. Yeah, it worked. Let me say it again. Okay. Over here, I updated the X part. X part needs to be a two-dimensional array. So for this, I need to add this thing. Yeah, it's not creating any problem over here for Y, but for X, it was creating the error. Okay. That's why I was looking at the error over here. That's why I just changed it and it is working fine. Okay. So higher dimension data in simple linear regression creates a problem. We need to give it in a linear format, Pragati. Okay. That's why this particular error came up. I can't replicate it again because you will see that the shape was something else which was required, but we gave a higher dimension data. That's why this issue came up. Okay. So were you able to come up to this particular point, guys? Once you reach to this point, just let me know so that we can move forward. Okay. Need few more confirmations. Thank you, Rakshita, for the confirmation. Need few more confirmation first. No, Ravi, you don't have to memorize anything. Have you heard of open book test? Right? So what is the agenda of open book test? That you know where to find the information. So machine learning or a data science field is like an open book test. You should know what to find on Google, on blogs. Okay. And that's all you need to know. But if you want to dig deeper as a research data scientist, then you need to know each one of these things. Okay. So for now, what I'll say is you should know how the algorithm works. Okay. Ritesh is sending something. Let's see. Yeah, it's perfectly fine, Ritesh. It's perfectly fine. Okay. So after this, the model is trained, guys. Now what we'll do, we'll try to visualize it. For this, I'm going to share the code again on the chat window. Simply copy it, paste it over here. And all you need to do is just call this thing. I'll just copy it, paste it over here and call it. And this is your linear relationship between the TV sales, oh sorry, the TV advertisement and the sales. The blue line is the linear relationship between them. Interesting, isn't it? Take a look at this graph. Okay, what I'll do, I'll try to just copy this and bring it over here for further insights. Let's try to see what exactly is happening over here. First of all, what kind of relationship is between the TV sales? Oh, sorry, TV advertisement and sales. Is it a positive one or is it a negative one? Positive, right? As long as you are increasing the advertisement budget, your sales are also increasing. So suppose uh, what is happening over here? Let's try to go slowly. At certain point, that this particular point, we can see the advertisement budget was around 10,000 rupees. Okay, 10K. And the sales which we got was somewhere around 140. Okay, conversions. Similarly, at certain point, on an actual case, the budget was around $17,000 or rupees, and the sales which we got was somewhere around 165 or 170, something like this, right? So these were the actual points. But now you will see we were able to create this linear relationship. The only thing which we are able to see is that when the actual value is this, the predicted value is somewhere over here. When the actual value is this, the predicted value is somewhere over here. Actual value is this, predicted is same over here. So this is a correct. But this is certain error which is coming, right? First of all, we know the dependent feature is denoted by y, but the predicted feature is denoted by y hat. Okay. Do we know the difference between them? This is nothing but the dependent feature. And this is nothing but the predicted feature or predicted value, anything. Okay. And the distance between them determines how good our model is able to predict. If we can see there is a very long difference between actual and the predicted, like this point and this point, and this is very much frequent, we can say that our model is not performing good. But we can see majority of the points are very much close to the actual dots, right? Won't you say this? Majority of the points, just like look at this particular area, very much close to the actual value. Similarly, this area is very much close. But the only problem which might be created are these points and maybe these points, right? So guys, as a homework, what I will recommend you, this is the formula which I gave you, right? What you will do is sit on your time and try to do this whole equation, the whole equation on Excel. Okay. Copy this, paste it over here. Oops, whatever. Let me try to copy it again. Copy it, paste it over here, and try to create the whole equation by yourself. And you are going to see how exactly what takes so much time in Excel. Like this is going to be x square. You're then going to make xy. Okay. And then you are also going to make y square. No. So how do you make x square? You are going to do this into this. How do you make xy? This into this. Okay. Do it at your own pace and you will be able to find the equation. You are going to find A and B by yourself. You will find that how tedious this task is if you do it manually on Excel. But if I want to find coefficient or intercept, all I need to do is call this function, train the model, and it is going to do all the job for me. Okay. If I want to know what is the value of coefficient or the intercept, all I need to do is copy this, paste it over here, dot coef underscore. And this is nothing but value of coefficient of linear equation. Similarly, if I want to find the intercept, linear regreg dot, I think it's INTER underscore. No, what is the, let's see, intercept, uh, linear regression, Python code. Let's see, what is exactly the code? It's intercept underscore. Okay, this is the one. So I'll just copy it, paste it over here, and there you go, guys. I got both the coefficient as well as the intercept. Both the values are here. So if I have to make the equation, it is going to look something like this. So print y equals to, can I do value of it? No. Let's see. Can I call it separate way? Float. Okay. So it is going to be, just copy it. str float plus x plus copy str float. Let's see. So this is how my equation is going to look like, guys. Y equals to, this is the m value, and then we have x, then we have c. So plus, this is how the equation is going to look like. Let me zoom in. This is my linear equation between uh, the TV advertisement and the sales. Paste it over here so that you can also understand. Okay. Doesn't work this way. I'm rounding the decimal values to 2 decimals because it is becoming very cumbersome. Incomplete. Okay. So this is how the code is going to look like. This is the updated code. So y equals to 0.05x plus c. Copy and paste. Please refer to the final code which I shared. Okay. This is how the code is going to look like. So guys, if we just go back over here, what we noticed was that there were certain type of errors, shall I say, that the actual value was somewhere here, but my prediction somewhere here, but my prediction was way below. In such scenarios, suppose I spent 100,000 rupees or $100,000 on TV advertisement, and my report said that you are going to have sale of maybe 35,000 product, but somehow it didn't meet this and only 20,000 product were sold. You will see that your model predicted this. The manager is going to come back. Hey, that your model predicted that it is going to have so much sale, but why only this much sale happened? So what is going to be your answer? You are going to say that model was not as good as this thing. So the natural question comes up. The question comes up, how do you test efficiency, or shall I say predictability of the model? So the answer to this question is you do model evaluation. By the term model evaluation, what do you mean? That you uh, see how good, or shall I say how close to the actual value is my model predicting. Okay. So for this thing, to evaluate your model's performance, there are a lot of different metrics which are present there. We are going to talk about them. First of all, we are going to talk about R square. Second, we are going to talk about MAE. Third, we are going to talk about MSE. Finally, we are going to talk about RMSE. Okay. So let's start with our first, shall I say, model evaluation metric. Okay. This is called as R square. Okay. Let's talk about it. So what exactly is R square? R square, I have a very good, shall I say, screenshot for it already at my kitty over here. Okay. So R square is a very good metric which is used highly in linear regression equations, whether it's simple linear, multiple linear, or polynomial, anything. And it is like termed as coefficient of determination. Okay. And the formula for it is SSR upon SST. What is SSR? What is SST? Let's talk about it. I told you Y is nothing but the actual value. Y hat is your predicted value. Okay. Everybody knows about this? Any questions? Now, is there any metric which can give us a range between 0 and 1? Okay. 0 and 1. Closer to 1 value means your model is amazing. And farther away from 1 means your model is very bad. Okay. That is what R square gives you. And how does it calculate it? It calculates by dividing SSR by SST. SSR, just look at it closely. It is nothing but the predicted value minus the mean dependent value. You don't have to learn this formula. All I'm telling you or showing you what exactly is going on in the backend. Whole square, and then you're summing it up. Divided by individual value minus the mean value whole square. So these are mathematicians, statisticians who came up with this formula. You are a data scientist. You are going to be applied statisticians. You don't have to learn these formulas. All you have to remember is what is R square? What is the range of R square? Okay. What is the value of R square actually tells you? Okay. Is it good to have any R square value closer to 1 or closer to 0? This is what you have to remember. Okay. So divided by summation of uh, y minus mean of y whole square. Okay. This particular thing is called as R square. Okay. R square value is between 0 and 1. Okay. Where closer to 1 means a very good model, and vice versa. Okay. Closer to 0 means bad model. So why not try to find how exactly our model is performing over here, right? Let's see R square value. Okay. So first of all, what I'll do is I'm going to make y test underscore pred. Okay. So my y test prediction is going to be nothing but linear regression. I'm going to call the model dot predict x test. Okay. These are going to be my predictions. Let's do it. Now, looking at this code, what do you think is happening? Can anybody tell me? I am feeding the X test, means the data which I hold it up for the testing part, and using the model to predict the value. And these are my predictions. Now that I have Y predictions ready, I have the Y test ready. I'm going to compare both and I'm going to see how good my predictions are. That's what I'm trying to do. Shrisha, anything which is closer to 1, just like I told you, is good. But acceptable range is somewhere around 0.75 and upward. Okay. 0.8 is very good. 0.9 is amazing, right? So anything above 0.75 or 0.8 becomes a good model. So guys, why not try to find the R square value, right? So how do you find the R square value? For that, you have to first import sklearn dot metrics import. Let's import everything like mean squared error. We are going to talk about it. And for now, R2 underscore score. Okay. I metrics. Okay. Now let's R2 score equals to R2 score, or shall I just say R2 test score? Okay. And I'm giving Y test and Y test underscore pred. Once I do this, what I'm going to do is I'm going to print test data R square value is guys. Now this is the result. You are a data scientist. You created a model. You pushed the test data to make the test predictions. Now you compared the test values or the predicted values with the actual values. And then you found the R square value. R square comes out to be this number. What do you think about the model? What are your insights? Tell me. So guys, anything which is close to 0.5 becomes a bad model. Okay. 0.67 is like low average score. Okay. We can do a lot of things, Trisha, guys. Okay. As of now, we are just judging this model. We are going to talk about new steps further. But as of now, just look at it. And you see that, okay, my model is not that good, right? So this is one of the metric. Okay. Now we also need to know other metrics as well, which we talked about. First of all, let's explore the full form. This is called as mean absolute error. This is the formula for this is summation of y minus y hat Okay, this is nothing but mean square error. So, oh, and it is divided by n. That's what I mean. This is nothing but y minus y hat whole square divided by n. And this is nothing but root mean square error. And this is nothing but square root of MSE. Okay. I think these formulas are self-explanatory. So what we are trying to find is what is the difference between the actual value and predictive value on an average. So this is what we are trying to find. Different type of metrics are used in different scenarios, but these all are very much important. So why not try to find the mean square value over here? I already like imported this. So why not just copy this, paste it over here, give it y test and y test spread. Okay. Save it as MSE test. Okay. And I'll just copy it, paste it over here. And it is coming something like this. Now, if you want to call root mean square error or MSE, so mean absolute error, root, I think uh, Scikit-learn RMSE. What is the code? Let's see. It's root mean square error. Let's just copy this, come back over here, root mean square error. I'll import everything and I'll try to paste everything over here. So this time I'm going to call absolute error, and this is going to be MAE. And I'm going to copy this time root mean square error and RMSE. Okay, so these are all the matrix which can help you understand how good my model is performing. Positive values. It is supposed to be positive Pragati, which is very good. But let's talk about it, guys, now. If I just go back over here, these are the evaluation metrics. Okay. First of all, uh, this tells us how far on an average the actual value is from the predicted value. So what do you think the number should be? The model should be good if then this particular number is smaller or larger. Let's see who can answer me this question. So Rakshita says the model is better if the value of these three metrics is larger. Is she correct or is she incorrect? Pragati says it's smaller. Okay. I'm giving few more minutes, a few more seconds for people to guess. Which model is going to be good? Where the values of these are larger or smaller? So I have model 1 and model 2. Which one should I pick? So the correct answer is smaller. We are talking about error. Error is nothing but the difference between the actual value and the predicted value. And the mean means the average difference between the actual and the predicted. Suppose a certain model gives the RMSC, suppose the MAE value as 200. Okay. But this particular model is giving 400. Which one is better? Model 2, right? 200. Similarly, these particular metric, these three are not capped between 0 and 1. There can be, so it's like any number, it can be infinity. Okay. But R square is capped between 0 and 1. Okay. It has certain drawbacks. That's why it's not used as much as these three are used. Okay. And which one is used when depends on what kind of problem you are using. So guys, if my value is centimeter and due to some equation it becomes centimeter square, can I compare these two? Of course not. Mean square error has certain problem that these are not in same unit because we are doing square. Just like we can't use variance as much as we use standard deviation. Why? Because standard deviation is nothing but root of variance, right? Because this changes the unit. If it is centimeter, it becomes centimeter square. Similarly, we don't use MSE, we use RMSE. Okay. Is it clear now? A good data scientist uses all these major metrics at the same time. Majorly these three. Till the time you are giving your response on this thing, I will like to come back on this particular graph. And we have also seen the R square value, right? The R square value for us came somewhere around 0.67, which we know is not that good for a particular model. That means, yes, Prateek. So we are going to talk about how exactly you can think of getting a particular model. Okay. So we saw that this particular line was not as good as what we thought it can be. That's why our R square value came out to be 0.69, which is not really a good model. Okay. We have to somehow increase it. There are certain ways you can do this. But for now, I will just give you one more thing. Because this particular data looks like this, maybe this is not a linearly separable data. Means the strict linear regression or strict linear relationship is not really a good idea. In this kind of thing, what we do, we go for a non-linear approach. One of the very basic linear approach becomes a polynomial approach. To understand polynomial, let's try to graph certain things. Okay, guys, if my equation is looks like x equals to y, and if I try to create a graph of it, how do you think is graph going to look like? It is going to look something like this, right? On both the directions. As x increases, the y increases as well. Okay. Similarly, if my equation looks something like this, x y is equal to minus of x, what do you think the equation is going to look like? So if y increases, so my y is increasing, my x is going to decrease, right? So it is going to look something like, not this, but yeah, the idea is correct. It is going to look something like this, right? Now, what if my equation is like this, y equals to x square? Now, what do you think the equation is going to look like? It is going to look something like this, right? What is the x cube y equals to x cube is going to look like? It is going to look even more sharper. What about y equals to x4? It is going to look even more sharper, right? So these are nothing but the relationship between x and y when we are including a power variable in it. And by power, we are talking about polynomial equation. A typical polynomial equations look something like this. Y equals to m1 x1 square plus m2 x2 plus c. The maximum power in this equation is 2. Similarly, if I want to show you higher power, m1 x1 cube plus m2 x2 square plus m3 x3 plus c. What kind of equation these make? These make a non-linear type of relationship between x and y. Okay. Uh, this kind of particular algorithm is very good as compared to simple linear regression. Why not try this in our own model? Okay. If I just go back over here, all I need to do is import polynomial regression first. Okay. So what I'm going to do is from, first of all, okay. So from sklearn dot preprocessing, import polynomial features where P is capital and F is capital. Okay. For now, you can stop writing. You just focus on my screen. Okay. I'll try to do it and I'll share the script at the end of the day. Okay. You can do it at your own pace. Once this is done. Okay. Now what I'll do is, first of all, I'm going to transform the data into polynomial data set. Okay. This is going to my first step over here. How do I do it? I'm going to call it as x train underscore poly. Okay, we have x test, x train, y test, y train. So I'm going to call it as, first of all, before this, I'm going to call this thing copy, paste, and let's give the maximum degree as 4, not more than 4. Means uh, x to the power 4 should be the maximum. We can even go further beyond. The only thing is it is going to make the data more complex and it might make your model perform a bit slower. In real world, this becomes a very crucial thing. So we are going to call it as poly underscore features. And I'm going to call this thing fit underscore transform. It is going to fit and transform both at the same time. Okay. X train. Similarly, for X test, I'm only going to transform it. So the natural question is going to be why only transform in test, but fit and transform in train? Can anybody think of any guess over here? So our model is trying to learn from the training data and it is going to implement all the learned thing into the test site. That's why the fit and transform works in the training data, but the only transform works in the test data. We have seen the same thing uh, over here also when we fit the data or prepared the model with fit, but at the time of prediction, what we did, we called the dot predict function. Okay. So similarly over here, the polynomial feature is going to get trained and transformed with the training part, but only the transformation with the test part. Once I do this, my polynomial regression data set is ready. Now I don't have to do anything new. All I have to do is do the exact same thing. I'll now call this model as poly model, and I'm going to call the same linear regression algorithm. Okay. This time, all I need to do is copy, paste, dot fit, x train and y train. Okay. Once I do this, the linear regression model is ready. What I'll do is exact same thing. I'll just copy this, paste it over here. I'm going to now predict. Okay. Uh, poly, poly. I think, yeah. Okay. Once I do this, okay, let's see. Poly dot model dot predict by test poly. Let's see what the error. X has 5 features, but linear regression is expecting 1. Okay. Let's see what is happening. It should work. Why it's not working? Oh, my bad, my bad. Over here, I have to give poly. Got it. Now it's going to work. Okay. So the ypred is ready for me. What I can do is, again, I'm going to score from here. So this time, ytest and ypred. Let's see what's the R square value is going to come like. If it is increasing, then it's good. So we can see that even after trying this thing, the model performance is still not good. So what we did over here, guys, we did simple linear regression. We got a result. We tried polynomial regression. We again got the result. So as a data scientist, what you have to do is just like I showed over here. If I go back, let's scroll up and go back to this particular point. We tried simple linear regression, got 0.67. We tried polynomial regression, got some result. Now in tomorrow's class, we are going to try other elements also to see if we can improve our model's performance. Okay, this is how data scientists work. They try multiple iteration of models, and whichever is working best in their scenario, that becomes the final model, which gets productionalized into the actual environment in the real world scenario. What we learned yesterday. So topics covered yesterday. You can also pinpoint if I miss anything which we studied yesterday, and I didn't mention it. Okay. So first of all, we understood what exactly is machine learning, right? So machine learning is nothing but making the computers learn something on a software basis. Earlier in 1980s and even earlier, uh, a machine was made specifically for one task, and it was hard programmed according to it. To make it work on certain other tasks, we have to create a completely different assembly line. Okay, that was good enough for the industrial age, but now that we were stepping into the information age, we can't do this over and over again. That's why the research scientists or statisticians found a way that if we train on a certain data using the statistical tools or the formulas, we can make a kind of a software which can easily learn and then do the designated task. You don't have to reinvent the wheel every other time. Okay, so machine learning is like we have a lot of data. Okay, and we can train, or shall I say, make the computer learn from what exactly that data is about, and then that the designated task can be done according to it. Okay, so machine learning is broadly classified into, I will say, two parts, but over here we are going to consider three, but it is mentioned as four. So machine learning is majorly divided into 3 to 4 parts. Let's talk about first, which is supervised machine learning. Okay, second is unsupervised machine learning. Uh, Third is recommendation system. Okay. Now we are going to talk about each one of them. There's one more category which we are going to talk about also. First of all, what exactly is supervised machine learning? So supervised machine learning, we throw in the data and make the computer learn just like you're teaching a kid. Okay. Suppose you're trying to teach kid mathematics. Okay. In maths, you are going to give it a formula, like maybe a equation like 2 into 3. Okay, and you already have the answer. My bad, 6. So uh, you already have the answer with you. Okay, so it's like you are giving the input feature. Okay, and you are also giving them the output. Okay, and then you're trying to make the kid understand that, okay, if you multiply certain thing, this is the output. So in short, this is a very good example of a labeled data in which you know that you are giving the input and what is the expected output from that particular data set. Okay, so that it understands the pattern, it makes certain equation in certain ways so that if in future any unseen data comes up, it can easily make a very good output from it. That is supervised machine learning for you. Okay. Now, if we come to talk about unsupervised machine learning, in this, it is given a data and we give a free hand to the computer. Try to find any category. Okay? So it is like giving a free hand to the system and say, okay, can you subdivide this data according to something you are able to find, which is very much impossible for us human to just directly look at the data. Okay. Suppose there's a census data. Okay. So census data contains lot of information. We don't know how to divide it at the first place. Okay. Let's consider this way. And the computer was able to divide the data into certain different categories. First of all, uh, babies, then we have teens, then adults, and then senior citizens. Okay, so we didn't tell it anything, but it was able to consider certain type of distinction which was very much evident by running through certain formulas. When we are going to talk about unsupervised machine learning session in future, like third or fourth session, I guess, then you're going to see how exactly this kind of thing it is able to do. Again, it's pure mathematics which is running behind. Okay. Finally, we have the recommendation systems. It is something like reward and penalty system. Okay. So it's just like teaching a kid again. Like if they do something good, the parents try to reward them. Very good, keep it up. Okay. But if a kid does something bad, then he or she is penalized. Okay. Like making them understand, okay, though, no, you should not do this. Similarly, recommendation works on the same principle. Okay. Very good example over here is going to be a gaming with bots. Okay. If you are playing very good, the bot difficulty becomes increased so that you still feel engaged with this game and you don't get bored from it. And vice versa, if you're playing very dull, the bot's difficulty level can go down so that you can again engage yourself over there. You don't get bored. Uh, Very good example these days is the autonomous cars. Autonomous cars works on this risk and reward reinforcement learning. Again, your music recommendation system again works on recommendation system over here, that if you are looking at certain type of reel for some long time, okay, there might be a very good algorithm. The system knows that, okay, you like certain type of category, let's throw in this kind of reels or whatever it is so that you stay engaged in that particular system. Okay, this is a very very small type of introduction, or shall I say definition, for these three type of machine learning algorithms. Now there is a few more, which is a blend of all the three sometimes too, which is called a semi-supervised. Okay. So semi-supervised works on the same principle, but they get blend. Okay. What you do, first of all, you start with unsupervised. Okay. Create categories, and then you go to supervised machine learning. So it's like a semi-supervised type of thing. It's a bit advanced for you to understand currently, but as of now, we are majorly focused on supervised machine learning. So let's talk about supervised machine learning again. Okay. So what is supervised machine learning? We already know about it, but what are the categories of supervised machine learning? Majorly, it depends on the question. What are you trying to predict? That's a simple question. Okay. So if your answer is, I want to predict something which is continuous in nature, maybe stock price, maybe rainfall, maybe temperature, anything, then the best scenario for you to use is regression. Okay. But if your answer is discrete, okay, a category, a true, false, binary, multi-class, okay, in that scenario, you are going to do classification. Okay. So this is what we learned so far. Yesterday, we started with our first topic, which was continuous. Okay. So continuous, we talked about like different things. First of all, we talked about if the relationship is linear. Okay. So if the relationship between the independent and the dependent feature is linear, means one increases, other increases, one decreases, other increases, something like this. Okay. If this kind of nature is there within the features, okay, so you can easily go for linear regression. Okay, can anybody tell me what is the formula through which you can easily do a simple linear regression? Let's see who can answer me this. Very good. So the school time equation is again coming to haunt you guys. Just kidding. So the simple equation is y is equal to mx plus c. If we try to put this in graph, this is how it looks like. Okay. First of all, y is equal to mx plus c again. Let's type it over here. If the line is going somewhere over here, so the distance over here is the c value. Okay. Y. What is the value of y when x is equal to 0? Is nothing but c value. That's why c is over here. And if you want, what exactly is this? This is coefficient of x. It is calculated by taking this particular area, how much slope it means how much change in x is leading to the change in y. Okay, so basic thing becomes this is your coefficient and this is your intercept. I gave you a new, or shall I say, a bit advanced type of algorithm, which is not y is equal to mx plus c. What was it? It was again y is equal to dash. What was it? Yes, very good, Rakshita. So there are different formulas, different researchers, different white papers using the same equation but different uh, symbols. Okay, so this very much introduced version is beta 0 plus beta 1 x. Uh, in future, you are going to also see this particular equation, which is called as z equals to w x plus b. Okay, so these two or these three overall are the same equation. If you see some other symbols, don't get disheartened. It's all about which researcher has put the white paper in such way. Everything talks about the same thing. We have intercept and we have, oh sorry, slope and intercept. Okay. Now, we talked about the topic which is called as simple linear regression. What exactly is simple linear regression? Can anybody tell me? Exactly same thing, right? In which we have one independent and one dependent feature. Okay. That's why this equation becomes legit. This, or even the one which is present over here. Okay. But can you guess? We didn't talk about it yesterday, but let's see who can give a wild guess. What is multi-linear regression? And what is going to be its equation? Many independent and one dependent. Very good. That's correct. Just a second, guys. Okay. So in multilinear regression, we have many independent feature, okay, but only one dependent feature again. Okay. So this is how you handle the equation. What do you think is going to be its equation if you try to compute it? Very good, Pragati. So we can give like y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 and so on and so forth. Yesterday, what we did, we created a simple linear equation. We tried to predict the TV advertisement and how much sales were happening through it. Can you tell me what were the steps we did as soon as we imported the data? The first step was import the data. Second step, let me tell you, which we obviously skipped, but I hope you are aware from your previous modules. Do EDA. Who knows what is the full form of EDA? and what are the things you can easily do in a EDA. Very good. Exploratory data analysis. Okay, if I say, okay, this is the data, do EDA for me. What is the few, shall I say, code, or what is the few steps you're going to do? Let's see. Okay, answer me this. Data wrangling. Big word. Okay. Data cleanup. Handling missing values, handling outlier standardization. What if I say this is not EDA? Feature extension, again, not a EDA. Take a guess. Take your time. This comes under a third category, which again we didn't do last time because, of course, you are coming from a certain background already. This, the topic which we call is as do feature engineering. So let's talk about feature engineering first till the time you are trying to remember about EDA. Okay. So in feature engineering, you can do the handling of missing data. You can do create new features. Okay. Like if you have date, you can easily bring out whether it's a weekday or a weekend. Okay. If you have unit price and the quantity of certain thing is purchased, you can make the total price. Uh, what else? What else? Handling outliers, very good. And standardization, normalization. Guys, interview question. If you want to write it down, wherever I say interview question, always keep it on note of it. What is the difference between standardization and normalization? Very good. Encoding. So this is nothing but a part of feature engineering. But what is a part of EDA? Very good, Shisha. So first thing is describe. What else? Shall I say head or tail? Okay. What else? Um. Okay. Min max. Very good. Is null. Shall I say info? Anything else? Okay. Shape is like coming. Shape and column names come both over here. So shape and columns are like all inclusive in info only, but it's good. Head and tail. Yes, we have already noted down. How about core? Who knows about this particular function? Very good. See, these are EDA where you're exploring the data. You're not doing anything else. You're trying to understand, or a soft understanding of the data easily, one by one. Okay, this is how the data is looking like. These are the problems. This is what it is happening over here. That's it. That's your EDA. Okay. Even over here, you can do, shall I say, lot of plots to understand your data even further. Okay. Uh, like for correlation, you can plot it in a heat map. Okay. For division of the data, you can show different graphs, bar charts, area plots, anything. The list is endless. It depends how you want to understand the data. But whenever you start handling the data, edit the data, that comes under feature engineering. Okay, so these two parts were not discussed yesterday, but this is like the second and third step. Okay, as a fourth step where you have done everything, you have understood the data, you have cleaned the data in certain ways. Okay, so guys, again, do always remember what is the difference between this. Okay, take it as a homework. And if you're still facing trouble, we can definitely take it up in the next class. So what is the next step, guys? Your data is clear. So the quality data is ready now. What is the first step in your simple linear regression? Very good. So the first step is to split the data into independent and dependent features. Okay. Created X and Y. That's the first step. What is the next step after this? Very good. So independent dependent is simple. You can use different techniques. You can use iLock. You can use drop. You can even use array components. It depends. Nothing is like fixed. You can explore anything. Splitting the data into split the data into train and test. This is the next step. For this, you use the function which is called as train test split. So guys, over here, there are two components which are very important. Can anybody tell me first of all, what is the purpose of test underscore size? What does it do? And the value are always between 0 and 1. Okay. Yeah, 0 and 1. So what exactly does it? Set the size of data in training. Good. No, in test. Okay, so test size is equal to 0.3, means 30% of data is going to be hold for the testing phase. Remaining 70% is going to go for the training phase. Now, again, very good question. What is random state? And if yours and mine numbers are same, suppose I say 77. So what is going to happen? So random state is nothing but we are trying to split in the same fashion so that the result are very much similar to each other. We are reproducing the same result in different systems. Okay. Reproducing of results becomes a very important task. That's why random state becomes a very important thing. Okay. So, okay, my data is split into train and test. My data is now ready. What is the next step for me to do? Calling the function, shall I say algorithm? Okay. If we are doing linear regression, we are going to call linear regression, prepare a variable, and we are going to set for linear regression. Okay. And what I will do, var dot fit. I am going to give X train and Y train. Okay. When I have to predict, I have to do var dot predict. Now, guys, can anybody tell me if I want to create Y train pred, what should I put in over here inside the y dot var dot predict? Very good, Pragati. X train is going to go. If I want Y test predict, what is going to go inside? Of course, it's going to be X test. Now, you can ask me, sir, why are we making this Y train pred at the first place? Now the question becomes, now this topic might be covered in future classes. Let me see which class are we going to talk about this topic. If it's too far, I'm not going to touch it right now. Um, it's not even present. Okay, so fine. So what we're going to do is, first of all, what we did yesterday, let's try to recall that first. We created this thing, okay? And then we saw the performance metrics. What are the performance metrics that we discussed yesterday? Let's see who can answer this. Very good. We talked about outscale. We talked about MSE, talked about MAE, and RMSE. Okay, what is the range of R square and what exactly that range tells us? 0 to 1. And what is the number? Like if I get 0.8, what does this number mean? Very good. So if number is closer to 1, my model is good. If the number is closer to 0, my model is bad. Okay. Uh, MSE, MAE, RMSC talks about the error. Okay. Error is nothing but what is the difference between the Y and Y pred. Okay. Now, how exactly you treat this thing? If you create absolute, becomes mean absolute error. If you do it square, it becomes mean square error. If you take a square root, it becomes RMSE. All of them plays a very important role. It's recommended to always show all these four metrics for better understanding. Now, I gave you homework that compare the R square value for both the Y train pred and the Y test pred. Now, I'm going to take a scenario. I'm not going to reproduce this thing. Okay. Suppose the Y train pred the R square value comes out to be 0.92 and Y test spread the R square value comes out to be 0.62. Think about it. What exactly happening? Model didn't work as expected on test data. Model fits well on train, then test. Okay, good. The term which I'm looking for or which I want to show you, this kind of scenario is called as overfitting. When your model fitted with the training data so much that it performed very good, but it didn't understood the theme behind of it. Similarly, like if you're a school student, okay, in mathematics, there are certain questions at the back side of the lesson. Okay, you only read those questions and the class test came with only the questions which are present in the back side of the notebook. Okay, you performed very good. In the class test you got 90% marks. But in the final exam, the questions were little bit twisted. The theme behind of it was same, but you performed very bad. That means you were not able to understand the actual theme, rather you just learn whatever was there in the book. This becomes a classic case of overfitting. Okay, let's take one more scenario in which your Y train pred R square value is 0.62, Y test pred the R square value is 0.56. Let's see who can answer me. What kind of scenario is it going to be? Correct, Kavya. So it is going to be exactly opposite of what was there in the above scenario. This is a classic example of underfitting. That the model was not even able to understand any logic from the training part, yet let alone that it was going to give any good performance in the test part. Okay. So, and overfitting and underfitting are the common scenarios which a data scientist come across on a day-to-day basis. There are a lot of things which can be done about these kind of things. Okay, I believe it becomes a bit out of syllabus for you guys. So, note this thing down. Okay, and do your small research. If you have any questions, we are going to take that up in the next class. Okay, so as of now. This is what we completed, but there is one more topic which we tried or like put our hands on, which was called as polynomial regression. So guys, in last or the yesterday's class, we saw that uh, when we were looking at the data, our data was looking something like this. Okay. And the first thing we did was, okay, guys, I am able to see that when y is increasing, x is also increasing. And we can see there is an upward trend which is forming. Okay. So what I did as a very basic person, I went ahead, formed the linear regression equation. With the linear regression, what happened? It created this kind of equation. Okay. Over here, the scenario was that, oh my God, it is working very good in this particular section, right? But at some point, this part created a problem. That's why our R square value was not that good. Okay. We see that this is not a linear, uh, shall I say, relationship. It is a polynomial type of relationship. It's, or shall I say, polynomial can also be known as the term which is called as non-linear relationship. Okay. So in the non-linear relationship, what we can do, we can use polynomial regression. We know that x square, x cube, x to the power 4, so on and so forth, are going to make sharper and sharper curves. Okay. Uh, Now the good question is, what kind of power shall we use? We are going to talk about that topic in some other time, maybe in few hours. Okay. But what happens if I do a non-linear relationship type of algorithm? It's very easy. We call the polynomial regression. Let me see, what was the function? Can anybody recall me? What was the name of function? Let me just quickly crawl up from yesterday class. Okay, yeah. So it was polynomial features. Polynomial features. P and F are capital. And over here, what we did, there is a degree which we have to assign. Now, there was a good question from yesterday. How do I know to use which degree at what time? There is a certain type of searching technique in which it is going to be optimized in such way, but we are going to talk about it in some time. This helps in creating a non-linear type of equation for us. Okay. And this helps us giving a better result. Okay. And that's it. This is what we learned yesterday. So can anybody tell me, if I am giving degree of 4, what kind of equation will it try to fit? If I say degree of 4, what is going to the output? Any guesses? So yes, good Pragati. The answer is going to be x to the power 4 m1 plus m2 x to the power 3 plus m3 x to the power 2 plus m4 x to the power 1 or x plus the c. This is where it is going to try and give us the answer. Now guys, I have created an equation, okay, and I try to find the coefficient of it, and my model name is var. Okay, how will I find coefficient from the feature or from this particular model? There is a formula which we tried yesterday. Dot coef underscore. Similarly, if I want to find the intercept, okay, so var dot intercept underscore. This is going to give us whatever coefficients are there, or the slope variables. It is going to give the value for them. Over here, it is going to give you value of the intercept. So let's start with the model performance which we saw from yesterday. So yesterday we tried linear regression, we tried polynomial regression. Linear regression, the R square value was somewhere around 0.67. Polynomial was even like performed worse, should I say 0.65. Now, what else can we do? There's one more technique which is like universal for whatever type of algorithm you are using, whether it's classification, regression, any. Okay. That topic or that particular algorithm, whatever you want to call it, is called as cross validation. So cross validation, what it doesn't do anything apart from what it is already doing, but it does that particular thing in a certain way that the model becomes much more better comparatively. Okay. So what if I had 100 rows Okay. And guys, if my test size equals to 0.25, what do you think is the division of x train and x test? How many rows are going to go in x train and x test? Tell me. That is correct. So 25 rows are going to be hold down for the test part. Rest 75 will be used for the training part. Now, the research data scientists or research statisticians, what they came up with, what about if we do training in a different fashion? Uh, what I will do is 50, 60, 75. Okay. So I will try to divide this into five parts, five equal parts. What will be the five parts? 15, 15, 15, 15, and 15. Okay. Now, in my training part only, what I'll do, I'll try to pick the first four blocks, okay, train on it and test my result on the last block. Okay. Then I'm going to repeat the process this time. Instead of taking the 1, 2, 3, 4, I'm going to take 2, 3, 4, 5, going to do the same thing. Other time, I'm going to pick 1, 2, 4, 5, and going to test my results on the third one. This thing is done for 5 times where the data is again trained the same number of rows. Like all 75 rows are going to be used for the training part. The only thing is the tuning, the way we are finding the coefficient and intercept is going to be much more sound, in which the training was done on all the 75 rows and the testing was also done on all the 75 rows. Okay. Uh, we don't call it testing. There is a new term which we call as, which is called as validation. Okay. So this is where you use cross validation. So it's not only five thing like I'm dividing into five. There's a term which is called as k, and you can give it any number. That is how many amount of block it is going to create. Universally accepted is 5. Okay, you always keep 5. You can try 10, 20, whatever you want. Okay, but the thing is, it becomes the more you are making the blocks, the more computation and little bit slow the algorithm is going to be. So k equals to 5 means it is going to create 5 blocks. Okay, and in 5 it is going to first use the first 4 and then test itself on fifth, and going to learn from the mistakes from over here. Then it is going to go for next 4, and it is going to then test itself on the next part. This fashion is done for all the times, means that data is going to be trained, so the model is going to be trained on all the 5 blocks, means all the 75 rows, and it is also going to be validated on the all 75 rows. This way the researchers were able to find that our model performed significantly better. Okay. Sure, Akshata, let me try to find if I have anything pictorial about it. Let me just quickly get some good image. Circulation. Okay, I got a very good image. Just a second, sharing it with you guys. And there you go. So according to this particular image, this was the complete training data. The whole data was the training data. Okay. So instead of just training the simply way, like completely training on one part, it is going to try to take out a certain block, train it on that particular thing, then it is going to test itself over here. Similarly, it is going to train on this particular block and this particular block, going to test itself over here. Similarly, over here, and this process is repeated for k times. Okay, in which all the parts were used for the testing and all the parts were used for the training. Same thing. It is again doing the same thing only, right? So this is what a cross validation is like. Now, cross validation is of two types, majorly two types. There is one more, but it is like having so much overhead that it is not really recommended in the real world. So one is called as k-fold, which what I have like explained you over here. This is called as k-fold. Second is called as stratified k-fold. So what happens? Suppose if we talk about a classification problem, okay, and we have a data set of 100 students in which there's a label called pass or fail, okay, and the division is like 80 people pass and 20 people fail, okay. Now, how do I create equally divided scenarios in which we get 10 samples each, okay, but in this the division is same 80-20, so 8 and 2, 8 and 2, 8 and 2 means it is having equal part of division of zeros and ones, okay, pass and fail. That is handled by the algorithm which is called a stratified k-fold. It keeps in mind that, okay, whatever the labels are, okay, I will give exact same division between the different folds. That is the only difference between k-fold and stratified k-fold, okay. uh, I should have like bookish language as well for this thing. Let me try to find that and paste it over here, okay, just a second. So far, if you have any questions, do let me know. Okay. Oh yeah, this is over here. Just a second. Just a second. I'm trying to take a snapshot over here. Okay, that's the one. So this is the bookish language of what exactly is the difference between k-fold and stratified k-fold. Okay. So I hope it is visible to you guys. Okay, let's do this. Open up the chat window. Okay. All right. So let's try to understand by zooming in first. Okay. So cross-validation is a machine learning technique that evaluates a model performance on unseen data by dividing a data into multiple folds. Okay. In each iteration, one fold is used for validation and the remaining is used for the training of the data. This process is repeated such that each fold serves as a validation at least once. Okay. So there are two different ways, which is k-fold cross-validation, which we have already talked about. In stratified, similar to k-fold, but ensures that each fold has similar portion of different classes. Okay. Just like I told you over here, let me zoom out. If the overall training set had 80 pass and 20 fail, it is going to divide folds in such a way that 80-20% ratio is going to be in the each fold. That is balancing out all the folds. Okay. So this is a theoretical part. Now in the theory, is there any questions? Do let me know. Need few more confirmations, guys. Kitagni, Mona Lisa, Pankaj, Pavitra, Pragati. How's it going for you? Any questions? Uh, so Shisha, we are going to take now the example is going to be in practical scenario. Okay. So that is going to clear it out perfectly. As of now, the theory part should be clear. Okay. So yeah, again, if you want to understand stratified, so let's go back to this particular example. We had a training data. Okay. And it contained 100 rows. In 100 rows, the dependent feature was pass and fail. Okay. In that also 80% was the passing people data, 20% was the failing people data. Okay. If I want to create a stratified k fold, it is going to divide this into, suppose that k equals to 10. So it is going to create those 10 samples such way that 80-20% ratio is going to stay same. Okay. So that means 10 rows are going to be there. Okay. Since I'm making 10, so 100 divided by 10 is nothing but 10. And over here 80-20% ratio is there, so this is going to be your complete rows. This is like 100%, and 80-20 is going to stay over there. So stratified is generally used in classification problems. It is something of future, but regression also we are trying to use in a different fashion. Okay, I hope it became clear now. Okay, so I will now encourage everybody to open up their Jupyter session, and I hope you were able to download the study material, because we are going to now import the data which is called as housing.xlsx. Please go to that particular folder in the dataset. In session 3, you're going to find housing.slxx. Okay, we're going to import that thing. So as of now, I'm going to do import pandas as PD, uh, import matplotlib dot pyplot as plt. What I'll do, not to give you the whole copy thing, like you're noting it down. In chat window, I have like completely given everything. Okay, so we are going to not use leave one out because it's never used. It is only used when the data is very small. Okay, leave one out is a type of k-fold technique in which the data is trained on every single row, and every single other 99% of the data is being tested on. So it's only used when your data set is very, very small. The good thing is I can easily give you uh, the comparison between all these things. Okay, so let me just paste it over here, expand it. Okay, let me take it down. So leave one out is something very different. It is only training on one sample at a time. So it is has very niche use case, but when you have very small data set, then this kind of thing can be done. But if you have like data set with millions of rows, okay, then this becomes very bad approach. So I hope you were able to import this thing. Let's run this code. Okay. The first thing I want to do is import the housing data set. Let's see where exactly the housing data set is for me. Housing.csv. Let's see. I think it should be housing.csv. Housing with ocean.csv. Yeah. So we are going to call this one as housing data. dd.read underscore csv. Housing.csv. And let's look at this particular data set. Okay. Take good 1 minute, look at the data set and tell me. Yeah. Look at the data set. Tell me what can be the independent features and what can be the dependent feature. Okay. Yeah, please take your time. Pragati, that is correct. Price if we want to predict the dependent feature. Very good, Preeti. So what we'll do is that why not try something new? Uh, First of all, we can do EDA. So in EDA, I'm going to use housing data dot head is already there. So that going to come over here. So first of all, let's go for info. We can see that there are 9 columns, and majority, or shall I say all of them, are integers or float. Okay, so numerical columns. We don't have to do much about it. We can do housing data dot describe. Can you share the CSV file here? Of course I can. There you go. So after describe, we can also look at things like info. Okay, info is done. How about if I want to see nulls? How do I see missing values? Can anybody tell me the code? Is null. There is a small thing which should also be there, which is called as sum. Okay. Once you do this, you're going to see that the total bedrooms has certain problem. 207 rows are missing values. We have 20,000 rows, which is very good proportion. So we can easily impute the missing values over here, right? Uh, let's see. How about we have so much rows? Let's drop the missing features, missing values. Okay, we can. It's less than 1%, around 1%. Okay, so what we can do is housing data dot drop any. Okay, I'm going to do this and overwrite this thing. Okay, once this is done, I can rerun this particular code. I'm just going to copy it. Dot drop any, and you can see that we don't have any missing values anymore. So we were able to do EDA as well as small feature engineering by handling the missing values. The main part is done. What do you think is the next part, guys? So let's recall over here. These three steps are done. What is going to the next step? Correct. We are going to split the data into training and the independent dependent features. So uh, first of all, x equals to housing underscore data dot drop. I'm just dropping one column, which was the what was the name? Median house value. Okay, median house value. X is equals to one. One means column. We are removing the column. Similarly, I'm just going to copy it, paste it over here. Instead of drop, what I'm going to do is keeping this, just removing this and doing it small capital Y. Once this is done, what I can do is the fourth step. What is the fourth step, guys? Fifth step. So, sorry. That is to split the data into training and test set. For that, I hope I have imported the train test split over here. Yes, I do have it. So all I need to do is call up this function. So for the people who are struggling to keep up with the pace, let me just come as a relief for you. There you go. Copy and paste it for yourself. Okay. Now, what do you think this particular notion is telling us, this particular parameter? That is correct. So what I'll do, I'm just going to run this and my data is completely ready. What do you think is the next step for me? Correct. So let's see. This is a linear regression. I will call it as model one. Linear regression. What I'm going to do is model one dot fit. And over here, can you please explain what is a data leakage? Too early, Srisha. Okay. We are going to talk more about it in the future classes. Bit too early to talk about it. Okay. So model one dot fit, we are going to do the X train and the Y train. Okay. Once this is done, the model is prepared for us. Okay. Now try to do it also. Okay. shall we move forward, guys? We were able to fit the model. Let's try to do two things. Okay. Why test? Just curious, is there a specific reason for using uppercase here? No, there's no specific reason. It's like the universally accepted thing. You can do anything. Okay. It's just that random state 42 is very much universally accepted. Like people just do it, you know. So no hard and fast rule. So guys, I want to create y test spread. What should be over here? That is correct, Rakshita. It is going to train. Okay, that is why it is called as fit. It is going to train on that particular data set. So guys, tell me, what should be the y test spread? How will I calculate it? Okay, I can use xtest, but what is going to be my code? Very good. So I'm going to do model one dot predict x test. Okay. Once this is done, I have the x test spread. Now what I can do is I can find all the metrics. Okay, let's see where exactly did we do that. Let me go over here, copy it, come back down over here, paste it. So first for mean square error, y test, y test red. Okay, same thing I'm going to copy for everything. Copy. So what I'll do, I'll just going to print it. Don't worry about copying. I will just copy paste it in the chat window. Okay, there you go. So let's see. Uh, so the mean square error is coming very big. Oh my god, very big number. Mean absolute error is coming very big. Okay. The R square value is coming 6.4 or 6.5. Not that good in the test side. How about training? Let's see how exactly the model is performing. Okay. So over here, I'm going to do again train. Let's see if it's overfitting, underfitting, what else? Okay. So is it of test, train, again, you don't need to copy it. There you go. So take 1 minute and see how exactly the model is performing. And what are your thoughts about it? Almost same, almost same. Which is a good and a bad thing at the same time, because same means very good, that okay, that the model was able to understand the uh, shall I say the reasoning behind all the features, but bad because it is very low. If it was like 7575 or 8585, amazing, our model would have done a very amazing job. But over here I can see that it's very low. Okay, so model is fitting the data, but model is not able to give very good results. Okay, so what I can do is, we are now going to do the k-fold analysis. For this, I'm going to copy it, paste it over here. Not going to make you understand what exactly is happening, but you have to tell me what is written in this code. Okay, tell me what exactly is happening over here. Very good. Rakshita, just like I told you that for the model to be good, the R square value should be very closer to 1. The MAE, RMSC, whatever it is, should be a very small number. Okay. This should be very small number. Lesser, closer to 0 is very good. This one, closer to 1 should be very good. Very good. Good, Shisha. So now I'm going to create a model 2 and it is going to be with k-fold. Okay. Now we are going to hit enter and let's see how to use it. Again, not going to explain you this particular line of code which I just pasted. You have to tell me what exactly is happening over here. Uh, just ignore this part. I'm going to tell you why. For now, just look at what exactly is happening over here. That should be model 2. Okay. So update it. Let me try if I can update it. Edit. It should be model 2 because we are using it as model 2. Since this is the model 2, this is the model 2. Okay. Any questions, guys? Are you able to understand what exactly is happening over here? Exactly. So we are calling the model 2. We are giving it X train and Y train. We are giving KF, which is nothing but the cross validation, in which we are saying that do 10 splits. Random state is given same so that your split and my split are exactly same. Number of jobs -1 means if your system has GPU, so it can use that GPU. But if you don't have GPU, so it's just going to ignore it. Okay. Negative mean absolute error means we know that MAE, MSC, RMSC are good when they're closer to 0. So negative means if anything is closer to 0, that is going to be the best thing. That's why it is given as negative. Okay. That is the only reason. Negative mean absolute error means try to find a certain model coefficient so that mean absolute error is as low as possible. That's why negative mean absolute error. So guys, let's try to run it. It is going to take some time because it is going to go give 10 different rows. Oh, it ran for me. Perfect. So k-fold score. Let's see what exactly am I getting. So I'm going to go for from statistics, import mean. Means we are going to do average. np.mean, np.absolute, and we are going to call k-folds. Okay. If you hit enter, uh, so you will see mean absolute error came as 0.559, which we can see that it's hardly any different from 0.5, oh sorry, 5070, 5095. So again, this approach also failed. Okay. So we have tried 3 approaches so far. Okay. 2 in the previous section in which we did linear regression and non-linear regression, which was polynomial regression. Okay. Over here, we also implemented k-fold technique. All right. Now there's one more technique which we are going to use, which is very, shall I say, very famous type of approach. But so far, just let me know if you have any questions. Okay. Oh, I think I was talking on mute. Okay. Let's try one more approach. model2 dot fit. I think the fit should work. Let me see. We're going to give x train and y train. Okay. We are going to do the same thing over here, predict. Then we are going to do copy and paste. Instead of this, we are going to just do this over here. And let's see. 6 4, hardly any difference. 6 4 5 5 1 3 6 4 5 1. Yeah, not much of difference. Okay, so there's one more technique which we are going to talk about. But before that, I want to just make sure that you are able to understand how exactly to use cross validation. What exactly is happening in cross validation? The question can be, why are we using negative mean square error? Okay, if you are not able to answer it, just let me know. I can reiterate. Else we can move forward. Or even better, we can go for a break so that you can just freshen it up so that we can start a topic after the break. Okay, which we have already discussed. And second is what we are going to discuss now. So suppose uh, there is one data set, or you are a data scientist who is going to predict a salary of a person based on the years of experience of that particular person. Okay, now the thing is, years of experience being the only feature makes it a simple linear regression problem. But what if we have many features along with it? Okay, suppose the relevant years of experience. Okay, graduation year, um, highest degree, maybe something like this. Okay, so there is one situation in which when these two are used, the R square value was coming out to be 0.65. Okay, so research data scientists started giving it more features which were really good, like uh, relevant years of experience, graduation year, um, whatever it is. Okay, so multiple features were given. The R square value tend to increase. Okay, maybe after adding all these, it reached 0.7. But then what they did, they tried to add stupid type of columns like middle name. Okay, maybe marital status, anything. I'm just giving very unreasonable column name, dog name, whatever it is. Okay, so they also see even after adding the irrelevant features, the R square value was still increasing. Okay, weird enough, it reached 0.74 or something. Okay, then they thought that what exactly is happening? Even if we are adding the garbage data, the R square value was getting increased. That means if I add thousands of features, R square value is going to be closer to 1. Okay. So they thought that, okay, maybe R square is not really a very good, shall I say, calculation for the model performance. So there's a topic which is called as adjusted R square. Okay. So adjusted R square. Adjusted R square main function is to penalize uh, the number of columns. Okay, so the R square, the simple R square, we know only depends on one thing or two things to be specific: actual y and the y pred. But the adjusted R square also started considering the number of rows and the number of columns. Okay, so what exactly happens over here, that the adjusted R square performance decreases as you increase the number of columns. Okay, this helped them to mitigate the issue which was coming over here. Okay, now the formula for adjusted R square looks something like this. Just a second. So let me just take a snapshot. Okay, adjusted R square looks something like this. So you will see it uses the R square, but it again uses two things: total number of rows and total number of columns. Okay, and it is in the denominator side. Okay, so as soon as you increase the number of columns, the performance is going to dip. Okay. So the shortcomings of R square were handled by adjusted R square. Perfect. But the thing is, there is one more technique which could have been used so that the number of columns uh, being used too much can be adjusted. Okay. And this particular technique is very famously known as regularization. Okay. So regularization is broadly classified into. So first of all, can Priti or anybody tell me what was the problem with the normal R square formula? Who can tell me what was the shortcoming of the normal R square formula? Yes, if you increase the data. So I will just not say increase the columns, but let's say the increasing of data was directly increasing the R square value, which in totality is incorrect. Okay. You can add garbage data and it is still going to show that the R square value is increasing. Okay. So to mitigate this, adjusted R square formula was introduced and it looked something like this. Okay. It used to penalize wherever you try to increase the data. Okay. So irrelevancy or anything, it is going to penalize it. That's why R square formula was disregarded and adjusted R square formula was started to get much more visibility. Okay. But that's not the only way through which you are penalizing your columns. Okay. The new type of, or shall I say the most famous type of penalization of columns. So I'll just say uh, penalization of columns. Okay. Can be done through the term which is called as regularization. Regularization is of two types. L1, which is also called as lasso regularization, and the other one is called as L2, which is called as ridge regularization. So if I just go back to the model which we created firsthand, let's just go back over there. And this was the model one which we created, right? If I want to see what all coefficients and intercept value which was created over here, all I need to do is model one dot coef. Okay. If I do this, this is the coefficients of each columns which came up. Similarly, model one dot intercept. Intercept. Okay. So this is how the whole equation look like. Okay. Any questions in understanding this particular part, guys? Let me just take this snapshot and take it to the blackboard over here. Paste it over here. Okay. So any questions to understand what is coef, what is intercept? Shall I take silence as no questions? So the idea is over here, each column, like column one is given this particular M value, column two is given this, column three is given this, 4, 5, 6, 7, 8. Okay. And then this is the nothing but C, or you can also call it as beta 0. Okay. So these are all the values which were given over here. Okay. Now, what if instead of only 8 columns, there were 80 columns? Each one of them had certain value. Okay. As big as 200 or as small as 0.001 of x to the power 3, suppose. This is not 3, x3. This is maybe x5, something like this. Can anybody tell me the difference between this value of coefficient and this value of coefficient? This is the value of coefficient for a certain column named x5. This is the value of coefficient for certain column which is called as x3. What exactly is it trying to show over here or tell us over here? Very good. Slope. So any uh, shall I say value of y, shall I or shall I say any value of x, y will move 200 points. Okay, means if y was equals to x, if x becomes 1, y becomes 1, but y equals to 200 of x, 200 of x, that means if x is 1, y is 200, right? This is the amount of slope value which increases or decreases. Okay, so this means that small change in x is making a very big change in the y value. That means this particular x5 column is very much important. Slight changes in that x5 column makes a significant change in y column. But on the other side, this is the one, x equals to 0.01 of x. Okay, so small change in x like 1 is hardly going to give very diminishing return to y. Means a small change in x is giving very small change in y, hardly any difference. Okay, so can we is it safe to say that this particular column x3 is not as important as this particular column which is x5? Do you agree on this point? Take your time, think about what exactly I asked. Let me try to rephrase it. Okay, there is an equation. Let's take a multilinear equation. Y equals to 200 of x1 plus 0.01 of x2 plus, let's say, 3. Okay, over here instead of x5 and x3 I gave these two. Okay, now we know small change in x1 is going to give us significant change in y. Small change in x2 is hardly going to give any changes to us. So is it safe to say that x1 is more important as compared to this? This is less important. Tell me. Yes or no? Higher the value of coefficient of certain column means higher the importance of that particular column. This is what you should know. Okay. So if you were not able to understand, take it as a note. Higher the coefficient value of a certain column, higher is its importance in predicting power of the model. Is it understood, guys? So Shishas is saying if the value of x1 is somewhere around 2, maybe 3, maybe 5, but the value of x2 is around 2000 or 5000. Who can tell me which column becomes much more important? Very good, x2. Getting very slow replies. This might lead us to be very slow in the approach. I might have to rush it then, guys. Okay, so I will sincerely request for you to help me on this one. So guys, over here also you will see, just look at these numbers. What do you think is the most important number according to you over here? This is x 10 to the raised to the power 3, this is 10 to the raised to the power 4, this is 10 raised to the power 1, and this is a negative, and this is very small value. So if you look closely, column 8 has the highest value over here, followed by column 7. Okay, I feel column 7, no, then column 3. Okay, in such a way that if you try to put it in a descending order, then in importance factor, column 8 becomes very high, then column 3, maybe then column 7, no, then column 5, and then we have column 7, so on and so forth. So e raised to the power e plus 4 is nothing but 10 raised to the power 4. Okay, 8, 3, 5, and 7. Very good, Shisha. So guys, this is the way if we have a problem like something which is having overfitting issue. What is the overfitting issue? Can anybody tell me again? What is overfitting issue? The Y train spread is giving very good results, but it is failing in Y test spread. Okay. What happens if my data looks something like this? Okay. This is my data, and it makes a very close type of regression line in the training set. But my test data looks something very different. It looks something like this. The same line is then copied and pasted over here, and it fails. Okay, so this is nothing but test. So in this kind of scenario, what happened? It trained very closely to the training data. So this is called as trained very closely with training data. This way, what happened? That the coefficient values of a lot of features were included. The regularization L1 and L2 helps us mitigating the issue of overfitting. Okay, so over here I can say that regularization helps mitigating issue of overfitting and just a second guys. Issue of too many columns. How? Let's talk about it. So what happens? The L1 regularization, which is lassos, nothing but lassos regression, it pushes out columns which have very low coefficient values. Okay, so suppose again taking this in consideration, this particular one, let me just copy it. Let me just take it over here. Y is equal to 200 of x1 plus 0.01 of x2 plus 3. It is going to push this one out. Okay, and the new equation is going to be like y is equal to 200 of x plus 3. Okay, this way the less important feature was pushed out. Okay, this way the issue of uh, too many unwanted, shall I say, less important columns can be removed. Okay, so this issue can easily be handled by L1 regularization. Let's talk about L2 regularization. L2, on the other hand, what it does, that it tried to, it is also called as ridge regularization. Okay, this particular type of regularization helps in mitigating the overfitting issue. Overfitting issue. What exactly does? Let's talk about it. How? Suppose my equation is y equals to 200 of x1 plus 50 of x2 plus 5 of x3 plus 4. after the L2 regularization, we are going to talk about it. Don't worry. Uh, how after L2 regularization, this becomes y equals to maybe like 100 of x1 plus 25 of x2 plus 2.5 of x3 plus 4. Okay. Over here, you will see that the values are decreased. Okay. This way, the overfitting problem gets mitigated. Now you ask how exactly does it do? There is one formula which we can easily look at. Let me just try to take a snapshot. It's a very big formula, so you don't need to get overwhelmed, but it's just a mathematics that we can definitely talk about. Okay, first of all, from yesterday class, how many of you remember this particular formula, RSS, which was nothing but this is our single row value or actual value, and this is nothing but your predicted value, right? So this is what we used in the R square calculation. R square was nothing but RSS upon TSS. Okay. So total sum of square and residual sum of square. Residual is nothing but residual, and residual is also termed as error. So over here, what we are doing, actual value minus predicted value whole square. And this is nothing but your mean square error. Remember? So what exactly happens in this particular formula? It adds a certain scenario. So let's try to create this thing. Over here, what is yi predicted? It's nothing but your beta 0 plus beta 1 x. Okay. If it is a simple linear equation. Okay. So if I put this value over here, it is going to look something like this. RSS equals to summation of yi minus beta 0 plus beta 1 x whole square. This is the value. Square is going to be outside. Okay. Now over here, there is one element which gets added, which is called as, I should change the color, alpha summation of beta. Okay. This is your regularization parameter. Okay. And this helps us how much penalty do you want to give. Higher the value of alpha, much more pushing out of columns is going to be. Lower the value of alpha, lesser pushing out of the column is going to be. Okay. So this is your regularization parameter. Okay. What I can do is I can take a snapshot for your reference over here. Let me just take it, paste it over here. Okay. So this is the formula which we created, yi, and this is a nothing but y hat. Okay. This particular thing is the regularization parameter, where alpha is the same coefficient as least square error, and alpha is equal to infinity means if you keep alpha is equal to 0, okay, this whole value becomes 0. It works exactly like RSS. But if you keep it as infinity, all the coefficients are going to be penalized and it is going to become 0. Okay. You don't really have to learn the formulas. The only thing is you should know what exactly is happening. The standard formula used to be this, but due to overfitting issue, they added this particular formula which handles how much penalty do you want to give to certain type of feature so that overfitting issue and unwanted columns can be mitigated. Any questions so far? Just let me know. So if there are no questions, I am going to now move to the practical side of this particular problem. Okay, we are going to talk about how exactly we can move forward over here. Okay, for this, I am going to import a new data which is called as hitters.csv. I'm also going to upload it over here so that you can directly use it. Okay. So what we can do over here, guys, we can just call this particular data, which is pd.read_csv, and let's copy the data. And once it's imported, do let me know if you are good to go ahead. Is anybody practicing right now, or shall I just show it over here and you just want to look at it? Thank you, Shasha. Who else? Okay, so what we'll do, guys, I will drop in the first code. You can see here, this is a kind of a cricket type of data set. It has a lot of columns over here. First of all, see df.info. Let's see how many columns are exactly over here. You can see there are 20 columns which are present. Okay, and not every column is going to be very much important, right? So first of all, we can easily navigate out this particular name column. So I have just pasted that code on the chat window. You can also paste it over here, and the uh, particular column has been removed. Okay, once this is done, let's see over here. You can see the dependent feature is going to be salary. Okay, so to keep it very simple, this particular data set, the all the important columns, we have to like justify what exactly is the salary of that particular batsman. Okay, so what I'm going to do is, first of all, use this code. I'm going to paste it over here in the chat window, and let's see who can answer with this. What exactly is happening over here? Take 5 minutes. Let me know. That is correct. We are doing the dummy encoding. Okay, so it's not label encoding, it's one hot encoding. Okay, so there are three columns: league, division, and I think which one was it? New league. Okay, so these are nothing but a kind of a categorical features. What we did an one hot encoding over here. Okay, so let me just go back over here, and once that one hot encoding is done, I can just run this and paste the next code. Okay, so this particular code, what it does, first of all, it creates dummies for this thing, and then those dummies are embedded over to the training data set. Let's see, X numerical. Did I miss a certain code? Yes, I did. Before this, you have to type in this particular code. Okay, let me just paste it on the chat window. Also, tell me what exactly is happening over here. First one was nothing but the one hot encoding. What exactly is this particular code is doing? Let's see who can answer me this. So what exactly is happening over here? First of all, I created dummy features. I created X and Y. I dropped those features which I don't require. First of all, salary because it is my dependent feature. Second, these three because I have created the dummy features. And those dummy features are then appended over here. So you will see league N, division W, league W. So all those things are now created over here. Okay. Guys, interview question. In one hot encoding, let's see. I didn't. One more question. In one hot encoding, I think I should write the whole one hot encoding. Why do we, shall I say, keep n minus one categories? Can anybody answer me? If one is true, then other is false for same category. That is true. That's why n minus one is always present. Okay. So similarly, over here, league yn and win or lose and yn. So that's why they are only keeping one because there might be only two categories. So very important interview question. People get confused. That's why you should know exactly what is being done. So now that we have all the features, we have created X and Y, everything is prepared. So why not uh, now split the data into training and test part. Okay, I'll just copy and paste it over here. Copy and paste it over here as well. Okay. Now, what will the last part over here? Model, let me call it as header equals to linear regression. And I'm going to fit the data. Copy it, paste it over here. Now, model dot fit. Value error. What exactly happened? Y contains NaN. Okay. I think they should have, let's see, we should drop NaN. Let me see if we didn't drop them. No problem. Let's go back over here and see how many nulls are there. Okay. Df dot is null dot sum 59. Okay. So what I'll do, I'll drop na. Df equals to df dot drop na. Okay. I'll do this. I'll rerun this thing, rerun this thing, and it should work. Okay. So Y-train was having a problem because there were nulls, and that's why feature engineering is a very important part. I just ignored that step and came over here. That's why it gave me error. So what I did, I'll just go back above. First of all, I found the is null and then I drop NA. So 59 rows were removed. Okay. So the thing is, why have I removed from the dependent feature? Because it's not a correct way of imputing the dependent feature. Okay. You don't want to impute it. So it's very safe that you can just remove those rows. Okay. Once this is done, what I'll do is same thing. Let me just copy it from over here. Copy, paste it over here. And instead of this model header, this, okay, this again, and boom, 0.41, very bad. It is performing very bad. Okay, so I'm going to white spread, model.fit. Let me just remove it first. Run it over here. Yeah, 0.41. So this is test. Let's see training. part, how exactly the training section performed. Right, we just try to copy it. Where exactly is train? Right, here it is. Train pad, copy, paste. Okay, look at it, guys. Tell me, what are your findings over here? How did the model perform? Underfit, okay. Mean absolute is slightly better. 216 and 213. Okay. Let's do one thing, guys. We should include this particular step after creating X train and Y train. Why not standardize it? Okay. So before this, when we split the data into training and test set, let's try to do this. Now, scalar, transform, transform. Can anybody tell me these two steps can be merged or not? Fit and transform. If you have like learned about standardization, fit and transform can work together, but transform can be done independently. But over here, this is, step is done in two steps. It's all too completely fine. So if I do this, standard scaling, okay, and rerun the model, let's see how's the performance now. Again, not much of difference came out because X train, X test, not much difference. So we still have 4.1 and still have 5.7. Now, what I can do is, let's see the coefficient values of each one of them. Dot OF. Let's see. What exactly can you see? Which column does has the maximum value and which has the least value? Take your time over here. Correct. So we can see there is a column which has 602 value as a coefficient, means that column might be very important. Followed by, we can also see 238, which can be the second most important column. No, third most, because 379 is also there. So there are a lot of columns which has very small values and a lot of columns which have very big uh, values. First of all, let's create a lassos model. So can anybody tell me the L1 model, is it going to remove the features or is it going to bring the values down? What was the difference? Let's go back over here. So over here, L2, it diminishes, like it decreases the value, and L1, it removes the value completely. Okay. So let's go back over here and create our first model. So this is going to be lasso regression or regularization. You can call it as anything, lasso model. For this, I'm going to copy it, paste it over here, and run it over here. But before that, let's see who can tell me what exactly is happening over here. First of all, look at this alpha value. Just like I told you over here, alpha over here value is the amount of penalization which you want to keep. If it is closer to zero, it is going to be as okay as normal thing. But if it becomes closer to infinity, it is going to be very harsh on penalizing the columns. The universally accepted, or shall I say the most commonly used value for alpha is 1. Okay. When we give small amount of penalization. Okay. So over here, what we did, we gave alpha value as 1. Iterations is nothing but how many times do you want to cross train the model. Okay. And then we are giving X train and Y train. Finally, we are now going to see coefficient and intercept. As soon as I run this, let's see what problem is. Lasso is not defined. Okay. Let's see where exactly am I calling it. Just a second. Okay. So this is where I was calling it. I'm going to paste it over here. And before running, I'm going to paste it over here as well. So once I run this, guys, now I'm going to zoom out. Look at the values between this one and this one. Okay. And tell me what difference are you able to witness. Okay. I'm going to give you 2 minutes. Any guesses what exactly is the difference between this value and this value? Who can tell me? So if you look closely, there is one column which became 0. Earlier, this column's value was 35. Okay. I feel this is the lowest value of the column because negative is also important. Okay. So negative 52 is very important as compared to positive 35. Okay. So then it is fine. But you can see that there was, shall I say, the lowest value came out to be this, I guess. That's why, or maybe there might be certain calculations in which it found that it can be reduced. So 252 became 238. 602 became, let's see, 1, 2, 3, 1, 2, 3, 4. I think it's 349 now. In short, it was able to decrease and it was able to kick out one of the columns, which was least important. Now, why only one column was kicked out? Because the alpha value over here was very low. Okay. What if I increase the alpha value from 1 to 10? As soon as I do this, you will see many of the columns are now 0. It has kicked out a lot of columns. Okay. If I make it 100, it is going to go even more penalizing. Only few columns are left. Okay. That's why alpha value plays a very important role. Okay. And how do you handle the alpha value? It comes down to R square value, MSE and MAE. Wherever you can see that you are able to decrease the number of columns, okay, without compromising the model performance, that value is going to be perfect for you. Okay. There's one, shall I say, view which you can just run. I'm pasting it over here, and it is going to show you how the alpha value is going to give you the insights. So if the alpha value is very small, all the features are working. Okay, every value has more than 0. As soon as you increase the features and you come across more than 100, majority of columns are now 0. Means extreme penalty is happening. Least penalty means you are not penalizing anything. Extreme penalty means you have made a lot of columns as 0 value coefficient. Means they are not going to be used in the model prediction. This is a very good example of Lasso's regression or Lasso's regularization, whatever you want to call it. So I'll now going to pause for like a couple of minutes so that if you have any questions, do let me know. And if you don't have any questions, please type in good to go so that I understand that we can move forward. So if the alpha is high, prediction quality is low. No, no, no. If the alpha value is high, so let me just type it over here. So the main point to note is if alpha is high, more penalization, more columns are going to be kicked out. if alpha is low. Okay, so less penalization. Less features are going to be kicked out. Okay, and if alpha is zero, no regularization is happening. Works exactly like normal linear regression. So working with less alpha is always better. Not really. If you have like thousands of columns, okay, and you want to bring it down to maybe tens, so higher alpha value is good. But if you're working with less columns, like suppose 20 or 30, so less value of alpha is very good. It's a good practice. Okay. Similarly, we can do the same thing with the ridge regularization as well. So we need to do is copy this, paste it over here, go back to the code part, back over here. We are going to now import ridge. Okay. And in the same fashion, I'm going to paste and OF. Okay. What was the power of ridge regularization, guys? Can anybody tell me? If L1 or the lassos was to kick out the unwanted columns, what was the power of L2? So the power of L2 is not to kick out the columns, but make them even lesser important. It to reduce the impact. That is correct. So once I do this, so you will see 214. Earlier it was somewhere around 252. Okay. Similarly, it was 379, and over here it becomes 312. So you will see alpha 1 value was important. As soon as I increase it, it is going to reduce it even further. Okay. So this is how it works. I feel I do have formula for L2, mathematical formula, but it's not really required for you. Again, it works on the same fashion, that if you increase the alpha value, it is going to be much more penalizing. If you decrease it, it is going to be less penalizing. If you keep it as zero, it is working as simple as linear regression. And why do we use regularization? Can anybody tell me again? There are two use cases. One, if we have many columns and we don't know which one is very much important, for that I use L1. Two, if my model is overfitting, means it is giving very good results in training part, but very bad results in test part. That's a problem of overfitting. For that, I can again use L2 or ridge regression, so that the impact it is creating becomes much more milder. That's it. I hope it was understood. If there are any questions, do let me know. Theory is perfect, because I want you guys to at least understand the theory, because I know these 4 hours are all about grasping the information, not to try it in practical. Okay. Any practical examples for these? The answer is yes, Rakshita. But in the interest of time, uh, you will find the, shall I say, the Jupyter notebook from this particular session in your download content. Okay. That particular notebook has all the much more aggressive practices of these things, like these particular algorithms. Okay. So the idea is understand the theory in the live class and apply this understanding at home whenever you get the time, apart from this particular class. Okay. Even if after this, if you have any questions, we can always connect in the next session to understand it more. Okay. Guys, any questions? Please let me know. If there are no questions, then also let me know. Uh, if there are no questions, we can take up one more topic before we go on a break. It's a small topic because it can't be explored more enough until we go to the classification part of the supervised machine learning. Will you also uploading the Scribble content? Of course, Shisha. Just like yesterday's class, you will get the PDF version of the Blackboard. Okay. So guys, the natural question comes up after all this thing. Like you must be considering like, oh my God, what is going to be the best way of let's first of all problem. Okay, the problem is which value of alpha is best. Just a second, guys. Just a second. Okay. So which value of alpha should I use? So what will be your smartest guess? The alpha value should be such way like XYZ anything so that my model performance increases. Okay. That's what we want, right? At the end, right? Anything else? Do you think that because we want alpha value in such way that my model performance maybe is, let's talk out MAE is the lowest. And what is the other name which we go give for the MAE at lowest? It is called as negative MAE, right? So I want the negative MAE to be the best. That value of alpha I'm going to use. Okay. But it's not like you are going to be like, first of all, I'm going to run first iteration with alpha equals to 1. Then I'm going to run with 1.2. Then I'm going to run with alpha is equal to 1.4. It's like you are going to get tired by rerunning. To overcome this problem by doing this thing, there is a kind of a loop which you can use, which can be used. And in that loop, you are going to say, okay, try all the values of alpha from 1 till 10 spaced at 0.2. Okay, so it is going to first run with the alpha of 1, then it is going to run with alpha of 1.2, then 1.4, so on and so forth till 9.8 and 10. And I want that MAE should be the least. Okay, so I want negative MAE to be the best scenario. Okay, and at whatever value of alpha the MAE becomes the least, give me that alpha value and I'm going to use that thing in my production ready model. Is this particular situational problem understood, guys? Come on, I don't want silent crowd. It becomes very difficult to teach. Right? What we want is a alpha value which is on loop. I'm going to give, okay, try all the values. Okay, like this is going to be around 50 different values which is going to be run on loop, and it is going to consider wherever the MAE values is registered. Okay, at one MAE value comes out to be 57, at 1.2 it becomes 55, at 1.4 it becomes 53, so on so on so on so on. At maybe 7 it becomes 10, at 8 it becomes again 12. So this is the least value it came up for alpha. Okay, so by the end of the loop it is going to say, okay, use alpha equals to 7 to get the best model out there. Okay, so this particular scenario is called as grid search CV. CV being cross validation and grid search. Like grid means all the values which you are going to give, it is going to do combination permutation, going to run each one of them, compare the result, and give you the best parameter which can be used for the best performing model. Okay, is the shall I say, is this clear to you guys? Any questions? What exactly the grid search is going to do? It is going to loop through. I will take again the silence as no questions. I'm going to copy one code, paste it over to you guys. Okay. And going to go back over here. What was the MAE which were we getting? Let's see. The MAE which we were getting was somewhere around 213 for train and 216 for the test part. Okay. What I'm going to do is I'm going to do the grid search. Look at this code. I'm importing the library. I'm doing a cross validation with 10 splits, means it is going to divide the data into 10 sets. Okay. And it is going to then do the repetitions of all the training and testing part. Okay. Then I'm creating a dictionary with alpha value. Over here, alpha is going to have all values from 0 till 1 at the space of 0.1. Okay, so first value is going to be 0, then 0.1, then 0.2, then 0.3, so on and so forth till 1. Okay, so this is where I'm trying to make a grid out of it. Even I can do something like this till 10, and I can make it as 20. So it is going to be from 0.2, 0.4, 0. Something like this till 10. Okay, but for now, let's keep it simple. So it is going to create 10 models. Okay, and all those models are going to be judged on negative mean absolute error. And then whichever alpha value is best, it is going to give us its MAE and what is the alpha value. So once I run this, repeated k-fold, let me just import it. Repeated k-fold. Okay. I'm just going to import this thing. And once this, okay, this model starts running, you can see it becomes slow because it is going to create 10 to 12 models. But since the data is very small, so it was getting MAE of 243 at the value of 0.9. So this is the best alpha value we were able to get without doing all the things manually. So this is what the power of grid search is. Any questions, do let me know. And if there are no questions, also let me. Won't this be expensive for large data set? Of course, it is very expensive. And that's why there's one more type of search which we are going to talk about. But as of now, is grid search understood by you guys? Okay, so very good point noted by Shisha. Very attentive, very good. So the only problem with grid search is it is going to run all the combination. Okay, and it is okay till the time the data is small. Okay, but as soon as the data becomes very large, this becomes troublesome. Okay, why? Because then all the models are run like 10, 20, 30 times. Okay, and it becomes impossible or becomes very slow. In that scenario, we do randomized search. CV. In randomized search, just like in grid search, we started from 0 till 1 at the space of 0.1. So all the combinations are 0, alpha value is 0, then 0.1, 2, 3. Let me type in everything. And 1. Okay. All these combinations were tried. Okay, that means the model ran 10 times minimum, or maybe 11 times. Okay, this is very slow and very expensive in terms of computation power. What randomized search does, it randomly picks numbers, maybe 0, then 2, then 3, then 5, then 6, then 8, then 9. Okay, wherever was able to find the least MAE, it is going to give you that. That is randomized search. It is not going to go through all the combinations. It is going to pick anything in random fashion. Okay, there is no biasness, only picking in random fashion and seeing which one performed the best. So that's why grid search CV becomes very expensive when the data becomes very large. In that scenario, we use randomized search. Okay, if you have a server and if you are a data scientist and if you have a weekend full of it, go for grid search. But if your server you're using over the weekday in your office and a lot of people are using that server, it's highly recommended to go for randomized search, because then the server is not busy throughout. In my career as a senior data analyst, I used to either run late at night at 12 o'clock, and it used to run for 10 hours before the next shift starts, or we still do very mathematically intensive practices in over the weekend. Okay, so that no one is using the server and the server is not getting blocked. So this is how data scientist works. Okay, okay, let's try to recap. Okay, in the recap we will talk about only regression. Okay, in regression we have covered things like simple linear regression, uh, its extension is going to be multilinear regression. What is a non-linear regression technique, guys? Can anybody tell me? Any guesses? It's polynomial regression, right? This is what we have covered so far. Then we talked about the performance metrics. The performance metrics, we covered topics like R square, adjusted R square. We talked about MSC, MAE, RMSC. Okay. After that, uh, what else which we have covered, guys? Can anybody tell me? We talked about cross validation. What are the different types of cross validation? One is called as k-fold, other is called as stratified k-fold. There is one more. Uh, it's only good enough for the theory. Leave one out. Okay. If you want to understand what is leave one out, I will just recommend you the screenshot which I shared above. Okay. This is the one. Leave one out. LOO. Okay. You can read through this and it will be much more understandable for you. So after cross validation, we talked about regularization. What are the different regularizations, guys? Can anybody tell me? Hmm. So there are two, L1 and L2. L1 is nothing but lasso. L2 is nothing but ridge. So guys, there is a homework for you. Combination of these two, L1 plus L2 makes elastic net. Okay. Take it as homework. Read about it, what exactly elastic net is and how exactly it uses both L1 and L2 at the same time. Okay. Finally, we ended our last topic before the break with grid search CV and randomized search CV. So these are the 7 topics which we have covered since yesterday. So I will just zoom out and take 1 minute, look at these topics. Are there any doubts, queries, misunderstanding, anything? Let me know. And if these topics are good enough in the theoretical manner, I will be okay with that thing. Okay. Because practice comes, coding is just like mathematics. You need to practice more. But theory is very important part to be clear of why we are doing what we are doing. Okay. Let me just highlight this one also. Leave one out. Take it as homework. Just study about it. Elastic net. We have covered these two. Stratified k-fold, which we have covered. Uh, you can also read about this once you're at home. We have covered rest of the things. Okay. So guys, with this, we end the topic, which is, okay. So Shisha is asking about cross validation. So cross validation, uh, in simply terms, is training the data much more aggressively on the same rows. Okay. Instead of just training the whole data in one go, we are going to break it down the learning process so that it is testing itself within the code only. This way, uh, what it does, that it makes a better judgment of coefficients. That's the best way of looking at it. Instead of just giving it one way, suppose, think about it this way. You have mathematics notebook, NCRT, something like this, and there are certain questions which are given at the back of the notebook. Okay. What happens that out of those 10 questions, you are given to only read the 8 questions. Try your learning on the last 2 questions. Okay. In next time, instead of the last two, top 2 questions are given as test, and on the rest of the 8, you are being taught. Similarly, this process is done n number of times, or shall I say k number of times, so that you get the hidden idea behind your learning. You're not just becoming a bookish child, you're actually understanding the key concept behind the data. That's why cross validation becomes very much important. Okay. So with this, we end our session on regression. Okay. Now, the next part for us is going to be classification. So the topic name is classification. Can anybody tell me what is classification in terms of supervised machine learning? How it is different than regression? When to use the classification algorithms? Very good. So whenever your, shall I say, dependent feature is discrete, or shall I say it's a categorical data, at that point, you have to use the algorithm, which is called as classification algorithms. Okay. Simple example is going to be just like I took the example yesterday, students with their IQ and numbers of hours studied. Okay. And whether that student pass or fail. Okay. Pass is denoted by 1, fail is denoted by 0. Okay. You can also say true or false, anything. Okay. So this data looks something like this. IQ of 90, hours studied 5, pass. IQ of 100, hours studied 4, pass. IQ of 70, hours studied 3, fail. Something like this. So over here, these are nothing but the discrete uh, dependent feature. Okay. The example I showed you is just containing zeros and ones. Okay. So where only 2 categories are present, these are called as binary classification problems. Binary classification. Okay. And where there are more than two, uh, shall I say, categories, maybe there is 0, 1, 2, 3, something like this. This becomes multi-class classification problem. Uh, Suppose there is a images data, and in images data, the image contains either a cat, a dog, or a horse. How many classes are there, guys? Can anyone tell me? So there are three classes, and this becomes a multi-class classification problem. But if there were only two categories like cat or dog, then these are nothing but two classes, and this becomes a binary class classification problem. Okay, and that's it. This is what you need to know. Now let's talk about the term which is called as event rate. Okay, so event rate is a term which is given uh, if we are talking about binary class classification, and we know there are zeros and ones. Okay, suppose we are talking about fraudulent transaction. Okay, fraudulent transactions, there are 1,000 transactions which happened. Okay, out of which only 10 transactions were fraudulent. Okay, so first of all, uh, if the data is A, B, C, D, and finally we have the Y, which is like fraud. Okay, question mark, and it is going to be 1 or 0, right? So what is the event rate? Event rate is going to be the number of ones divided by total rows. So if there are ones are 10, total rows are 1,000. So what do you think is the event rate over here? Can anybody tell me? Come on, what is the event rate? I hope you are not sleeping, guys. Come on, I can see a lot. I should see a lot more participation. No, wrong. How many ones are there? There are 10 rows with fraudulent transactions. Total were 1,000, shall I say, rows. Okay. So this is nothing but 10%. Oh, sorry, 1%. So the event rate over here is nothing but 1%. Is it understood now? So event rate is nothing but how many ones are there upon total row. Okay. This is your event rate. So this is a very important thing. Uh, because this stems out a very good topic which is called as class weightage. Okay, guys, if we have 1,000 rows, and zeros are around 500 and ones are around 500, what will you say? What is the event rate? Yes, Shisha, this is only for binary. We are going to talk about multi-class as well. What is the event rate? It is 50%, right? Or you can also call it as 0.5. Very good. But if zeros are now 700 and ones are now 300, what is the event rate now? 0.3, or you can call it as 30%. So guys, the main thing about classification problem is, first of all, we have to see how many zeros and ones are there if you're talking about binary class classification. Okay, but if we are talking about multi-class classification, this becomes much more advanced. But we are not going over there, because first we have to understand what is multi-class classification. Now there's a term which is called as imbalance data. Imbalance data is when the event rate is very low. So can you give me an example where event rate is very low? If total rows are 1000, so how many ones might be there? Anything, uh, anything below 50%. Okay, anything below 50% is going to become imbalanced, because zeros are going to be more, maybe like 600. Ones are going to be 400, right? So anything below 50% is going to be imbalance. But over here in data science world, imbalance is when your event rate is less than maybe 15% or 10%, something like this. Okay. Think of it this way. You are a data scientist in a bank. Okay. Your data is about money laundering. Is certain person doing money laundering or not? What is the percentage of event rate there might be for a fraudulent transaction? What do you think? Of course, it is going to be very less. It is going to be around 3%, maybe 2% of the whole daily transactions, right? Because not everybody has like guts to do something illegal, right? So this is the time where the data becomes highly imbalanced. And in this kind of scenario, we do some balancing techniques, but more on it later. As of now, the idea is to understand what is event rate. Is the term event rate clear to you guys now? Need few more confirmations? Okay, so let's come back to what exactly is classification problem. Maybe one of the classification example can be this. Maybe you are creating a model which is going to predict whether a mail is a spam or not. Okay, so what do you think one is going to be and zero is going to be, guys? Can anybody tell me? Very good. If the column name is spam, okay, so any row which is having spam as one, the mail, that particular mail is a spam. Any row which is having zero, it is a not spam. Okay, this is what we want to know. Suppose there are 1000 mails which are like collected in a data, and if my event rate should be 20%, what do you think is the number of rows for ones and zeros? This is your event rate. Correct. So no, not 20, Rakshita. Yes, 200 rows should be one, rest of the 800 rows should be zeros. Okay, because obviously not all the mails are spam. Some of the mails are spam, some of them are not spam. Okay, Shisha, good joke. Okay, so this particular thing uh, shows you how exactly binary class classification works. Now let's talk about what all algorithms actually work for this thing. First of all, the question is always like, what kind of dependent feature is this? Is this a continuous feature or is it discrete? If it becomes discrete, then you know it's a classification problem. Okay. Now, how many classes are there? Second question becomes, how many classes? If there are two classes, it becomes a binary class classification. If it's more than two, it becomes multi-class classification problem. To understand the classification equation, we are just going to start with two classes. Okay, it is the easiest way to understand it. And let's talk about algorithms. What all algorithms are there which can handle classification problems? Okay, So first and foremost, we are going to cover logistic regression. Okay. I think then afterwards you have naive Bayes. I have to see how is the chronology, naive Bayes. Okay. Let me see what is, yeah, naive Bayes. Third, you are going to do k nearest neighbors. Fourth algorithm you are going to learn is decision tree. And post that we have random forest. This is something which we are going to cover in future classes, guys. Okay, so don't worry. We are not going to cover everything today. SVM, support vector machines. And that's it. This is what you are going to cover or learn. Today, we are going to talk about only one algorithm, which is called as logistic regression. Okay. So guys, suppose there's one data set. Now let's start with logistic regression. Okay. So there's one data set. It looks something like this. And this is uh, pass slash fail. And let's only take IQ. Okay. So what we can show is like if IQ increases and pass and fail, something like this. These are pass people. Let's show it with blue. And these are students who failed. Can you reiterate over imbalance data after this? Yes, sure, Priti. We are going to cover it up. Don't worry about it. Okay. So we can see that IQ and pass and fail category can be easily distinguished. Okay. And how we can do it? If, let me just first of all remove this. If we create a line or a border, anything below this is going to be predicted as fail. Anything above this is going to be predicted as pass. Okay. So instead of pass or fail, let me write hours studied. That is the perfect way. Number of hours studied. Okay. And over here, blue equals to pass and red equals to fail. Okay. So you can see a student who has IQ somewhere around suppose 90 and hours studied is 5. So you can see that student was passed. Okay. Similarly, some student who has a IQ of 70, R study is only 2, they failed. This one is failed. So in short, what I'm able to show you that if there's a linear relationship, so the main point is if there is a linear relationship between the features, we can use a simple algo for classification. And what is that simple algo? That simple algorithm is called as logistic regression. So what exactly this logistic regression does? First of all, it is going to create one thing, y is equal to mx plus c. So step one is to create the linear relationship. Okay. Once the linear relationship is created by it, it is going to pass to a activation function. Okay. This activation function is also called as sigmoid function. And what is that sigmoid function? It denoted by this 1 upon 1 plus e raised to the power minus z. And where z equals to w x plus b. Okay. And what is this equation, guys? Can anybody tell me? What is this equation? This is sigmoid. What is this equation? Exactly. This is linear equation. Okay. So the idea is if I have a classification problem and I have a linear relationship, okay, if I push my linear relationship to a sigmoid function, it is going to help me determine between classification problems, 0 or 1, true or false, pass or fail. How does it do it? Let's see. Suppose this is the linear relationship which came up between certain things. Okay. Now, if I pass it to the sigmoid function, this particular output is going to look something like this. Okay. It is going to look. What is the meaning of pushing a linear into sigmoid? Simple idea is this is your equation, multiply over here. This is nothing but the z value comes over here. Okay. And the whole equation becomes your sigmoid equation. So you are multiplying certain thing. You're creating a formula. That's it. Okay. Is it understood? So after this is linear relationship and you are pushing it to the or making a calculation. Simple terms, making a calculation. Okay. Okay. And calculation is this sigmoid function. Once this linear equation is pushed to a sigmoid equation, this is the output. And this output is cut at 0.5. Any value which is above 0.5 will be denoted as 1. Any value which is below 0.5 is going to be denoted as 0. Okay. So this is how you create a simple thing into zeros and ones. Okay. Any questions? You don't have to go into the whole literal format. Okay. All you need to do is this linear equation is created. Okay. It is multiplied, or shall I say multiplied with sigmoid, and the output comes between 0 and 1. Okay. Anything which is above 0.5, 0.5, say above, it is denoted as 1. Anything which is below 0.5, it is denoted with 0. So this is how you do the binary classification. I'm going to zoom out, look at this whole equation. And if you have any questions in the theoretical part, just let me know. So this is the whole equation. Have a look, and I'm giving you 2 minutes. Okay. Then we are going to move forward. Any questions, guys? Okay. So this is the very basic thing which you need to know. So what all I did, which is very much different from linear regression, is in linear regression, we try to find relationship between two variables. Between two variables. Okay. And this helps us in giving the continuous output. But if we multiply this with a sigmoid function, okay, the output which is continuous in nature is going to be bucketed between 0 and 1. And anything which is above 0.5 is going to be denoted as 1. Anything below 0.5 is going to be denoted as 0. This is all you need to know. That's it. Okay. So for this, what I'm going to do is I'm going to take one data set, and in the interest of time, I'm going to show it directly over here. Okay. Is my screen visible, guys? Over here, I'm showing the VS Code. So you will see this is a sigmoid function, and the z value is nothing but the linear equation between the two features. if this is passed through this particular sigmoid function, this particular type of equation becomes, you don't have to learn it. You can take it as is. Okay, you don't have to learn it. But the output is between 0 and 1. Any value which is above 0.5 is denoted as 1. Anything which is below is going to be denoted as 0. So what happens? We are going to now try and import one data set. I'm going to run this code. The kernel is being connecting. Just a second. It is going to run now. I hope people know how the VS Code looks like. It's nothing but similar to what Jupyter Notebook is like, but a bit different interface. Okay. Now we have a data set. I'm going to run it. Oh, it is not going to work. Just a second. Where is the data? Let me see. Just a second. Copy as path. I'm just going to remove it. I'm going to run it. So guys, this particular data set talks about the breast cancer. Okay, it is going to create a model which can predict whether a certain patient is suffering from breast cancer or not. Okay, for that there are a lot many features like what is the diagnosis, what is the radius mean, what is the texture, what is the perimeter, means all the medical terms which are there. Okay, what is the size, what is the radius, what is the compactness, concavity, concave points, texture, okay, parameters, what all you think the doctor might judge by looking at a patient, whether they are suffering from breast cancer or not. Okay, so all those parameters are present over here. Finally, there's a column which is not viewable over here, is going to tell whether a patient is a breast cancer patient or not. Okay, so I just going to run this thing info, and info is going to show me that there are 33 columns. Many columns are there. Okay, what is diagnosis? Okay, so this is actually, this is your dependent feature. Okay, so M means malig and B means something like this. So M and B, we are going to talk more about it. Okay, and these are all the columns like radius, texture, perimeter, area, all the columns are given over here. Okay, through these columns from 2 onwards, we are going to predict whether a certain patient is a breast cancer patient or not. Okay, we are going to also describe this in nothing but your simple EDA. We are going to see if there are any nulls. We can see there are nulls in this particular column. We can drop it. Okay. So guys, this is your target. Okay. Benign and malignant. So I think benign means cancer patient. Let me just quickly Google it. It's a medical term, so I tend to forget it. Okay, so banning means safe. Thank you, Shrisha. So any patient who is considered as B is going to be safe. Any patient who has M is a cancer patient. Okay, so what is the event rate over here, guys? Can anybody tell me? We can see 350 are malignant, 210 are benign. So what is going to be the event rate? If any data scientist asks you, okay, this is your data set, what is the event rate? Let me just go back over here. So M is 350 and B is 210. So what is the event rate? So it is going to be 350 upon 350 plus 210. Okay. So let's quickly calculate. Is equal to 350 upon 350 plus 210. So somewhere around 62.5%. Okay. 62% is going to be the event rate because this is the main part. I want to see who all are a cancer patient, guys. So M upon B plus M. Okay. Is it understood, guys? Event rate. So if I go forward, let's see. Let's do some simple basic EDA. I'm going to remove the unwanted column. And who all are aware of this particular chart? I hope you know what exactly this chart shows. Any guesses? Heat map. Correct. So I'm not going to go through it because I'm pretty sure you already know about it. This shows you correlation. Wherever the correlation value becomes very high, typically anything above 9.9 to be specific. Uh, Shrisha, thank you so much. I saw your message now. Uh, so yeah, anything above zero point 0.9 is highly correlated and you want to drop one of those columns. Okay. So I hope you already know about it. So guys, what I'm going to do is diagnosis, and it is going to be first of all encoded. So anything which is your cancer becomes one, anything non-cancers becomes zero. So first of all, I did encoding part. Label encoding is going to be a very good part. Okay, so this is what I did, and this part is done. Let's move forward. And then I split the data into the independent and dependent. Can anybody look at this code and tell me if they were able to understand it? Any questions so far, guys? Yes, diagnosis is the target feature. That's correct. Okay. So after this, I'm going to do some standard scaling. Then I'm going to do logistic regression. Simply logistic regression is called. We are going to show iteration and run the random state. Once I run this, pipeline is nothing but it does one thing after other. First of all, I'm showing that first do the standard scaling. Okay, it is going to standardize the whole data, and then it is going to drop down and do the logistic regression. It's like a pipeline which I've created. That's it. That's all you need to know. What does pipeline mean? It is going to give sequential data. It is going to go through or passes through sequentially. First of all, it is going to go through standard scaler, then it is going with the logistic regression, and my data is done. Finally, we do some predictions and we have the predicted data. Okay. Now the thing is, that's all you should know from today's class. Okay. Rest of it, how to read the answers, what is the model performance is going to be covered in the next week's class. Okay. As of now, all you need to know is what is logistic regression, how exactly it works. Okay. Logistic regression is nothing but when your data is having linear relationship, all you can do is push it through sigmoid function, and it is going to give you output between 0 and 1. Okay, any value which is more than 0.5 is going to be considered as 1, and less than 0.5 is going to be considered as 0. So 42, because it is the answer to the ultimate. Yeah, Shisha, 42 is like universally accepted random state, but you can be rebellious and just change it. Okay, so okay, guys, with this, I hope you are able to understand theoretically what exactly is classification problem. We can take the next 10 minutes for any types of doubts or queries. Okay, so I'm also going to allow you guys to unmute yourself. So if you have any questions, you can go ahead and yeah, that's it. Where is the participants? You can unmute yourself now. If there are any questions, do let me know. Okay, so Preeti is asking about what exactly imbalance means. So as of now, you understood that event rate is nothing but number of ones upon total rows. Okay. What if this event rate becomes very, very smaller, like less than maybe 5%, let's say 10%. Okay. In this scenario, it shows that the data has majority of zeros and very less rows are represented with ones. Okay. How can I create a model in which there is very small percentage of data which is having one, and I have to predict zeros and ones? Okay, that's why those type of data where it is less than 5% or less than 1%, it becomes a problem and it becomes highly imbalanced data. What is imbalance over here? Because if it is 5%, that means 95% of my data is of zero category. Rest of the 5% of my data is containing one. Okay. And if my model should be trained such way that it can predict 1, it doesn't have that much data. It has much more data which is considered for 0. How can I handle such kind of thing? There are a lot of techniques which helps you handle this kind of things. That is called as imbalance data treatments.
So let's start by writing topics covered so far. And I might skip few topics or few lines, so I'll encourage you guys to remind me of those things. Okay? So first of all, we started with the introduction to machine learning. What exactly is machine learning? How exactly machine learning is useful in our current time, right? That talks about what are the different types of machine learning practices are there: supervised, unsupervised, semi-supervised, and reinforcement learning. Okay? What we started from machine learning was the first part, which was called as supervised machine learning. In supervised machine learning, we know that we talk about different types of supervised machine learning. One was called as regression. In regression, we talk about the fundamental regression technique, which is simple linear regression, followed by we talk about different techniques about simple linear regression. Okay, we have things like intercept and the coefficient. Okay, how exactly we can have a y and the relationship with x, which is nothing but a kind of a weighted relationship, right? And how is this weighted relationship described between by the linear equation? It's nothing but y is equal to mx plus c. This is what we learned so far. Okay. Then in simple linear regression, we also talked about the shall I say the performance metrics. In performance metrics, we talk about things like first is R square. The better format for R square is nothing but called as adjusted R square. How it's better, I hope you all are aware. If not, then I will encourage that you should revise what we have covered in the previous sessions. Then we talk about other things like MAE, MSE, and finally RMSE. Okay. So this tells us how good or how bad our linear model is, regression model is, right? But since we perform certain type of regression analysis, okay, and beyond that, what happens that we are like, okay, we got certain numbers. Is it the best model which I can make? The answer is no. There are multiple models which we have talked about beyond this thing in regression only. So the first is your linear regression, right? In linear regression, we should have a linear relationship. That's important. Guys, there's one good homework. So you can't always just go ahead and go and do the linear regression for a particular problem. There is a type of assumptions of linear regression. If and when these are passed, then only you can do the linear regression type. Okay. So this is nothing but your homework. So I'm just going to give it over here, and this is going to be your homework. There are 3 to 4 assumptions which you should know. Okay. And if those assumptions are met, then only you can go ahead and do the linear regression. It's kind of beyond your course as of now because it's not given in your course agenda. But coming from a data science background, coming from a person who takes a lot of interviews for data science roles, I recommend that you should know. Okay. If there is no linear relationship, then you can go for non-linear relationship type of regression, which is non-linear regression. And the best example over here can be your polynomial regression. There are a lot more type of regression algorithms which are there, but as of now, you are only aware of polynomial regression. Okay. Third, what we have talk about is L1, L2, and elastic net. Okay, I kept it in the third category only because these come in the same agenda. So one is ridge, one is lasso, one is the combination of them. So this is nothing but called as lasso regression. This is called as ridge regression. And this is the combination of L1 plus L2. Okay. So can anybody tell me what is the difference between ridge and lasso? Any guesses? What is the difference between ridge and lasso? Very good, Pragati. Exactly. Lasso is used when there are a lot of variables in, or shall I say, a lot of independent features which are present. And your idea is to bring it down to a certain number so that my model becomes much more faster without compromising on the performance of my model. Okay. Suppose there were 20 features which were there to predict your output. Okay. But the thing is, 20 is a big number. Can I bring it down to 15 or maybe 10 without compromising much on my performance? If my performance or R-square value was 0.9 with 20 features, can I bring it down to 10 features without compromising much? Maybe the R-square value is 0.88, right? So only 0.2 difference with regards to 10 features which are now only used. Okay, that makes our performance better. Oh, sorry, that makes a model much faster without compromising much on performance. And yes, good, Priyanshu. Ridge is used when there is a bit of overfitting. The model features looks very much important, but can I make it bit less overfitting so that it becomes much more generalized and the difference or the delta between the training output and the test output is not big? That's where ridge is used. My idea is to go for elastic net first. Okay, it is going to do both the things. It is the way you assign the penalty, it is going to do both the things. First of all, it is going to do lasso by removing any unwanted one. Second, it is going to also decrease the feature importance for the other features so that even the overfitting part is not happening. In short, best of both the worlds. Okay. And that's it. With this, we were able to complete not one, but 1, 2, 3, 4, and 5 types of regression algorithms. I hope these are a bit clear to you. Okay. Again, for the people who have just joined, homework is assumptions of linear regression. Okay, there are 3 to 4 assumptions which are very much, shall I say, famous or very much important. Okay. Whenever you become a data scientist and you come across a problem in which you have to predict something which is spontaneous in nature, uh, you have to first test all these assumptions. If all these assumptions come true, then only you can go ahead using the linear regression. Else you will go for non-linear type of regression analysis. After this, guys, we jump to the classification. Okay, so we talked about the first type of classification which we have covered in the last session, which was called as logistic regression. So the logistic regression idea derived from linear regression only means. Just like in linear regression, what we did, if we have certain type of relationship between X and Y, okay? And the relationship says if X increases, maybe Y also tends to change. So that is nothing but the kind of a weighted relationship, right? For how percentage of X is Y changing. It can change like this, it can change like this, something like this, okay? Now, instead of giving a certain continuous type of output, I want a discrete output between 0 and 1. 0 means fail, 1 means pass, something like this. Okay. How can I do it? So idea is just pass your linear regression equation through a function which is called a sigmoid function. Okay. The sigmoid function, what it does is going to bring the value between or the probability of certain thing occurring between 0 and 1. Okay. This is how it is able to help us determine whether it is going to be a fail or a pass category. Okay. Now sigmoid is denoted by the formula which is called as 1 upon 1 plus e raised to the power minus z. Over here, z is nothing but z is equal to w of x plus b, where w is nothing but your coefficient of x, b is nothing but a constant or intercept. Okay. So if you pass your equation through like this, so if your linear equation looks something like this, guys, if it looks something like this, it is going to get transformed into something which is going to look something like this. Okay. So the thing which you should know is that this is 0.5. Okay. The value, just like I told you, is nothing comes between 0 and 1. Okay. So 0 is over here, 0, and 1 is over here. Okay. Any value which is below 0.5, we term it as 0. As of now, I'm going to tell you how to distinguish between all of those things, how to play with the threshold, etc. But as of now, this is how it's done. Okay. So you can just go ahead, use your features, use your model, and go through this thing. Today also, what we are going to do, we are going to use the exact same data set for the different algorithms as well. Okay. So the data set was about predicting whether a certain patient is suffering from breast cancer or not. Okay. I hope people have that data handy with them. Okay. So what I'll do, I'm also going to open up my Jupyter notebook. That's what I'm going to also encourage you guys to open as well. Okay. Once it is open, do let me know so that we can move forward. So let's get started. This is going to be nothing but session 3. Today's date is going to be 0404-2026. And let me bring in paper. Set obvious parts. Okay. So first of all, what I have to do is import the necessary libraries. I hope people are also doing that with me hand to hand. So import pandas as pd, import numpy as np. Let's import cbon as sns, import matplotlib pyplot as plp. From Scikit-learn model selection, import train test split. From Scikit-learn preprocessing, import standard scaling. Let's also import from Scikit-learn linear model. Maybe not. Okay, let's pipeline. From Scikit-learn model import logistic. Import accuracy score. So these are what I'm going to first of all import, and pd.read_csv. df.head. Let's see. So there were a lot of features. Since you can see there is a dot coming, means there are a lot of features which are there. So why not, let's see, look at df.info. Okay, let's take a minute and see how the features are divided, guys. Okay, you can go alongside of me. First of all, we have to see that there are 568 entry. Okay, let's see. Yeah. So in short, 568 number of rows are there. Okay. We have around 33 columns. Okay. Yes, sure, Shisha, I can definitely do that. There you go. So we have 33 columns and we can see there is a diagnosis. Okay. I think this is the one which is the main feature. Okay. Malian and Binig, I apologize if I'm not pronouncing it correctly, but this is our main dependent feature. Rest of them are the independent features. I hope from your previous modules or from your previous time when you learned Python from the beginning, you might have heard of the correlation part. You might have heard different things like heat map, how exactly this all EDA is done. Okay, because we are stepping up from that particular module over here. Okay. So we can also look at df.describe. This is how df.describe looks like. Okay, you can go ahead and read about it. We can also look at how many missing values are there. df.isNA, or shall I say is null dot sum. We can see there's one column which is named as unnamed. 569 features are missing. What is unnamed? We don't have any column like unnamed. Okay, over here. We can just simply drop this one because it might be just a garbage value. Okay. So we know how exactly it needs to be done. Okay. Says there's no null and missing. What we can do as a first thing is to see how exactly the event rate looks like. Now, with the term event rate, what exactly does it mean? Can anybody tell me? I would like to also know who all are like doing coding side by side with me, because then I'll be aware that who all are like writing the code and I will be waiting for it. If everybody is just watching it, then it's also completely fine, no hard and fast rule. It's just that if you type in the code, you are going to learn much more code. Thank you for confirmation, Priyanshu, Vinita. Okay. Okay, Kavya, good. I hope so far people were able to like copy it. Any questions so far? So the idea is the event rate looks something like this. First of all, it is an event distribution. Right now, I'm not saying event rate. I'm talking about event distribution. Category, we are using breast cancer data. You can easily get it from your module. Okay. If you don't have access to it, I can also help you with pasting it over here in the chat. Just a second. There you go. So guys, this is what our data distribution looks like. How many cancer patients are there with respect to how many non-cancer patients are there. Okay. So malignant and benign. Sorry, I just not able to pronounce it correctly. But anyway, what you can do is this is nothing but the way of showing it with the help of chart, which is very good. Okay, it gives you much more information. I have pasted that code in the chat window. Okay, you can also try it too. Okay, but if you only want to see the numbers, how exactly can you see the numbers, guys? With the help of a function like diagnosis. Okay, what I can do is use a value count function. Who all knows what exactly is the output of value counts? Very good, Pragati. Once you do value counts, you will see how much difference of the data is if between the benign and the malignant. I think this is incorrect. 357, 357. Okay. This is incorrect. It should be other way around. Okay. So this is how it looks like. And if I talk about event rate, it is going to be whatever the one is. For us, one is malignant, okay, divided by the sum of both. Okay. And first of all, we can go ahead and drop the unwanted column, which we already know. I have pasted it in the chat window as well. So the unnamed 32 was something which was an unwanted column, which we have. So this is where we are starting the feature engineering type of stuff. Okay. So we have removed one unwanted feature. I think with which this all we have covered in the previous session also, but it's okay that we are copying it again. Second code which I have shared talks about the correlation. Okay. Take 1 minute and tell me which feature looks highly correlated to you over there. First of all, what is the definition of high correlation? Can anybody tell me? What if a certain feature is highly correlated? What exactly does it mean? Very good, Pragati. Nearly equal to 1. Yes. Anything which is nearly equal to 1 or minus 1 is highly correlated. Okay. One is in the positive direction, other is in the negative direction. Guys, I also want to know, is my voice loud and clear? Today I'm not using headphones. I'm just using my laptop's mic. If you feel it's not coming quite as good as earlier, just let me know. I'll attach my headphones. Thank you, Pragati. All right. So anything which is close to 1, you can see there are a lot of features which I can see are coming in light colors. Okay. That means these are highly correlated. The real good definition is that anything above 0.85 or 0.9 becomes highly correlated. You can drop one of the two features and you're not going to miss anything out of it. That means you're going to reduce the number of features which are there. Okay. So that's it. You can drop a certain amount of features from over here. Okay. One relationship between field is very high. Yes, yes, Priyanshu. There are a lot of features which are having highly correlation between each other. You can go ahead in your feature engineering part to remove them. But as of now, that is not important in our analysis because what we are doing is to understand what exactly is the different type of machine learning algorithms through which we can predict a certain patient is suffering from breast cancer or not. Okay. So the second part is to encode 0 and 1. Okay. So diagnosis is now converted into malignant if it is cancerous and non-cancerous is equal to 0. So let's go back to this board. The data which we are handling right now is the breast cancer prediction. Okay. In which what we are simplifying now is as y equals to 1 equals to cancerous. Okay. And 0 non-cancerous. That's what you have to know. Okay. As of now, this is what we want to see. Okay. Whether my model is able to perform this particular exercise or not. Okay. So if I just go back over here, the code which I last shared with you is going to encode M and B. Okay. So this is nothing but M. This is nothing but B. Malignant and benign. Okay. Benign means non-cancerous. Malignant means cancerous. I know Shisha has already helped me understand that particular pronunciation, but yeah, I'm not a good student. So you better be. Okay, guys. Okay. So now after we have done our feature engineering, I still have not done it clearly. It can be a really good homework for you. You can just remove the highly correlated features. You can play along with different feature engineering. That's on you. But as of now, let's understand the different algorithms. So first of all, I want to split my data into training and test set. Again, I have pasted my code into the chat window. So X is going to drop the diagnosis, Y is going to keep the diagnosis, and then we are going to split the data into training and test. So independent, dependent, and training and test. Both the steps are done together. Once that's done, guys, I'm going to show you a pipeline. Okay. I hope the pipeline is understood. So pipeline is nothing but, if you want to, what exactly is pipeline? Let me just write it down over here. Priyanshu, random state is a very good, shall I say, function through which, if your random state and my random state are same, the splitting of data happens equally in the same fashion. If the row number 2 comes as a test data set for you, it is going to come the test data set for me. So replication of the same type of splitting between your system, my system, and any system, the random state becomes very much important. So keep in mind that you keep the same number as mine. Okay. And 42 is like a random number. That's it. So guys, again, one question becomes, what is pipeline? So pipeline is nothing but a type of function which works in a sequential manner. Okay, just like in your suppose there's a pipe, okay, and in this pipe the water flows from left to right, okay, and suppose there are certain filtration processes which is happening, okay, maybe over here certain type of bacteria gets out, over here different types of bacteria gets out, over here maybe certain type of minerals are added, anything. So this is like a step 1, then this is like the step 2, and this is like a step 3. You can do them each individually, but if you like make a wrapper out of it, this is nothing but a type of a wrapper. Okay, it becomes a very systematic way of depiction. So this becomes a pipeline. So in data science, what exactly can be my pipeline? My pipeline can look something like this. First of all, I will be doing some feature engineering. Okay. Feature engineering like removing of highly correlated features. Okay. Removing or imputing the missing value treatments, analyzing outliers, anything. Okay. Then I can do feature selection. How can I do feature selections, guys? I can do feature selection by handling the correlation. Okay. If there are few of the features which are highly correlated, I can do it in the same. Okay. And finally is the model preparation, something like this, anything. You can have any number of things stacked together, and this all becomes a feature engineering, or shall I say machine learning pipeline. Okay. So if I just go back over here, look at this code, guys. This is the pipeline which I created. In this, there are two things which is happening. Can anybody tell me what are those two things which are happening over here? Very good, Priyanshu. Exactly. So there are two things which are happening simultaneously. First of all, it is going to do standard scaling. Then it is going to fit a model which is called a logistic model. Once I run this, okay, and my model is prepared. First of all, it is going to run this. Second, it is going to run this. Okay. Now, all I need to do is find the model performance, right? So for that, I'm going to put this code. First of all, you will see that I'm going to predict for the training set. Then I'm going to predict for the test. Okay. And then this is nothing but trying to show how exactly the output is coming there. Okay. So if I just remove this code for now and run this, it is going to give us normal output. We are not looking at any output, but now I'm going to look at the output of test set and how exactly my output is looking. Okay. So let's see how exactly my output is looking like. Copy this code, paste it over here. But before that, let's try to see exactly how my output looks like. So these are the probabilities of how exactly my output is going to look like. All right. You don't have to see it because everything is done automatically. So I can just remove it. The next step is to do the prediction. Oops. Copy, paste it over in the chat window and over here. So you will see, guys, this is a random data set which is shown over here. Over here, you will see row number 204. Actual label was 0, means the patient was non-cancerous. My model also predicted non-cancerous. And what is the probability of 1? So this probability is, what is the probability of 1? So probability of 1 was only 11% or 0.11. So according to logistic regression, is 0.11 less than 0.5? What is your answer? Exactly. Look at the next row. In the next row, you will see that the actual label is 1. The model also predicted 1. And the probability of the model is given as 0.99%, means it was 99% sure that this patient was suffering from cancer, which is very good. Again, 99%, again, hardly 0% and 0%, which is my model is performing amazingly good. So this is how it is shown. Okay, so why not let's talk more about how exactly classification model works. Okay. So how exactly classification model works, guys? So first of all, it exactly do the same principle. We have a data, and in this data, we have two things. One is your independent feature, and one is your dependent feature. Okay. Now, independent and dependent features are first of all divided, then they are divided into train and test set. And then we try to make a certain relationship out of them. How we do it? The first algorithm which we are talking about is called as logistic regression. Okay. The logistic regression formula works upon this same thing, that it is going to make a relationship of y is equal to mx plus c. Okay. And what it does, that it is going to push this particular formula upon this particular sigmoid function, which is 1 upon 1 plus e raised to power minus z. Now what happens if the y value is very high? Suppose our y value is around 100. So this value becomes very different and the answer is going to be close to 1. Similarly, if my y value is very low, suppose minus 100, this becomes different and the answer is around 0. So in short, this particular formula is playing a major role between dividing the data between the value 0 and 1. 0 become a 0 class, which is a false class, 1 becoming a true class. Okay. In this example, what we saw that there's y and there's y hat. I hope y and y hat is clear to everybody. Okay. In certain row number 1, okay, the y was 0 and y hat was also 0. But logistic regression gives us the data prediction in probability. Predicts in probability. So if I just go back and just take this whole data again. So I'll just paste it over here. Can anybody tell me which one is y and which one is y hat over here in these two? Any guesses? Very good. So actual is nothing but y, predicted is y hat. But how exactly this is being considered? Output of logistic regression is this. Logistic regression output. So this was the output. And I told you that anything which was below 0.5 is considered as 0. So since this is below 0.5, the output is 0 over here. This one is above 0.5, the output is 1. This is how we are able to make a classification problem. Okay. We can classify between 0 and 1. Okay. Now there might be a certain condition, guys, where my actual is 0, but my predicted might be 1. There might also be a case where actual is 1 and predicted is 0. These both are wrong predictions, right? Do you agree? Just like in your linear regression, if we had certain line like this, okay, and my dots were somewhere around over here, okay, this dot is very much far from the what was predicted over here. This is the error. How exactly error is calculated in regression, we know mean absolute error, mean square error, root mean square error. But how exactly the wrong prediction classification is calculated, that is calculated with the term which is called as confusion matrix. Okay. Confusion matrix is typically divided between, it is actually typically shown as a 2 by 2 box. You can something like actual value, and this is going to be predicted value. Now, if actual value was 0, over here it can be 1. Actual value 0, over here it can be 1. Okay. Yes, Shrisha. All those are the output from the original data set. These are randomly put, they are not in order, but these are the actual values. Okay. These are coming from the real data set. So looking over here, guys, if my model if the actual data said 0 and my model predicted as 0, is it a good thing or a bad thing? Suppose over here, if the value was 0 and my model is predicted 0, it is a good thing, right? So we are going to say it as true negative. Okay. This is nothing but true negative. If my model, if the actual value is 1 and my model predicted 1, what do you think is going to be a good thing or bad thing? Obviously good. This is called as true positive. Now, here comes the main part. If my actual value was 1 and it was predicted as 0, this becomes false positive. And if the actual value was 0, oh sorry, my bad, false negative. False negative, and this is false positive. Okay, means my model predicted it as 1, means a certain patient is having cancer, but that person was not having cancer. Then that means false positive. Falsely accused that the certain patient is suffering from cancer. Similarly, opposite of it, the patient was suffering from cancer, but my model predicted that the patient was not suffering, means false negative. Just like HIV negative, HIV positive, COVID negative, COVID positive. Okay. Now these two are called as errors. Okay. How these errors are termed as? These termed as type 1 and type 2 error. So this particular image is going to help you understand what exactly is the type 1 and type 2 error. Suppose you go to hospital and you're a male and you are predicted that you are pregnant. That's a false positive, or we can say it as a type 1 error. False positive is nothing but type 1 error. Similarly, false negative, when a patient or a certain person who comes in is pregnant and said that you're not pregnant, then false negative. Okay. So false positive, type 1 error, false negative, type 2 error. Okay. Can anybody tell me over here which one is type 1 error and type 2 error? So false positive, this is nothing but your type 1 error, and this is your type 2 error. Okay. Will that be clear to you guys? Okay, good. Now what I'll do, I'm just going to take this whole thing. Oops. I'm just going to take a snippet, bring it over here. And now we are going to talk about different type of performance metrics. Okay. Different performance metrics of classification problem. Or shall I say model, anything. First of all, the first and foremost is called as accuracy. Accuracy is called as true positive plus true negative upon everything else. True positive plus true negative plus false positive plus false negative. Okay. So why not just go back over here and we can see if I can bring in confusion matrix for you guys. Just a second. Okay. Let's copy it. Paste it over here. Copy it and paste it over here. So this is how my whole data looks like. Let me just copy it also. So sorry, let me just copy this. Okay. Bring it over here into the chat window. Okay, let's keep it over here. Okay, so can anybody tell me what is going to be the accuracy in this particular model? So to calculate it, first of all, we are going to see which are the proper thing. Means if binning was there and binning was predicted, that was 70. Malignant, this was this. So 70 plus 41 upon 70 plus 41 plus 1 plus 2. So this is the whole data which we are going to have. So it's going to be, let me just calculate it. Bring the calculator. It's 41 divided by 20 plus 41 plus 1 plus 2. It is going to be somewhere around 0.9736, or we can easily say 97.36% of accuracy. Okay, this is how you calculate the accuracy, in which we are only considering true positive, true negative, and all of these things. Okay, guys, can anybody tell me in this kind of scenario, suppose I have highly imbalanced data. Okay, but before that, what do you say that if my model has to predict something like COVID positive or COVID negative? Okay, and we again have this kind of model, and this is actual, this is predicted, this is again 0 1 0 1, and what is going to be bad if I'm going to have too many true positives or too many true negatives? Let's think about it. Okay. Again, I type false, actual, negative, false, positive. Okay. Think about it this way. We can directly know by calculating test data percentage of rows in emoji dataset. Yes, of course, Shrisha, you can do it. No worries about it. You don't even have to do that as well, because you just have to call this particular function, which is accuracy score. Just give in your y-test and y-test predictions, and it is going to do everything for you. Okay, this is how we are able to achieve this particular accuracy. Okay. So guys, suppose my model has to predict whether certain person is suffering from COVID or not. So if by chance I give a certain person false positive, means that person was not suffering from COVID. Yes, of course. But it was given that this person is suffering from COVID. What will happen with them? Nothing. Maybe like 15 days of quarantine. Okay, which is good enough if you compare with false negative. If a certain person is suffering from COVID and it is given that this person is not suffering from COVID, what is going to happen? They are going to travel to different place. They are going to spread their virus or not. Okay, so this becomes a very high penalty. So the idea is wherever the false negative is very dangerous. Okay, you don't use any other metric but recall. So recall is going to be the next type of formula. Let me just copy that formula for you. So let me just take a snippet. Good formula, just a second. Okay, this will work. No, not this one. Okay, so this is the formula for precision and recall. First of all, I'm talking about only recall because any model in which false negative is very dangerous. Okay, just like a COVID-19 type of place where predicting 0 when it is 1 is very dangerous. Then a recall function is used, which is nothing but true positive upon true positive plus false one. Let's take another scenario. Suppose you are a parent and you want to block adult movies and violent movies from your children. Okay, and you created a model. Okay, so that it is going to do this particular thing. Okay, it is going to give 0 as a child friendly, means not child friendly. I should say this. 0 as not child friendly, and 1 is child friendly content. Okay, in this, suppose you are you have made this model to work on YouTube. Okay, any violent type of things, any unwanted type of things or videos, you want to block them. So in this case, suppose it's okay that you make some cartoon as false negative, which is fine. Okay, it's okay that for some reason I just forgot that Tom and Jerry is good show for children, and I have made them as 0. False negative still acceptable, but if there is a certain type of horror movie, okay, which is having blood and violence, and I say false positive. So any model or any scenario where false positive is very risky, in those kind of scenario, we try to work on precision. Okay. Now, if this question comes in your, shall I say, interview, can you be able to define what is the difference between recall and precision and where exactly should those be used? The examples are very good over here. Okay, this can be your YouTube videos, and the above one is going to be your COVID test. Okay, wherever the wrong prediction is very dangerous. Certain scenario where false negative is very dangerous, you should use recall. Okay, so recall is going to give you a good answer. Similarly, where false positive is very dangerous, you have to use precision. All of these things, accuracy, precision, and recall have the same range 0 to 1, where anything which is closer to 1 is very good. Okay, that's it. This is all you need to know. Any questions so far, just let me know. I'm going to take a pause and just zoom out over here. And if you have any questions, we can take them. If no questions, then we can move on. Sure. So if you want to know what exactly the definition of them is, I'm going to share a document which can tell you what exactly does it mean. The main thing is where exactly you need to use it. Okay. Theoretical definitions are going to be there. What is the practical definition of practical usage? That's what I have told you, Priyanshu. Okay. So just to recall again, guys. So our confusion matrix looks something like this. Okay. We have true positive, true negative. Okay. False negative and false positive. Okay. We know that anything which is false positive or false negative is not a good model. Okay. Means it's the unwanted thing. False negative means if the actual value was 1, but my model predicted it as 0. False positive is which when the actual value was 0, but my model predicted as 1. Okay. These two are unwanted things. And in real world scenario, you can't make both of them 0 at once. Okay. You can try to mingle with the threshold to come close to a very satisfactory point. But you have to understand what kind of model you are working with. Is my model important in which scenario? Suppose my model is there to predict whether patient is suffering from cancer, suffering from COVID, anything like this. Wherever the false negative becomes very heavy. Suppose there's a patient who is like suffering from cancer, but the model predicted as non-cancerous. That's very, very dangerous, right? Similarly, certain patient is suffering from COVID and the model predicted that they are not suffering from COVID. Wrong diagnosis becomes very highly problematic. In those kind of scenarios, recall becomes very good, in which we try that we minimize the false negative as close to 0 as possible. Okay, we don't want any false negatives. Give us false positives, it's okay. It's fine. We are still going to be okay with it, but giving false negative is going to be very dangerous. On the opposite side, if my model is suppose tagging a certain videos being friendly for kids or not, okay, in this scenario giving false negative is still fine, that okay, there are certain shows which were predicted as not friendly for children, but they were, it's completely fine. But on the other side, there were certain definitive shows which are not friendly at all for children, but they were shown as safe for children. That becomes a very big problem. That is precision field. Okay. So if you want to know the definition, let me just take a snippet of it. It is going to help you understand it. So if we talk about precision, this is what precision looks like. The ratio corrected predicted positive instance to the total predicted positive instances. It indicates the quality of positive predictions. Okay. How much positively predicted are those, and out of which how many are correct? So how many true positives are there and how many false positives were there? Okay. So this becomes a very big agenda. Similarly, how many true positives are there and how many false negatives were there? So these are the small changes which defines precision and recall. But if you want a certain type of model which should have both the things correct, means they should be both balanced. So the balanced approach is going to be a score which is called as F1 score. Okay. So F1 score is a balance or weighted balance between precision and recall. With when you don't want, or shall I say, when you want lower number of false positives as well as lower number of false negatives, you are going to optimize on F1 score. The formula is going to look something like this. Let me just copy paste it over here. So this is nothing but your F1 score. in which we are using precision recall, and it is going to again give us a range between 0 and 1. Okay. So let's see if I can grab a very good example, and we are going to see how exactly my data is going to look like. Copying this data, coming back to my code part, pasting it over here. Okay, ignore this line. This is 0. We just want to see on the 1. So the model which I created, I already know the accuracy of my model came out to be 97%, which is very good over here. The model's precision came out to be 98%, very good. Recall came out to be 95%, and F1 score came out to be 96%. Everything is above 0.9. My model is working very good. Okay, this is how I'm able to judge my model. With this, there's one more important topic which you should know, which is called as ROC AUC curve. Okay, we are now going to talk about this thing. Shall I move forward, guys? So what is exactly ROC AUC curve? First of all, AUC's full form is area under the curve. Okay. And ROC is receivers operating characteristics. It's a mouthful, but once you understand it, you're going to be very much pro in it. Okay. First of all, to make you understand this thing, I'm going to open up one Excel notebook. Okay. Here is an Excel, and this is my model performance. Let's see. Just look at this particular data. There is like row number. These are the actual values, which we know is as Y. And this is my model's score. Okay. Means over here, the actual was cancer. My model score was 0.95. Actual was cancer, 85764. Actual was healthy. Model score was 0.9. Okay. According to this, guys, we already know that logistic regression says that anything above 0.5 is going to be a cancer or 1. Okay. So if I say if this is greater than 0.5, say cancer. Else you can say healthy. Okay. So what happened? So you will see that cancer, and over here it's healthy, over here it's wrong prediction, and over here it's healthy again. Okay. So see, yeah, it's fine. Okay. Let's talk about it now. So if we have a threshold, then we have true positive rate, and then we have false positive rate. So if my threshold is 0.5, how many true positives are there? First of all, this is positive, okay? The cancer is going to be 1. So if I say cancer, it is 1. Healthy is going to be 0. So true positive rate is going to be nothing but how many positives are there upon how many were actually positive, okay? So totally one were like around 5. So there are 5 cancer patients and 5 healthy patients. 5 were 1 and 5 were 0. Over here, out of 5, 4 were predicted as 1 and 1 was predicted as 0. So I can say that it is going to be 4 by 5. Okay. Is it understood? Any problem over here? Just look at this data. First of all, take time and try to understand. What I'll do, I'll try to put out this formula as well. For your, okay. So true positive rate. Okay, so I forgot about false negative also over here. So it is going to be, what is the true positive? 1, 2, 3, 4. So 4 divided by 4 plus false negative is going to be 1 over here. 0.9. Any problem in understanding this thing? Similarly, what is going to be false negative rate? Is going to be how many false negatives were there? If you can see, which are wrongly negative, which is 1 upon how many, what is true positive? We have 4 plus 1. So 0.2. Okay. So this is how you can see the true positive and false positive rate. What if my threshold was not 0.5, but it was something else? Maybe I will say 1. So according to 1, any probability which is over 1, then only I'm going to say that this particular patient is suffering from cancer. Else I'm going to say it as 0. What is going to happen then? What I'll do, I'll just copy this formula, paste it over here, and I'll say any patient who is having a probability of greater than 1, then only I'm going to say it is suffering from cancer. I can see that all of the patients were predicted as healthy, which is not correct, right? Okay. Similarly, over here, if I talk about the threshold one, the true positive rate is going to become 0, false positive rate is also going to become 0. Okay. Now let me try something else. This time I'm going to give it 0.9. Okay. So according to 0.9, any prediction which is above 0.9, I'm going to say that that patient is going to suffer from cancer, else it is healthy. So you can see this particular patient is going to be predicted as cancer suffering patient. So again, I'm going to change it over here. This is cancer. Let's see what about others. Let me make it equal to. So you will see over here, wrong classification are over here. This is also wrong classification. So at 0.9, if you do the calculation, the true positive rate is going to be 0.2 and 0.2. So this is how the model is performed. So let's talk about what exactly is ROC AUC curve. Okay. So this particular curve is divided between the true positive rate and false positive rate. Can anybody tell me how exactly we want our model to be? Okay. So if this is 0, this is also 0, this is 1, and this is also 1. So we want our model to give us the best performing model with true positive rate as 100% and false positive rate as 0. This is the ideal model. Ideal model where true positive rate equals to 1 and there are no false positive rate. There are no false predictions. But in real world, this doesn't happen. Okay. The worst model is going to be somewhere over here. Okay. Or shall I say somewhere over here. Okay. In which true positive rate and false positive rate are equal. So first of all, the worst model is going to be here, where no correct predictions are made. Okay. And this is a random guess. So guys, random guess, what exactly does this mean? Suppose you have a coin and you are a person who is going to give me the probability of head and tail. What is the probability of head and tail, guys? 50%, 0.5, 0.5, right? 50% of time your model is going to give you, or your guess is going to be correct. 50% of time your guess is going to be incorrect. Okay. So this particular place is nothing but random guess, where you have equal amount of true positive rate and true negative rate. Okay. Now to understand this whole curve, anything which is below this line, this is nothing but a random line. Okay. Any human can tell a 50% accurate answer when there are only two things: head or tail, 0 or 1, pass or fail, yes or no, positive or negative, right? These are two things which we know that there's only 50% probability. So this becomes a random line. Any probability curve which is below this is a bad model. Okay, bad model. We have to try and make our model above this curve. Okay, and the higher this curvature is, the better our model is. And the best model which we know looks something like this. Okay, so what exactly is happening? This is the area under the curve. Okay, or shall I say this whole area under the curve? Okay, the higher the area under the curve, the better the model is. Okay, so over here, according to this particular screen, pink model is having the highest AUV, highest area under the curve. Okay, this becomes the best model, number one model. Number two model is green because it is better than green model. It is better than blue model, right? And number third is our blue model. The orange line over here is nothing but your random guess. What is random guess? We know that when there are two classes, head or tail, true or false, yes or no, there is a 50% probability that you are going to pick one. So 50% is a random guess. Anything below means you're deliberating, making your model predict incorrect all the time. Okay. So this is your area under the curve intuition. Okay. It is depicted between true positive rate and false positive rate. Over here, this is the best model. Over here, this is a random guess. And over here, it is no correct prediction, means worst model. So suppose any type of diagram which is having certain like this is the worst model possible. Okay. The way it is predicted is called as area under the curve. So if you look at this particular part, you will see that there are 10 patients. Okay? And we have the model accuracy, or shall I say model prediction and probability. Okay. And a simple, shall I say, default rule is anything above 0.5 is going to be treated as 1. Anything below 0.5 should be treated as 0. But why? How can we make our model tweak with that particular threshold so that we get the higher, better accuracy overall? Okay. If we make our model that anything above 1 should be termed as cancerous, anything below 1 prediction should be termed as 0. You will see that everything is predicted as non-cancerous or healthy, which is completely wrong. Okay. You will see at this particular threshold, true positive rate is 0, false positive rate is also 0. Means the model is not predicting positive, or shall I say cancer, at all. This becomes the bottom left part. What is the bottom left part? This is the bottom left part over here. The model is performing over here, which is the worst thing. Okay. Let's take another scenario. Over here, if we take it as 0.9, we will see that it is going to come as 0.2 and 0.2. Okay. What is 0.2 and 0.2? It is going to be somewhere around over here. My model is performing over here. Again, not a very good model. Okay. On the same note, we are going to tweak and turn with our model so that we can see how exactly my model's performance looks like. The best model out there is going to look something like this, where it is over here. What exactly this particular point is telling us? That the true prediction or the true positive prediction is 100%. False positive prediction means any patient is not falsely accused that they're cancerous is at 0%. Then our model is ideal, means it is performing the best performance over there. Okay. On the exact opposite side, I can also make a certain type of model which is on the right bottom over here, in which true positive rate is 0%, but false positive rate is 100%. Means all the non-cancerous patients were treated as cancerous and all the cancers were treated as non-cancer, means exactly the opposite one. Okay, this is again a very bad type of format. Other is 50% are predicted as cancer when only 50% of them are correct and 50% of them are not correct. Okay, in that kind of scenario, this is the middle line. Okay, so the idea is we have to make a model which can give us better result. Okay, it is going to give us more of a true positive and less of a false positive, and this is how the model looks like. The better the model curve is, the better the model performance is. The highest performance is when it looks something like this, the pink one. The next best is green one, in which we are still getting a very good performance, but the pink one is like the ideal thing. We don't really receive a certain type of model, which the ROC curve looks like this. Blue is good, but anything below this random line is very bad. Okay, so this is your ROC AUC. AUC is area under the curve and ROC is receiver's operating characteristics. How much true positive rate is received to us on the cost of false positive rate. That's it. Okay. Okay. So far we have understood first of all logistic regression from our previous class and the performance metrics which are there in the classification type of problems. Okay. Now, what we have to learn is the different algorithms which are there. From this particular algorithm, which saw that 97% accuracy was achieved, precision was 98%, recall was 95%, F1 score was 96%. Okay. Since this particular model is a breast cancer prediction model, which type of accuracy, or shall I say performance metric, should I consider more? What do you think? Take your time. This is a breast cancer prediction model. Okay. So what do you think is going to be the very important type of metric over here? Any guesses?
Since there are no guesses, I think I might have to answer it myself. Uh, First of all, we know that uh, the model needs to have a balanced type of false positive and false negative. If a certain patient is predicted as cancers, but they are not cancerous, they might have to go through a chemotherapy, which is very bad also. If a certain patient is predicted non-cancerous, but they are cancerous, then also it is life-threatening to them. So both false positive as well as false negative are very much crucial for us. So as at these kind of scenarios, we go for F1 score. Okay, because it's a weighted average between the false positive and the false negative, or shall I say precision and recall. Okay, so we will refer to two main agendas over here, which is going to be accuracy, because accuracy is like the fundamental type of metric, and the F1 score. Wherever these two are very much balanced, or shall I say good, then the model is going to be used for the final production. Now, for the second type of model, we are going to talk about a model which is called as naive Bayes. Okay, it works on the formula, or shall I say theory, which is called as Bayes theorem, naive Bayes. Okay, to understand this, guys, I'm going to show you one PPT, and I want you guys to be attentive on this one. Okay, let me just open it. Three. Okay, so let me take it over here. Bayes theorem. First of all, let's try to understand this thing. So guys, suppose you work, or shall I say you are going to visit a particular factory, and this particular factory has two machines. Okay, machine one, this is the machine one, this is machine two. the machines are there to make wrenches. These are wrenches. Okay. Machine 1 also produces wrenches. Machine 2 also produces wrenches. Okay. Now we know that any type of machine is not a highly accurate machine. There might be some defects. So at the end of the day, first of all, we have a lot of wrenches which are collected in one bin. Okay. But we know that any machine is not perfectly aligned. So there might be certain defects. So you can see over here, there are certain defective wrenches which are present over here. Okay. And what exactly happens? That the question comes, if I pick up a particular wrench, what is the probability that particular wrench came from machine number 2? So this is going to be our problem. Is the particular use case clear to you guys? So if it is clear, let's take it to the this particular scenario. Okay. So what is the scenario over here? Let me just come back over here. We have to find what is the probability if a certain defected item is picked, it is coming from machine number 2. To understand this, let's talk about a theorem which is used, which is called as Bayes theorem. If you look at this particular theorem, is it like a nostalgic moment which is getting hit, or are you able to like remember this kind of particular formula? Any guesses, yes or no? We have like studied this particular formula in our school time, maybe 9th or 10th standard. So this is how exactly we are going to solve our classification problem as well. But to understand it, I want you to look at this particular thing. First of all, what I'm going to do is going to see how exactly my data is divided. First of all, we had two machines which are making wrenches. Okay. There is machine 1 and then there is machine 2. And the idea, or shall I just say the question is, out of all the defectives, what is the probability that a certain defected item is coming from machine B? To understand this, machine 2. Okay. To understand this, first of all, we should know a lot of things. And those are going to be how many different agendas are there. So to understand that, let me just copy this and paste it over here. So we can see that machine 1 is preparing 30 wrenches per hour. Machine 2 is making 20 wrenches per hour. There is 1% defectives in both the machines. Okay. So only one out of 100 wrenches which are being made. Okay. Only like one wrench is being defected. Rest of the 99 are non-defective. And there is one more thing, like 50% of wrenches defected are coming from machine 1 and 50% coming from machine 2. So this is what we have known so far. Any questions, guys, in understanding this thing? Any questions, any doubts? No? Okay. So let's try to go more deeper into this thing. Okay. So what is the probability, first of all, of M1? The probability of M1 is how many in 1 hour are wrenches being created. There are 30 plus 20, 50 wrenches which are being created. So 30 by 50 is going to be the probability of M1, means 0.6. Again, what is the probability of M2? It is going to be 20 by 50, which is nothing but 0.4. So first thing we have already known. We know that the P percentage of defective is already known, which is 1%, or we can also say at 0.01. Okay. Now we also know from this particular part that the probability of defective is 50% for both of them, means what is the probability of a defective when it is coming from machine 1 is nothing but 0.5. Similarly, probability of machine 2 of defective is nothing but 0.5. So far, is it clear, guys? Now, the question which we have is what is the probability of a defective coming from machine 2, right? It is going to be nothing but the formula is M2 by D into probability of D upon probability of M2. So what is going to be the answer? M2 by D, we already know is 0.5 into probability of defective, we already know 0.01 upon M2 is 0.4. If you do the calculation, it is going to come somewhere around, let's see, 1.25%. So let me just take you back to the PPT. It is going to help you understand more. Let me zoom in. So we already know that probability of machine 1 is 0.6, probability of machine 2 is 0.4, defective is 1% and 50-50%. Since we want to know the defective coming from machine 2, so the first of about machine 1 is not relevant for us. These are the 3 to 4 things which we already have, and this is what we want to find. Now just use the Bayes theorem formula, and you have to do P2 by defective into P defective upon P of M2. If you put in all the data over here, multiply it, this is the probability which is coming out for the defect from machine 2. This is how your naive Bayes theories work. Let me just try to show you what exactly we have calculated over here. So these are all the calculations which you need to use. And what you need to find out is what is the probability of defective coming from M1. No, Shisha, this is not how you calculate it. The idea is to use exactly same this formula. So P of D upon M1 is going to be P of M1 upon D into P of D upon P of M1. Can anybody do the quick calculation and let me know what is the answer? So the answer is going to look something like this. What is P M1 upon D? We know it's already 0.5% into 0.01 upon 0.6%. Over here, we calculate 0.6. If you do the calculation, I think it comes around 8% or something. Let me just look at it quickly. So yeah, if you do the calculation, you're going to get the answer, 8.33. Very good, Devika. So this is how you are creating, or shall I say, you are understanding the particular type of naive Bayes theory. Okay. And if you look at this thing, Bayes rules provide as a formula for the probability of Y given a certain feature X. What is the probability of us getting a cancerous patient when all the independent features are like this? This is how Bayes theorem works. Okay. When the feature are independent, we can extend Bayes rule to call it as naive Bayes. Okay. And this is how Bayes theory works. To understand it a bit more, okay, this is how the formula works. Like, I'm going to share you this PPT. This is what I have created personally. Okay. And it is going to give you very, very intuitive answer. Okay. To understand it a bit further, let me take one data set. Okay. And I'm going to open up my Excel. This is the data set, guys. Okay. This particular data set calls about, can you pet a certain type of animal or not? If the animal is dog, the size of the animal, or shall I say the size of the dog, is medium, the color is black, the probability that that dog is pettable shall I say, is going to be yes. If the dog is big and the color is white, no, you can't pet it. Rat, small, white, yes. Cow, big, white, yes. Something like this. You have this whole data, okay, in which there are certain different independent features and the dependent feature, yes or no. Can you pet it or not? How do you solve it accordingly? First of all you need to do is create a certain type of data. First of all, I am going to only look at the one feature or one independent feature, which is called as dog. Okay. And this is how I'm going to make the scenario. First of all, I'm going to first say, is a dog pettable? Yes or no? Okay. How many yes are there? I'm going to calculate it first. I'm going to just filter down on yes. I can see that there are 8 number of pets which I can be said as yes. Rest of them out of 14, which is around 6. So 8 yes and 6 no's. Okay. So I can say this as 8 divided by 14. Okay. Alt HN and U. 8 divided by 14. And this is 6 divided by 14. Okay. Uh, Alt HN number 6 divided by 14. Okay. 0.57, 0.43. Okay. Now I'm going to create one for the dog. Oh, sorry, the animal. How many animals are there? There is one dog, there's one rat, and one there is cow. Okay. So in the interest of time, I have already created it. This is how it is going to look like. Uh, Dog. How many dogs you can pet? 4. No, no as 1. What is the probability of y? Which is 4 divided by 8. How many y's were there? There were 8 y's, and out of 8, 4 of them are coming from dog. So 4 divided by 8. How many no's? There was 1 no, and there were 6 no's overall. So 1 divided by 6. Similarly for rat, you are going to do the same function, and same for cow. Please look through this. If you understand this one table, the other two tables are going to be easily understood. Okay. Let's do the same exercise for the other features also. Now it was animal. Let's talk about the size of the animal. This is how the table is going to look like. Similarly, what is the body color? Okay. Similarly, this is going to be the whole data. The small, we have 3, 3 by 8, 2, 2 by 6. 2, 2 by 8, 2, 2 by 6. This is how I will create for all the features. Okay. For the ease over here, I'll say Alt HN text. Ashwati. So this is going to be nothing but 8 divided by 14, and this is going to be 6 divided by 14. This is the whole data which I have now. Okay, guys. Now, if the question comes up that what is the probability that if there is a cow who is medium and black is going to be pettable, can I pet that particular cow or not? Okay. How will I do it? The formula is going to look something like this. I'm just going to paste it over here. Take it over here and paste it over here. Okay. So this is the formula, which is exactly the Bayes theorem. Okay. Y equals to test. Okay. This is what you have to look at it. Okay. So what is the probability of cow and yes? So first of all, cow and yes is 3 by 8, right? So we are going to do is 3 by 8 into medium and yes. Over here, medium and yes, which is 2 by 8. So let me just highlight this. 3 by 8, 2 by 8, black and yes, 3 by 8. And what is the probability of yes, which is 8 by 14. All you need to do is multiply all these 3 values or 4 values. So the answer should come out to be equals to 3 by 8 into 2 by 8 into 3 by 8 into 8 by 14. And without taking much more of time, the answer is going to be somewhere around 0.02. Okay, 0.02. This is the answer which is coming. Don't worry, I'm going to tell you the next step also. And what is the probability of no? It is going to be exactly the different one. Okay, so for no, we know it is going to be cow, and no, it is going to be 2 by 6. 2 by 6. 1 by 6, and 6 by 14. If you calculate this, let's go back over here. So this was for yes, and for no, it is going to be 2 by 6 into 2 by 6 into 1 by 6 into 6 by 14. Once you do this whole calculation, the answer is going to come out to be 0.0079. Okay. So answer is 0.0079. We have both the probabilities with us now. Okay. Now you will say, sir, this doesn't look good, right? To get the final answer, you have to normalize these two numbers. How do you do it? It's very easy. You just go down. You have to normalize it using this particular method. Below you have to add both the numbers, and above you have to change it. Okay. So to get the probability of yes, all you need to do is 0.02 upon 0.02 plus 0.0079. For probability of no, you're going to do 0.0079 upon 0.0079 plus 0.02. And the final answer is going to come like 71.68% and other is 28.31%. So guys, if the probability of yes is 71%, probability of no is 28%, what is the probability that the cow, where is the question? The cow who is medium and black is petable. Can anybody tell me from these two? Exactly. So in this scenario, the answer is going to be yes, it is a petable. The p equals to 1 is going to be there, or p is equal to y. So this is the very simplification of the idea how exactly Bayes theorem is used in the classification problem. Okay. Okay, guys, what we can do now is go back to our this particular table and try to do this exact same thing on Jupyter Notebook. Okay. So for Bayes theorem, all you need to do is, first of all, import the library. Okay. And call the particular pipeline. So if you will see over here from sklearn.naive Bayes, import Gaussian naive Bayes theorem. Okay. And then in the pipeline, instead of logistic regression, all I'm doing is going for the Gaussian naive Bayes. Okay. Finally, I'm fitting that particular model. If I run this model is run. And then all I need to do is copy and run this particular code. This code is going to, first of all, tell us the accuracies. Okay. The training accuracy has fallen down to 93%. Testing accuracy has improved to 96.49%. Okay. So if I just go back over here, okay, over here, testing accuracy was better. So we can see that naive Bayes, the model is not performing as good as logistic regression, but it's a very good type of algorithm which you can try. Okay. Any questions so far? Let's also look at confusion matrix for this particular model. I'm going to paste that also over here. In confusion matrix, we can see logistic regression, there were two false negatives. Okay. Instead of over here it's three. So it's hardly any difference, but we can see that, yeah, there's still a difference between them. Okay. Let's also look at the whole model performance over here, which looks like this. Okay. You will see 96% accuracy as compared to 97% accuracy for logistic regression, 95% F1 score as compared to 96% F1 score in the logistic regression. Okay. So next algorithm, or shall I say next classification algorithm, is called as KNN, which is also called as K nearest neighbors. Okay. I think from the name itself, you are going to understand what exactly we are trying to talk about. So, guys, let's take a good example. Suppose there's one road. Okay, this is one road, and on this road there are a lot of cafes, sports cafes. Okay, over here there's a sports cafe which is specifically for football fans, and over here there's a cafe which is specifically for the cricket fans. Now, there's one person who walks in, and suppose that person comes from over here and goes to this particular cafe. Okay, what is the probability that this particular person who came into this particular cafe is a football fan? High or low probability? Similarly, a certain person who comes in and goes to this particular neighborhood, or shall I say this particular cafe, what is the probability that this particular person is a football fan? High or low? Any guesses? So over here, if certain person who entered, we can say that there's a high chances that this particular person is a football fan. But if the person who entered over here, there's a low chance that that particular person is a football fan because they entered into the cricket cafe. On this context only, the k nearest neighbor algorithm works. Okay, how? Let me again show you this time with the help of PPT. So if we talk about a certain k nearest neighbor algorithm, it is also called a distance algorithm. So if we just go back over here, the distance from the actual point is very far. Okay, so there is a low chance that this is a football fan, but over here the distance was very low. So k nearest neighbor algorithm works on a distance theorem. Does anybody of you know Euclidean distance? Euclidean distance? No? Okay, we are going to talk about that as well. But as of now, suppose there's a new data point, okay, and there are two categories, a red category and a green category. What is the probability that this particular gray point will come in red or in green? It is made sure by looking at certain number of nearest neighbors, okay, and that particular will decide whether this is going to be green or red. Okay, how exactly it is done? First of all, we have to choose how many neighbors do you want to look at. Okay, maybe three, maybe four, maybe five. Okay, then we have to calculate a distance between those neighbors from the data point. Okay, and whoever wins this round is going to decide which category this is going to be in. Okay, so first of all, why not let's talk about Euclidean distance. Anybody in the class knows what is Euclidean distance? So if we have a certain graph, okay, we are again going back to graph theory. This is your point one. This is your point two. For point one, we know it is going to be x1, y1. Point two, it is going to be x2, y2. What is the distance between these 2 points? The straight line distance between 2 points is Euclidean distance, correct? So the distance between P1, P2 can be easily calculated by square root of, sorry, square root of x1 minus x2 whole square plus y1 minus y2 whole square. This is nothing but the formula for Euclidean distance. Okay, this is the straight line formula which can be used. There are many distance formulas which are there, but the most famous or most important one is the Euclidean distance. Is it clear now? We have studied this particular thing in our school time as well, if you remember. Yes. So the idea of k nearest neighbor is simple. First of all you need to do is find how many nearest neighbors do you want to see. So the value of k, and k is how many neighbors. Okay. So let's take the same example which was there in the PPT. Okay. Let's take this. Uh, okay. And paste it over here. Suppose my k value, I will keep it as 5. K equals to 5. So first of all, I am going to calculate the distance with the 5 distances, or shall I say I will calculate with everyone. I'm going to calculate the distance with every one of them from here, 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 each one of them same here, 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 each one of them over here as well. Okay. And from this, I'm going to see the lowest 5 distance. Okay. So lowest 5 distance, I can say this point and this point, this is the lowest. Okay. So the first is going to be red. Second, this one and this one, again red. Third, I can see this one and this one, it is going to be green. Fourth, I think this one and this one, green. And fifth, I can see this one and this one, which is red. Okay. So if I have to do a democratic vote over here, which one will win? A red will win or green will win? In top 5 lowest distances, 3 are red and 2 are green. So I can safely say that this particular gray point belongs to the red category. This is the simplest way of assigning to the different categories. Is the intuition clear now, guys? Good. So, you know, the Euclidean distance formula looks something like this. All you need to do is find what value of k should be there. So the natural question comes up that, sir, how do you find the value of k? How do you find perfect value of k? The easiest answer, or shall I say the quickest answer, is elbow method. Okay. So what is elbow method? Let's go and find it out. So first of all, there are different distance formulas. All we have studied right now is Euclidean distance. Euclidean distance is the shortest distance which is there between 2 points. Manhattan distance is the perpendicular distance. Okay. This is the Manhattan distance. This plus this. Minkowski distance is the weighted average between Euclidean and Manhattan. Okay. Then cosine distance is the cosine distance, which is theta, and this is the cosine distance. Jacquard distance is again one more distance between the bit rate of distances. But the most important one is the Euclidean distance. Okay, all you need to do know right now is Euclidean distance. As a homework, you can take this as homework. What are the different distances? Okay, and what are the different importance of these distances? It's bit beyond this particular course, but it's a good to know knowledge if you want to know further about what is a distance. Okay, but as of now, the requirement is only this particular distance, Euclidean distance. Okay, so let's move forward. So again, we talked about this. There are 3 neighbors over here, 2 neighbors over here. By the democratic vote, it became a red category. Okay. Now, k value is calculated by the error rate, first of all. And if we plot it by the k over here, how many k's? Maybe 0, k, 2, 5, 7, 10, so on and so forth. Wherever there is an elbow which is happening, okay, elbow looks something like this, okay. Wherever your elbow comes up is going to be the best distance you can take up. Wherever the drastic change between this stops, okay. So somewhere around over here, I will say, or over here, any value between these values can be the perfect value for k. Okay. The error rate is how much distance is there. Okay. If you only look at one, shall I go back over here? If k equals to 1, guys, okay, k equals to 1, I'm only going to look at one particular, shall I say, neighbor, and I'm only going to decide it, means top one, or shall I say lowest one, lowest one. Okay. And in this case, I can see the lowest is red only. So my prediction are going to be correct. But if I, by any chance, there was one green over here, okay, which was much more nearer to this particular point, and by choosing k equals to 1, the model predicts that this particular category is going to be in green. That is error. Error is what is the difference between the y and the y pred. Okay. If the y and y pred are very big, or shall I say opposite, the error is high. Okay. And if they are low, then the error is low. Okay. So this is how I can do it. That's why if I go for k equals to 2, okay, the my prediction being wrong, the error rate is going to decrease. Okay. If I go to 3, it is going to decrease again. If I take 4, going to decrease again. After one point, this is going to saturate. Okay. That saturation point where the saturation starts is going to be the best k value. Okay. So if I just go back to this particular point, this is the error rate. Okay. At after one point, it saturates. Okay. So before the saturation, wherever our value is getting drastically changed, we can easily take that value as the k value. Okay. Again, there is algorithm for it. Again, there is a pictorial view which you can go for it so that you find the k value. So guys, if I, as an interviewer, ask you, okay, you're using k nearest neighbor algorithm, how were you able to find the proper k value? What is going to be your answer? Exactly, elbow point or elbow method. Okay. And if they are going to ask you what is the X and Y in elbow, you're going to say the error rate, how much error is there in my prediction, and how many cluster, shall I say, the nearest neighbor should I look on. So this is how much error which is happening, error rate, and what is the different K values. Okay. Through this, I'm going to able to make the proper judgment. Okay. So let's talk about the advantages. It is very understandable and implemented. Uh, in the instance-based learning, lazy learning algorithm, the main problem is the different scales. So there's one thing which you should know, guys. A very important thing. It is asked almost in every interview. Okay. Wherever distance algorithm is used, the need of standardization slash normalization becomes mandatory. Okay. It is very much important. Of course, Priti, I'm going to make you understand this thing. Suppose this time I'm just going to take one example, years of experience and salary. Years of experience, starts from 0 and going to go till maybe 40 or maybe 50. You only work for 40 years or 50 years of your life. Your salary goes from 0 till maybe million of dollars. Okay. So if I have to find a distance between, suppose there's years of experience is 2, salary is somewhere around 50,000 rupees or anything. What is going to be the distance between 2 and 50K? Very big, right? Very big. So all you need to know is that you have to bring down both of them into same scale. That's why standardization and normalization becomes very much important. You have to scale down on similar scale to perform distance calculation. Okay. Else what is going to happen? that the power of any column which is having very big value like 50k is going to diminish the power of other feature. Suppose 50 and 2 is very big. What is the distance between 55 and 2.5? Hardly any difference between 52 and 55 and 2.5, because this particular thing is diminished a lot, and this is like overly important over here. That's why this particular standardization or normalization becomes very much important, or shall I say scaling down. Okay, is it clear now? Any questions? All right, so why not just go back and discard, go back to our, yeah, so over here only try the same thing with the KNN. As of now, let's now try KNN. To use KNN, all you need to do is copy this, paste it on the chat window, paste it over here. I'm now bringing k nearest neighbor, and everything else is already there. So I'm just going to run it. Let's see what happened. Physical course for the following reason. Anything? I think it's not working as of now. Why so? Okay, it's working now. Never mind. Copy this thing, paste it over here. We can see the performance of training is 98%, testing is 94%. Means still now the winner is logistic regression so far. But let's see how exactly the confusion matrix looks like. If you look at the confusion matrix, we can see it was 70 earlier. Now it is 68. It is now having 3, 3 as the false positive and the false negative, which is not a good thing. Okay. If we look at the confusion matrix, or shall I say accuracy score, accuracy is down to 95%. F1 is at 93, which is like not as good as what we saw in the logistic regression part. So is everything clear to you right now, guys? So instead of the elbow method, can we do the grid search over here? Who all remember the grid search, which we have covered in like first or second class? Any guesses? Very good, Pragati. Hyperparameter tuning. So what if I do hyperparameter tuning so that I'm going to give k value multiple times, okay, and see which one is going to be the best k value, okay? So I'm going to just paste the whole code over here, and let's walk through what exactly is happening, okay? In this, I'm going to give k value between 1 to 21. Okay, it is going to be a very big type of model. Okay, and I'm going to see which particular is going to give me the best accuracy in the model prediction, or shall I say the least error. Error rate should be least. Okay, so this particular, if I run it, it is going to make multiple models. So it is going to take some time. The star is going to stay. Okay, it worked very quickly. Over here, we can see the accuracy of my model is coming somewhere over here. And through this, I can see somewhere around 7 number of k nearest neighbor is giving me the highest accuracy. So I can safely use the k value of 7. And through that, I'm able to achieve 97% accuracy in the cross validation. Okay. So why not just go back above, change this to 7. Over here, it was 3. Let's just change it to 7. Over here, run this pipeline, run this again, run this again. and run this again. Still, I can see that hardly any changes are coming, but then it's fine. The model is not performing as good as logistic regression, which is okay. So what exactly grid search does is that it is going to try all the permutation and combination. Okay. Over here, what we can see is, first of all, this is going to be my grid search parameter. I'm giving this particular np.a range. Okay. So what is going to happen? K value is going to be from 1, then 2, 3, 4, 5, 6 till 21. Okay. I'm going to train my model over here with this particular thing using the grid search. And I'm going to give a scoring as accuracy, like whichever number of K value gives the highest accuracy, give me that particular K value. Okay. After this, it is going to run this particular model multiple times. To be specific, 21 models are going to be run. Okay, it is going to note down each one of them's accuracy. Whichever has the highest accuracy is going to be the one which is going to be given to us. Okay. So this particular model is going to run multiple times on this particular test. And then what we are going to see that it is going to give us optimal number of K, which you can see is highlighted over here. That optimal number of neighbors is 7. The best cross validation accuracy is 97%. And if we try to show it in the pictorial view, we can see as soon as we have one nearest neighbor, the accuracy was 94. When we reached to 2, it became 94.7. Then as soon as we hit 3, it was very good at 96%. It is going to increase till 7. Then it started decreasing. Okay. Because more the neighbors we are looking at, more noise is going to be get collected and more the decision is going to get hindered. Okay. That's why hyperparameter tuning is helping us to find the optimal number of K. So you can go ahead and say either you go for the elbow method or the hyperparameter tuning. Both of them are going to work for you. Is it clear now? All right. So let's take one more algorithm before we go for a break, guys. Okay. And this algorithm is very, very important because this is the most used algorithm, not this one particularly, but the extension of this particular algorithm is going to be the uh, very important part. Okay. This algorithm is called a decision tree. Okay. We have seen decision tree, or shall I say this particular decision making in our day-to-day life. Okay. Suppose you are a student. Okay. And you have a decision to make, and this decision starts from over here. Okay. And the first question which you have is, uh, let me just type it over here, make a box over here. The question is it going to rain tomorrow? Okay. And the answer can be easily two things. Either it's going to be yes or either it is going to be no. So if the answer is yes, you have a different decision to make. If the answer is no, it's different. So is it going to rain tomorrow? If the answer is no, my decision is going to be uh, I'm going to play out. Okay. If the answer is yes, it is going to rain tomorrow, the decision can be I am going to do the chores. Okay. So what exactly is happening? This is how a decision looks like. Okay. Uh, we can also extend this particular thing even more. Okay. Uh, Instead of yes, or shall I say, instead of doing chores, I can also add in, are my chores done or not? If yes, then I can just sleep. If no, I can do the chores. So this is how a decision tree looks like. There's a start point, or shall I say the root node. Okay. Then we have the decision node. Okay. And then finally we have the leaf node. So these are all the part of a decision tree. So far, I hope the very simple definition is clear to you now. Okay. How exactly can we use this particular thing in data science is what makes it very much special. Okay. So before knowing that, I have to open few things. Just a second. So to understand what exactly makes a decision tree classifier, we call it as decision tree classifier. How exactly decision tree classifier works depends on majorly two parts. Okay, those two parts are like this. First of all, it is known as entropy and Gini impurity. Or shall I just say one thing, which is impurity. And second is information gain. Now, guys, please have very much good focus over here. This is a very important part. Okay. So entropy, or shall I say impurity, is divided into two parts, or shall I say is of two types. Okay. One is called as Gini and one is called as entropy. Okay. Both of them do the same thing, but one's algorithm is simpler and one's algorithm is much more complex. Simpler one is used when the data is very big and complex one can be used when the data is small. Simple thing. Okay. So how exactly decisions are made? We already know. These are this, it looks something like this. It is going to look something like this, something like this. Okay. As of now, this is how it looks like and how exactly it is done. We are going to talk about it. Suppose there is one question that age less than 15. Is the particular student's age less than 15? No or yes? If no, then we can say that they are not in school, they are in college. Suppose something like this. So they are in college. If yes, then they are in school. Okay. Something like this. So what exactly is happening? We have a certain type of division which is happening, and then we have the final solutions. These are the leaf nodes. These are also called as the root node or the decision nodes. Now, we can divide this further down with a simple example. Let me just try to show it to you over here. Suppose this is the data which we have. Copy, paste it over here. In this data, just look at all the information which is given to us. If the day is sunny, the temperature is hot, and the humidity is high, wind is very weak, I can't play tennis. Can you go out and play tennis? No. If the day is sunny, it's hot, it's high and strong, you cannot play. If it's overcast, it's hot, the humidity is high, wind speed is weak, and play tennis, you can say yes. So there are a lot of things which are given to us, but why not try to just break it down first? Okay. First of all, let's keep this particular, only focus on this particular window. Okay. And we'll say outlook. Okay. How many outlooks are there? There's sunny, there's overcast, there's rain. That's it. So there are three possible outcomes which are there: sunny, overcast, and rain. Okay. First of all, we have to see how many sunnies are there. Okay. So there's 1, 2, 3, 4, 5, and okay, 5. Total of 5. In this, how many are no and how many of yes? Once you do this, there are 2 yes and 3 no in the sunny part. Okay. Similarly for rain, there are 3 yes and 2 no. Okay. In outcast, or sorry, overcast, there are 4 yes and 0 no. Okay. So there's something which is very unique. Over here, there are 0 no means this is a pure split. What is pure split? When there's only one category present, the other category is not present. Over here, we can see that there are 4 yes and 0 no, means this is a pure split. Okay. Over here, there is certain impurity. Half of them are yes, half of them are no. Again, over here, half of them are yes, half of them are no. So is this clear to you now? We know this is nothing but the leaf node. This is a pure split. Is these two topics clear to you now? And also the term which we have already discussed or mentioned, which is called as purity. Okay. Purity is nothing but how is the mixture of yes and no. Okay. What is the mixture of yes and no? If there's only one category which is present, then it becomes a pure purity. If there is like mixture like 2 3 yes 2 3 no, then it becomes impure. Okay. How do you find purity? Is through the algorithm which is called as impurity algorithm. And impurity algorithm is divided into Gini and entropy. Okay. First of all, this is what you have to find. Okay. Any questions so far? Just giving you a very small intuition. Just going to zoom out and let give you a time so that you can look at it easily. Any questions, guys? So I will take that there is no questions since there are no comments on the chat window. As of now, all we have understood is like, suppose there is a certain type of data set. Okay. And in data set, I am trying to find different categories. The outlook column over here has 3 categories: sunny, overcast, and rain. And how many yes and how many no's are there in all of these individual categories? In the overcast, we can see there are 4 yes and 0 no. This means this is a pure split. There is no impurity present. Okay. In other categories, there are certain number of yes and certain number of no, means there's a mixture. Okay. So we know how exactly to find the impurity through this particular algorithm. We are going to talk more about it, but this is the first question: how to find impurity. Second is what feature you need to split on. This particular question is answered through information gain. Okay. How much information are we getting from different categories? Okay. So information gain is a very important feature. Information gain value is between 0 and 1. Okay. Wherever the information gain is closer to 1, we are going to use that feature as the topmost feature. Okay. This is how you have to understand it. As of now, this is the only thing which you have to know. Okay. First of all, what is impurity? Mixture of yes and no. Second is which feature to keep on the top. It comes from the information gain. Whichever columns information gain is highest is going to go on the topmost. Okay. That's it. Okay. Any questions so far? Theoretically. I'll take silence as no questions and move on to dig more deeper into Gini and entropy. Guys, please be proactive on chat window. Else I will just keep on moving forward and forward. Okay. So let's talk more about the impurity part again. Impurity. And I told you about one is good for big data set and one is good for small data set. So one is first of all is called as entropy. Other is called as Gini. Let's see at both of the formulas and you have to decide which is going to be a better a quick formula and which is a big formula. It is denoted by h of s, okay, minus p plus log of minus p, okay, minus p minus log of, this is based on 2 p minus. This is the formula for entropy, and for Gini, this particular formula becomes like 1, or shall I say Gi equals to 1 minus summation of p whole square. These are the two different formulas, guys. Okay. Which one do you think is a quick formula and which one do you think is a big formula? Any guesses? So if you want to guess it, this particular formula includes logarithmic functions, then it becomes slower formula. It is much more accurate, but since it uses logarithmic function, if you have a very big data, it becomes a lot more troublesome. So in the big form, shall I say big data set, Gini is a very good function, which is used for the impurity calculation. Okay, that's it. Now you can also, this becomes a bit advanced, but the range of entropy is from 0 till 1. Okay. The graph looks something like this for entropy. And for Gini, it looks something like this. Okay. So the highest peak of entropy is at 1. Okay. The highest peak of Gini is at 0.5. Okay. Now, why are we looking at this? You don't have to understand it. It's a very advanced, shall I say, um, mathematics. For now, all you need to understand is how exactly both of the formula looks like. Which formula do you think is much more simpler? This is what a newcomer of data scientist should know. And what is the range? Okay, so entropy range is still 1. Okay, and Gini range is from 0 to 0.25. Over here we say HS. Okay, and it goes from 0 till 1. And over here we say P of positive or P of negative. Okay, and this is 0.5. This is all that you need to know. Okay. Any questions, guys? Please be active on chat window. We are going to go for break just right after completing this theory. So Devika, the range of entropy formula, this particular formula is from 0 till 1. Okay. And the range of it is from 0 till 0.5. Okay. So the easiest way to understand is the output of Gini is from minimum of 0 and maximum it is going to go till 0.5. Output of entropy is minimum 0 and maximum 1. Uh, it doesn't matter for you right now. All you need to understand is the formula difference. Entropy uses logarithmic function, which makes it slow if we are talking about very large data set. Gini uses a simple square function, which becomes much more quicker as compared to entropy in terms of large data set. So if somebody says, okay, you have a decision tree algorithm which you need to use, the data is of 1 million rows. So you will say, since the data size is very big, it's easier to use Gini impurity, shall I say, function, because it is going to be quicker in calculation. Okay. You're welcome. Now, to end this particular topic, and let's talk about information gain. So guys, you can see in this particular example, there were 3 columns: outlook, temperature, or sorry, 4 columns: humidity and wind. The question is, which one should I make as the root node? How will I decide between these 4? which one is the first thing which should be compared? The easiest answer comes out from the information gain. Kithagni, we are going to see why. We come to Outlook or some other column. The answer is going to come from information gain. So wherever information gain is highest is going to be the root node. Not only the root node, this is not the correct way of saying it, but after root node also, suppose I say that over here the root node becomes Outlook. After Outlook, which column should be there? Is it temperature, humidity, or wind? Maybe humidity is going to take the second place. After this, shall I take for temperature or wind? Then maybe it is going to be wind. How am I even deciding this thing? That is going to come from information gain. Which one is going to come first afterwards? Okay. So how exactly this is done? There is one formula which I can show you. I think it's a bit beyond. Let me see if it is going given to you as well. Okay, yeah, we do have it. So information gain formula looks something like this. Let me just take a snippet. So this is the formula, guys. You can take your time and just read through it. But suppose for all the four columns, the information gains look something like this. For Outlook, it came out to be 0.7. For temperature, it came out to be 0.6. For wind, 0.3. And for what else was there? Humidity. Humidity, it came out as 0.65. Which one do you think is going to be the root node? Any guesses? The answer is very much evident. Outlook is going to be the root node. Okay. After this, information gain is again calculated between these three. Of these three, whoever is going to be the highest information gain is going to be the next node. Afterwards, it is going to be again covered into the these two part. So this is how this whole calculation is done. Okay. So the very good interview question which comes from this particular part is two things. First of all, what are the different types of impurities in decision tree? You can say Gini and entropy. Where do you use which one? You will say entropy is used for lower, smaller data set because it uses logarithmic calculations, which become a bit slower. Gini can be used for the higher number of data sets, or shall I say higher number of rows in a data set. Second, anybody say, how do you decide that which column is going to be on the topmost part? The easiest answer is information gain. Okay. Whichever column's information gain value is highest, it is going to take up the topmost part. And this particular practice is done again and again till the time all of them are ordered fashionably. Okay. That's it. This is how your decision tree works. Any questions? Now, there's one more good thing that you should know is what we call as pruning. Okay. So, you know that you might be having a lot of pots at your home. So, pruning is something which you do with your flowers, or shall I say your plants. So, if my decision tree looks something like this and it becomes very much deep, okay, at certain point, you know that uh, this is not a good thing. It can make overfitting of the data. How I can make this proper fit, or shall I say it can make less overfitting? I can just cut certain number of branches out of it. Okay, that is called as pruning. Pruning can be calculated by how much maximum depth I want to go. Okay, maybe after 2 or 3 layers I want to stop. Maybe I can, so this is depth. I can control depth. I can control impurity. Okay, how much impurity is good for me? There are lot and lots of things which you can work around with. Let me show you. If you just Google decision tree parameters. Okay. And just open up the Scikit-learn blog, you will see there are a lot of parameters which are there. Okay. You can play with maximum depth of a tree, minimum sample split, minimum sample leaf, maximum features, minimum weight fraction. A lot of things are there. Can anybody give me the answer? I have so much parameters. What is the best way that I can find the best number for each parameter? The answer is hyperparameter tuning. Okay. So before ending this particular and going on a break, let's try and copy this, paste it over here and try decision tree. I have the decision tree pipeline ready with me. Okay. And if I hit enter, I can see the training accuracy is 1. Testing accuracy is 94. Okay. So what I'll do, I will now try the cross validation technique. Okay. Going to paste it over here and see if I can improve such score. The cross validation score looks something like this, which is good. Okay. And you can see with cross validation, the mean cross validation has now come down to 91%. Overfitting was eliminated using the cross validation. Okay. Next I can do is try to show you the confusion matrix, or maybe even better, I can show you the classification report. If you try to look at it, 95% accuracy with 93% F1 score. So I can see still the logistic regression model is the winner. Okay. Now let's see if we have anything in hyperparameter tuning. Let's see. No, we don't, but we do have pruning. We can try pruning. I'm going to paste it over here. So let's try pruning. In this, what I'm going to do is, first of all, I'm going to make a pruning alpha, CCC alpha. Let's see what exactly this talks about over here. CCP alpha. What exactly we are talking about? This is a documentation which you can always follow to, guys. Okay. All you need to go is Scikit-learn's documentation website, and it is going to give you what exactly each parameter means. So this is a non-negative float complexity parameter used for minimal cost complexity of pruning. So this is going to help us do the pruning. So 0 means no in this, if you go down by having it at 0, you're not doing any pruning. If you're going to increase that number, the pruning exercise is going to become more and more penalizing. Okay. So I can give it 0.01, 0.1, 0.2, anything. The bigger the number I'm going to give, the more harsher the pruning is going to be. That is going to decide how my model performance is going to look like. So if I hit enter, it is going to show that from 1 or 100% training accuracy, it is now crossed down to 98%. From 95%, it has slightly increased to 95.6%. So this is how I'm playing with the different parameters so that my model can perform much better. Okay. With this, I can just see the final post pruning accuracy score. You will see it has now increased to 96%. If I just look at over here, it was 95%. Now it has increased to 96%. So you can see you can play with much more algorithm and find the best fitting one, which is going to give you maximum result. Okay. And with this, we can also try cross validation, shall I say hyperparameter tuning. Okay. If you look at this particular code, guys, in this, I'm going to give all the parameters now: maximum depth, minimum split, maximum samples, maximum features, all the things. I'm saying these are all the features which you have. Try everything and give me the best parameters which can give me the best result. Okay. So far, I have only used the pruning parameter, but now let's try all the parameters which are there in the decision tree. Okay. With this, if I just hit enter, this particular code is going to run. See, it is going to see a lot of things. Over here, we can see maybe 20, 30 models or even more are created. Maybe 50, 60 models are there. It is like 4 into 3 into 3 into 3 into 3. So a very heavy amount of models are created. Hyperparameter tuning is very good when you have a very big server with you. Okay. And it's okay that you want to keep it busy for some time. See, it took a lot of time over here. Okay. After everything, the best accuracy is still 95.6%. And that shows that our model is not able to bypass that threshold. This is the best it was able to do. Okay. And what are the best parameters? These are the best parameters. If you keep pruning to 0, maximum depth to null, maximum features to log 2, and maximum sample leave as 1 and sample split as 2. On that scenario, cross validation becomes 94% and test validation becomes 95.6%. Okay. So with this, we can go on a break, guys. Okay. We have covered most of the algorithms and only one last algorithm is going to left, and then we can call today's session. Okay. So let's go for 20 minutes break. So we know all the algorithms, how they function now theoretically. Practically, it's just calling up those functions as of now. Okay. There are certain things which you can play with, which is called as your hyperparameter tuning. Majority of hyperparameters come from the decision tree, because decision tree have a lot of things which you can play with. Okay. In k-nearest neighbor, you only play with the elbow method, which is number of clusters, or shall I say number of neighbors. In naive Bayes, you are just using the simple naive Bayes theorem. Okay. Now there's one pretty complex type of algorithm which is now left for this today's session, and it is called as, let me just try to bring it over here, support vector machines. It is a very highly sophisticated type of algorithm which is present, and the least information which I will be going to give you about it because it is very mathematically intensive thing. The thing which I can tell you is what we are going to say, that a very basic part of how SVM works. To understand it, first of all, we can talk about how a simple data looks like. Suppose there's a certain type of yellow dots, certain type of blue dots. Okay. And these are the two classes which are there. And you have to make a classification division, which can give you a proper classification. Anything above that particular line is going to be categorized into yellow. Anything below that line is going to categorize as blue. Okay. So what's the easiest way of doing it? Simply like giving a straight line, right? That's good. And in SVM, this straight line is called as, uh, you can call it as maximum margin. Okay. Now this particular thing is as similar as what we have covered in our other type of algorithms. We are trying to create a kind of a plane through which we are able to distinguish between the two categories. In support vector, there is one more category which comes up, which is a dotted line. Okay. Now this dotted line is nothing but the support margin. Okay. Now we can play with how big or how small this margin can be. Okay. That's how hyperparameter tuning is going to work like. Okay. If this particular thing is called denoted as C, if we call C as 0, then it is going to work similar to what we have learned so far. If we increase this value, this margin is going to increase. Okay. Now why we use it, how we use it, we are going to talk about it a bit more. But what is the advantage of such kind of algorithm? Let's talk about this first. Guys, this type of division is very much simple. We know that there is a cluster of yellow dots which are over here and a cluster of blue dots which are over here, and we are talking in two-dimensional data. So it's easy that you can create a certain type of line which can distinguish between these two type of data sets, or shall I say different categories. But what if I ask you, if my data is, instead of being two-dimensional, suppose my data is only one-dimensional, okay? And the data looks something like this. We have yellow dot, then we have some pink dot, then we again have some yellow dots. How can you make a distinguishing line which can help me divide yellow and pink? If you say that, sir, how about we create a certain type of division over here? Anything on the left side is going to be yellow, anything on this side is going to be pink. I will say that this division is good, but over here these are going to be misclassified. This is a wrong division. But you can't create a certain plane over here. What if there is a certain type of algorithm which can convert the one-dimensional data into two-dimensional data, and it's going to look something like this. This time the data looks something like this. Okay. Now what do you think is going to be the way? The easiest answer over here is I'm going to now create a straight line. Above this, everything is pink. Below this, everything is yellow. What I did was converting the one-dimensional data into a higher dimension, or shall I say two-dimensional data. This conversion happened. Okay. This is the power of support vector machines. Similarly, suppose there's a two-dimensional data. Okay. And this data looks something like this. Okay. In this, we have certain yellow dots, and then we have some red dots. Now, again, my question is, how can you make a line which can convert these things? Okay, which can just amplify and say that, okay, beyond this is red and above this is yellow. This is a two-dimensional data. For this, I'm going to convert it into a three-dimensional data. It is going to look something like this. Of course, I can't just depict it over here, but it is going to look something like this. We have circles over here, and then we have a higher circles over here. Okay. And in this, there's going to be a plane. Okay. The plane is going to look something like this. Okay. Anything above this plane is going to be red. Anything below that plane is going to be yellow. So two-dimension converted into three-dimension is going to give us the idea of how to divide the data set. Now just think of how much mathematical intensive it is going to be that you are converting this data into a higher dimension. Okay. Now the problem with this thing is, now this is a solution, but the problem is this particular type of algorithm is very good when your data is highly complex, yet your data is very small, because the algorithm which goes behind this particular calculation is very high. If you use SVM for bigger data sets, or shall I say bigger features, it is going to become very slow and counterproductive. Okay, so support vector machines is very good when you have a very complex data yet very small data. At that time, this particular algorithm works superbly. Okay, to apply this, this is the intuition, guys. Okay, majoritarily, you can say that. Let me just show you one more thing. Not over here. Let me try to pull this one. SVM works on this agenda. Paste it over here. These are the 2 to 3 parameters which are there. Okay. Mainly, what you are going to do is use this C value, which is the one parameter which is called as cost parameter, and the gamma value. These are the two parameters which are there. So what is the purpose of C? It controls the trade-off between the smooth decision boundary and the classification of the training points. Okay. So this is like how overfitted you want to make your model to be. Lower the C value, lower is going to be its impact, means higher the C value, higher regularization, means higher penalizing and lower overtraining. Lower C value is higher thing, means overtraining can be remedied. Okay, so this, so if I say high value of C, this may lead to overfitting, and low value of C, it is going to be a very good fitting of the model. Just like I told you, if I give it a high C value, it is going to impact this particular support vector boundary. Okay, with this, we also going to talk about the gamma parameter. This determines the influence of the single training example and how far it reaches, means how much this particular data point is going to influence this particular data point, this particular data point, this particular data point, all the data points. Okay, this is very good when your data set is very small. So if you increase the gamma value, the influence become very much stable. One point is going to help you understand a lot of things. Uh, we are going to talk more about it in our tomorrow's class also, because tomorrow we are going to talk about highly imbalanced data and what exactly it is and how to remedify it and how SVM is actually useful around it. Okay, so this is a very good theory part which you can work on and how exactly it is this is used. That's it. This is what you have to know about the support vector machines. The second thing which you need to know is how exactly the different parameters work together. Okay, so let me just try to find. There is one thing how exactly these work. Suppose this is a single line, this is a plane. There is a term which is called as kernels. Okay, there are different kernels which are there for different problems. Suppose my problem is a linear separation problem. If I know my problem is a linear separation problem, I'm going to use a linear kernel. Okay, so kernel is nothing but a type of calculation which is happening to create a separation. Now, if we have a non-linear separation, over here there are different kernels, but the most prominent and the most famous one are polynomial kernel, and the most famous one is the RDF kernel. Now, guys, uh, this particular course doesn't ask you of the different kernels which are there, or shall I say, this even doesn't want you to know the kernels. But I am coming from a data science background in which uh, I know what are the different techniques or questions which are definitely asked by the shall I say, the interviewers. Okay, so this becomes a very important thing. The most important kernel becomes the RBF kernel because it is much more nuanced, or shall I say, very much used type of kernel. So that's it. This is all you need to know about the SVM, uh, shall I say, algorithm. To replicate this on your system, what we can do is now we can just go back and try to indulge how exactly we can use the SVM. I'm going to copy it, paste it on the chat window, okay, and paste it over here. Again, the pipeline contains the SVM, probability to random state. Okay. And all I am doing is the same repeated work, guys. If you just look at all the algorithms, this is the part which is changing all the time. Just like I told you, you are a data scientist. You should know the theory behind it. And the only easiest part is how to apply that particular function. How do you call that particular function? That's it. Okay. To grow from over here, you are going to go much more deeper into the machine learning part. How can you improve this algorithm in a different sense? Can you change the mathematics behind it? Answer is yes and no. Okay. And that's a question for future. But as of now, how do you call different algorithms and how do you perform the checks and which particular algorithm is the best performing throughout the whole scenario? Okay. So once I do this, I can see 98% accuracy in testing part, guys. Okay, this is the best performing model so far. Okay, so let's see how exactly the confusion matrix, or shall I say the accuracy score looks like. Okay, amazing. Accuracy is coming out 98%. and F1 score is around 98%. So this is by far the best algorithm. If we compare this with logistic regression, k nearest neighbor, naive Bayes, decision tree, and finally this is SVM. Okay, there's one more algorithm which you can use as random forest, but for now this is what we have covered so far. Okay, so with this, what I can show you is, let's see, different techniques which we have covered so far. Let me just scroll up to our logistic regression. So as a data scientist, what we have done so far, we have tried multiple algorithms to see which one is the best performing algorithm, right? So first of all, if we just look at the logistic regression, if we scroll down, it's 97% accuracy, 96% F1 score. Good. This was good. Let's go down. Then we went to naive Bayes. The accuracy fell down to 96% and 95%. Then we went to the KN nearest neighbor. It went to 95 and 93, even further down. Okay, no problem. Then we went to decision tree. It increased to 95 and 93. Finally, we came up with SVM. Oh, before that, we even tried the hyperparameter tuning in decision tree. Okay, that increased to 96 and 94. Okay, finally, we tried the most complex algorithm, which is SVM, and it increased to 98 and 98, which makes it the best performing model. And we can say this is a winner model, and we can go ahead to productionalizing this into the production environment. Okay, and that's it. We can, I think, close this topic, or shall I say this class on this particular topic. And we have very good time for any types of doubts and queries. So I'm going to open up the window for any types of doubts and queries. Okay, please use the chat window. And if you want to come unmute, please mention in the chat window. I am going to allow you to unmute you also. Yes, of course. So kernels are nothing but a type of algorithms which can be used for different type of scenarios. Okay. First of all, you should know, is there a linear relationship between the independent and the dependent features? Okay. If there is a linear relationship, linear kernel might be working for you. Or shall I say SVR, support vector regression. If you are trying a regression equation and if you want to use support vector, you can go for a kernel which is linear kernel. Okay, but if you have a non-linear type of relationship, and in classification problems, there is 99% of time the non-linear relationship is used. You can use polynomial kernel or RBF kernel. What is kernel? Kernel is nothing but the type of calculation algorithm which is being used on behind the data. Just like in the decision tree, we saw what is the difference between Gini and entropy. You can see this is a different algorithm, this is a different algorithm, right? Similarly, kernels are working in a similar fashion. There is a mathematics which is going on behind. Okay, you can use different algorithms to see which one is giving you the best result. Okay, of course, Priti, I can definitely explain you the impurity. So guys, what is impurity? First of all, to understand that, let's look at a certain example. Let me see over here. Okay, if you look at this particular example, a sunny environment has multiple no's and multiple yes. If you look closely, there are going to be 2 yes and 3 no's in the sunny environment. Overcast has only yes. Okay, so overcast over here, the answer is yes. Overcast over here, the answer is yes. Overcast here, yes, yes. So we can say 4 yes and 0 no. So first of all, any type of leaf node, this is a leaf, okay, where there is only one category present becomes a pure split. Means this is a pure form. But any kind of a leaf node which has the mixture, it has certain amount of yes and certain amount of no, becomes an impurity. Okay. This impurity can be calculated. Okay. We are seeing it over here through pictorial view, but how exactly the computer understand? They understand via impurity formulas. Okay. You can do one thing. you can just go on and try to find the impurity complex over here. If you try to impute it for outcast, oh sorry, yeah, outcast, the impurity is going to come out to be 0 because there are 4 yes and 0 no. But if you do the same thing for the sunny day, it is going to come around somewhere 0.4 or 0.7, something like this. Okay. So this is how the impurity works. The more the impurity, the more the opportunity to split it even further. Okay. Just go back above, guys. Okay. Overcast. I know the answer is yes. I don't have to go on and look at other features, temperature, humidity, wind. I don't have to look at it. But in sunny, I can see that there are still some impurity left because there are yes and no's. I might have to go to a certain different feature. Now, which feature should I go to, guys?
Can you briefly explain what exactly does a pipeline do? I mean, internally.
Mhm. So, just like I told you, pipeline is nothing but a type of sequential type of coding which can be like integrated in a very neat fashion. That's it. Uh, it doesn't really do much, but it beautify your code in a way. So once you become a data scientist and you come across a very big code, how can you make improvements without changing anything? So what pipeline does is like you can add steps sequentially. So what exactly do you do once you get the data apart from EDA, right? So apart from your exploratory data analysis, you might be doing some of the missing value treatments, some of the outlier treatments, some treatments which might clean up your date variable. Okay. So these are like the very pretty basic type of, shall I say, practice which a data analyst or a data scientist does. Okay. Post this, you go for something like correlation checks and then only picking the very important features. Wherever the correlation high, you can drop either one of them. Okay. Uh, Finally, what you do is like training your model. So all of this can be easily like made in a clean fashion, and you can call this pipeline function. And it is going to do sequentially, whichever is coming first, it is going to run that formula first, and so on and so forth. So that's pipeline for you.
Okay, so this is almost like, uh, I mean, I can visualize it like a
Mhm.
series of funks.
Yeah, series of functions which are working sequentially. So
Okay.
sequence is very much important.
Yeah. Okay.
Mhm.
So it's okay. I mean, basically, I work on .NET, so I'm thinking more on the like basically an action and funk pair.
Ah, okay. No, no, no. So you don't have to like make it so complex. It's just a sequential following of the code. That's it.
Okay.
Mhm.
Okay. Got it.
Good
Thank you.
question. Thank you, Shusha. So I'll welcome any more type of queries and questions. Please feel free to unmute or use the chat window. So guys, so far, till the time any question comes up, let's talk about what we have covered so far. Okay. So it's been, sir, when will to use which algo? So Priyanshu, first of all, this question is very much open-ended. So let's try to understand which algo you're talking about specifically. Um, okay, let's start with Priyanshu's question. Okay. So as of now, you might have learned around 3 to 4 algorithms in regression and 4 to 5 in classification. Okay. So what exactly is a data scientist's workflow? First of all, you have to uh, understand the business problem. Okay. So this is beyond coding. Okay. So coding is just a very small spec which is going to help you in your day-to-day exercise as a data scientist or a data analyst, anything. Okay. So understanding the business problem. What am I trying to solve over here? So the as of now, whatever you have learned is very much small window. So let's try to just utilize that part only. So just like I told you when we started with the supervised machine learning, that supervised machine learning is divided into two types. Either you are trying to predict something which is of continuous in nature, or you're trying to predict something which is discrete in nature. So something which is continuous and something which is discrete. Okay. So that's something which we are trying to think about. So in continuous, the examples can be numerous, like maybe you're trying to predict tomorrow's rainfall, how much rainfall it is going to be there, tomorrow's stock price, okay, maybe gold price, or maybe someone's salary, or house price. Okay, these all type of shall I say business problems uh, are coming from the bucket which is called as regression. Okay, so all of this comes from the bucket which is called as a regression type of supervised machine learning. Okay, over here now that the regression part is clear, that okay, I want to talk about regression, we have so far learned a lot of shall I say algorithms in regression. First of all, guys, yesterday's homework was what are the assumptions of linear regression. Okay, so the first agenda, once you have accomplished that, okay, my problem is a regression problem, the first thing you have to do is see that am I able to like clear all the assumptions of linear regression. If all the assumptions of linear regression are complete, or shall I say true, then you can go ahead and use the linear regression equations. Okay. If they are not, that means there's not a linear relationship, but you are going to then go for non-linear regression equations. In linear regression equations, we have talked about multiple, like your normal linear regression, your L1, L2, elastic net. Okay, these can be used. In non-linear, we have talked about so far polynomial regression. Okay, so polynomial regression. Also, yes, polynomial. After polynomial regression, there is one more type of, shall I say, algorithm which you can use. This might be a news for you, but decision trees can also be used for regression problems. Even SVR, support vector regression algorithms, can all be used. Um, there might be few more algorithms, but as of now, this is the workflow on how to choose what kind of algorithm you have to choose. Okay, so this is talking about continuous. Let's talk about discrete. What comes in discrete? Whether a student is going to pass or fail. Okay, whether a certain patient is suffering from COVID positive or negative. Okay, whether something is true or false. Uh, is something a fraud or not fraud? Okay. Uh, so guys, as of now, I'm only talking about binary classification. We are going to talk more about multiple classification, but as of now, binary classification. These all comes under the category which is called as classification problems. Okay. In classification, we have again learned a lot of algorithms like naive or logistic regression. Why are you forgetting about the most important one, logistic regression? Then we talked about naive Bayes. Okay. Then we talked about KNN. Then we talked about SVM. Then we talked about decision tree. So we have covered only these, shall I say, algorithms so far. Now, each algorithm has certain pros and cons with them. First of all, logistic regression is a very good algorithm. The only problem is that the stronger the linear relationship, stronger the logistic regression's output is. But if it's not having a linear relationship, it might not give you that good of answer. That's the one thing. Naive Bayes works good enough when the data is having lower dimensions, not many features. Uh, there are certain more, shall I say, drawbacks to this algorithm, but that is something you are going to learn in your own journey. As of now, just go ahead and use it. Okay. KNN is a distance algorithm. The only downside is you have to standardize all the features throughout. If the standardization is not happening, normalization is not happening, means in short, scaling is not happening, the distance algorithms becomes very much fruitless. Okay. SVM, SVM is very good when you have a small and complex data. Okay, if the data becomes very large, SVM becomes very slow and might yield to not so good results. Finally, decision tree. Decision tree is a very good algorithm. It is like very versatile, not decision tree itself, but the shall I say wrappers, or shall I say the better formulas from decision tree which are derived. We are going to talk about one of them today. Okay, those are used a lot. Okay, so this is how a data scientist think about any type of algorithm by thinking what is the business problem. Okay, all right. So I think I have already covered what we have covered so far in this particular block, and overall what we have learned in machine learning overall. Okay, so why not let's talk about what we are going to cover today. Okay, so topics for today. So today I want to like show you something which is there are one or two points which are a bit beyond your course, like which are not mandatory, but I'm going to show you the working of SVM. Okay, it is a very good mathematical based intuition of how exactly SVM works. Okay, uh, till now we have talked about decision tree, but what if multiple decision tree works together? It becomes random forest. So we are going to talk about what is random forest. Okay. After this, random forest brings us to a lot more type of problems which it can solve. And the most important one is handling imbalanced data, or shall I say highly imbalanced data. In highly imbalanced data, how do you, shall I say, clean your data, or how do you do the feature engineering? Okay. So Priyanshu is asking, class, sir, in classification task, can I use all the algo to test which works better rather than selecting which algo which works best? Yes, of course, you can go ahead and use all of them. Okay, there is no cap in like which algorithm to choose and which not to choose. Okay, uh, but if your data becomes very, very large and your server is getting hindered, then you might first of all go for less complex algorithms. Just like logistic regression can be used, it's not that much mathematical intensive. Go for a decision tree or random forest. We are going to talk more about it. You can skip SVM because SVM becomes much more overhead problems. Okay, so at that time, you can choose like which algorithm is less computing intensive. That's it. Okay. So let's see what all we are going to talk about. Basically, these three topics, guys. Okay. This topic is very big and it will require you to think as a data scientist. Okay. I can just teach you like simple topic. Okay, this is how you do it. But it will be good if you are going to engage on how exactly can we do certain type of equations. Okay. Okay. So why not let's start with looking at how exactly SVM works. Especially there's one algorithm which I wanted to show you. Before starting with the working of SVM, let's first of all write working of SVM. We talked about a specific type of things which are there in SVM. The term is called as kernels. Okay, so we talked about very famous kernels like linear kernel, polynomial, uh, RBF, and there's one more which is called a sigmoid. And I think there are multiple, but these four are the most common used. On that as well, RBF becomes the most commonly used among all these four kernels. So RBF calculation becomes a bit complex. So it's easy for me to show you how exactly polynomial kernel is working like. So to understand polynomial kernel, let's talk about polynomial regression first. Okay. In linear regression, we saw that if there's a distribution of features and it looks something like this, okay? So what happens if I try to go for simple linear regression? It is going to try and make a straight line, okay? Because that's how the linear relationship is able to make y is equal to mx plus c. This is the best it can do. But what polynomial allows you is to try higher degree of coefficients. And the higher degree can be x square, x cube, x4, and how exactly those relationship works like. So the higher the degree value, the steeper the relationship becomes. Okay, and how exactly can we show it? So if it is x square, it might look something like this. If it is x cube, it might look something like this. X4, might go even steeper, x5 even more steeper. So it's like a curve which is getting steeper and steeper as the higher power is introduced. So what happens, we try to make this a polynomial equation. Okay, and how it's done, we are going to like see a small intuition, and after that the type of problem which we are going to solve becomes like y is equal to m1x, maybe if the highest power we are giving is q, so m1x cube plus m2x square plus m3x plus c. So then we are going to try and create this kind of scenario, and the final output which comes might be a very good fitting line according to this particular equation. So the hidden agenda over here is, if there is a non-linear type of relationship, then we try to add some of the non-linear type of algorithms over here. Okay, so I have a very good, shall I say, data set. Uh, Now what I can do is either I can just walk you through it. Okay, that will be much more quicker. Okay, so I'm going to just walk you through it. Let me just bring this whole slide over here. And if there are any questions, I'm going to stay as slow as possible. Okay, if there are any questions, you can just stop me. Or if you just want to read through the data and the code to understand, just let me know. First of all, I hope there are few of the very basic functions of NumPy, Pandas, which are very much clear to you from your previous modules. Uh, Anybody know what is line space in NumPy? Any guesses? Equally spaced sequence of numbers. Very good, Shasha. So that is the correct answer, guys. So what exactly line space, or the full form is linear space, linearly spaced, generates number with equal spacing. Very good, Rakshita. What it does, you provided the starting point, you provided the end point, and you provide how many equally spaced numbers you want in between the starting and the ending point. It is going to create that. So what I'm trying to do over here is to create a synthetic data. So over here, what I'm trying to do, I'm creating a synthetic data for the independent feature, first of all. And then there's a dependent feature which I'm creating using the independent feature. Okay. So you don't have to learn why am I doing this. It is just a random data set which I'm creating, or shall I say a synthetic data which has been created. Okay. And so this is how synthetic data has been created. And if you look at the synthetic dependent feature, it looks something like this. Okay. And that's it. All you need to know about the data. Okay. So what I'm going to do now is to plot the data and show you how exactly this looks like. Okay, my data looks something like this. So remember the intuition of SVM. What SVM does is what a normal algorithm is not able to do. Okay, just look at this particular data. If I'm just going to take it out and paste it over here into the blackboard, if you take it over here, paste it over here, it is going to look exactly like what we created in our yesterday's class. If my data looks something like this, if there are a few points which are in circle, and there's a concentric circle of different class. So this is a class A, this is class B. Is there any way possible that I can create a classifier plane, okay, which can distinguish between these two type of data set? Okay, so this is the exact type of data which we are looking at. We have two different data sets, okay, and there are very lot of number of data points which are there. So how can I do it? With the help of SVM. What SVM does is it is going to make it plus one dimension. So this is a 2D graph. We have X and Y. Why not add a Z axis and we take it to a hyperplane, a new plane, and then we are going to create a certain distinguishing boundary. Let's try to see how exactly this can be done. Okay. So what exactly happens is, let me just scroll down, and this is how my X1, X2, and Y are looking like. Okay. Very much simple. Uh, Let me just go back above. And this is how the data set is created. And all this is a synthetic data. And I can see that there are two features and there's one independent feature which has been there. Okay. Now what I'm going to do is I'm going to first of all split the data into training and test set simply. I'm doing nothing else. I have split my data into train and test. I can see how my training data looks like. Now let's talk about polynomial kernel, guys. Okay, this is a very much simple equation which can be there. So yesterday, one of my students over here asked, "Sir, what exactly is kernel?" Kernel is nothing but how are you transforming your data using a certain formula. That's it. So it's like a feature transformation process. Okay. Polynomial kernel works on this particular formula. We can see there's x raised to the power t plus into y plus c raised to the power d. Okay, this is the formula. Again, we don't have to learn how exactly this. So this is nothing to do with Python kernel. No, Python kernels are very much different thing. Okay. In SVM, kernel means a certain type of calculation metric. Okay. So this particular formula, when applied to a certain type of dimensional data, the dimension might increase. How exactly can we do it? By mathematics, this particular script is going to show you. So what I'm going to do is, guys, first of all, each of the feature is being squared. Okay. So I have x1 and x2. Initially, if I just go back over here, my equation might look like this. Y is equal to m1 x1 plus m2 x2 plus c. Now what I'm going to do is, first of all, I'm going to square this one. So this is going to become x1 square. I'm going to square this one is becoming x2 square. Okay. First of all, these two things are done. Then I'm going to create one more feature, which is going to be nothing but x1 into x2. Okay. So it's like I am adding more complexity into my data. I'm adding one more dimension over here using a simple mathematical function. Okay. So if I just go back over here, x1 square, x2 square, x1, x2. This is nothing but a type of feature engineering which is happening right now. And this is my data is going to look like. I have 1, 2, 3, 4, 5 independent features now and one dependent features now. Just think of it, guys. Out of two, I was able to square, like I have increased the dimension of my data. Earlier there were only two features, now there are five features. Just think of it, if we have 10, 20 features, and if I just go with a kernel which looks something like this, SVM, it is going to exponentially increase the number of features. That's why it becomes like not a good type of algorithm when we are dealing with a very big type of data set. Okay, you can go ahead and try it, but it is just going to give you very big overhead and the calculation might slow down your system. But if you have access to a very high GPU server, you might use it. Okay, so this is how my independent dependent features are going to look like. Okay, and now I'm going to split the data into test and train. Okay, so that particular thing is done again. Okay, and my data looks something like this. Now what I'm going to do is, I have done the feature engineering part, guys. Okay, the main kernel application has been done. The kernel application was this, what which I showed you over here. This was the kernel application. Make x1 to x1 square, x2 to x2 square, and x1 x2. All I need to do is just plot this particular thing and see how my data looks like now after applying this polynomial kernel. Okay. So my data looks something like this now. I used a scatter plot. Okay. And this is how my data is looking like, guys. Can you see it? If I just increase the size, this is how my data is looking like. Now I can see, okay, the hyperplanes are much more better aligned and I can easily make a distinguishing between train and test. Okay. At this point, I might make a hyperplane which can distinguish between yellow category and the blue category. I have a much better type of graph which shows a better alignment. You can see this is how it looks like. Okay. Over here, I was showing you two tails, but look at just one tail and you are going to say, okay, let's make a plane over here. On the left side, it is going to become a yellow category. On the right side, it is going to become the blue category. So that's it. That's your intuition about how SVM works, specifically how polynomial SVM works. Uh, if there are any questions, I will be happy to take them now. If no, then please type in good to go. Okay. I'm also going to share this script today. For some reason, yesterday the LMS was not allowing me to upload the yesterday's content. I will try it again today. So you can have this particular script and try it in your own system. Okay. So I see no questions on the chat window. So I'm going to just take it as no queries. Okay. And we can move forward now. So if I just go back over here as a small recap, it is just going to create a type of three-dimensional space. Okay. In one dimension, it is going to have x1 square, other in x2 square, and x1 into x2. Okay. And this is going to create a type of a blob. Okay? The blob is going to look something like this. And the next blob is going to look something like this. And in between them, you can have a hyperplane, which can distinguish between the two planes. Okay, that's it. This is all you need to know. There are few more like algorithms which you can go through. Those are very much mathematical intensive, just like we have sigmoid is very much clear to you guys. It might work, but RBF becomes very much famous, which is used in the most of the complex equations. All right. So let's now talk about today's agenda number 2. So we are done with number 1. Let's talk about number 2, random forest. So before random forest, why not let's talk about decision tree again. Okay. So let's talk about random forest. So decision tree. What exactly is decision tree? Decision tree looks something like this. You have a root node and then you have some splits. Okay. I can see there's one question. The idea behind which kernel to use is, again, I can show you very much clearly. A good question which you have asked again. So again, there's a walkthrough which I can give you. There's again one script which I have. Okay. Uh, what exactly happens is how or which kernel to use when. Okay. Take it as each kernel is its own algorithm. Okay. Just take it at this way. Try to apply all the kernels as individual algorithms and see which particular model is performing the best. Okay. But if you want to ask me in a straightforward fashion, what kind of relationship is there between the independent dependent feature? Is it a non-linear? Polynomial might work. If it's linear, just go with the linear type of kernel. If it is non-linear and a very complex bending spaces, go for RBF. Okay, so there are certain rules which you can follow, but if you have the bandwidth to apply all the type of kernels, just go for it. So this particular shall I say code helps you to understand that how to apply each of the kernels. So we have a certain type of data set over here. Okay, there are like orange category and blue category. First of all, I applied linear kernel. Okay, I tried my shall I say uh, model performance. This is what the model performance is coming like. Then I tried RBF kernel. Then I again saw the model performance. Then I tried polynomial kernel. Again saw the performance. You can see just by looking at it, the linear kernel gave me 85% accuracy. RBF kernel gave me 88% accuracy. Polynomial kernel gave me 82%. So out of three, these you can say that RBF performed better. You can just go ahead and use RBF kernel. You can also use sigmoid. Sigmoid gave us very low 79% accuracy. You can do hyperparameter tuning just like we have tried. We talked about C and gamma. You can also add kernel and add all the type of kernels over here. It is going to give you which kernel perform the best. And once that is done, if I just scroll down, uh, so C value at 1000, gamma at 1, kernel as RBF gave us 93% accuracy. So that's it. This is how you are going to pick which particular kernel works best or which particular parameter is going to work best for you. Okay. I hope I was able to answer your query. All right. Thank you. Good question, guys. So let's come back to over this topic now, which is the random forest. But to understand this, let's first understand what is decision tree. Can anybody tell me what is at the top node over here? What exactly this node is called? Root node, right? Perfect. Shall I also say this can be, if this is not a root code, suppose this is the one, and over here also we have certain things. Okay, can we call it as a decision node also? Okay, decision node is that it has few more decisions, maybe a yes, maybe a no, maybe true, maybe false, anything. Okay, so there are a lot of different type of flows which can become from the decision tree. Now we need to know two things. They come your interview question, they come in your basic, shall I say, topic revision. Okay. First of all, how do you decide a root node? Can anybody tell me what is the way to pick certain column and call it or crown it as you a root node? Very good, Devika. The term which we are looking for is called as the formula of information gain. Okay. Information gain formula I shared with you yesterday. That formula is applied throughout all the columns, and whose ever information gain is the maximum, which is like closer to 1, is going to be crowned as the root node. Okay. After that, once we are at the second level, we are going to again see all the rest of the n minus 1 columns, because this particular became the root node. Okay. N minus 1 columns, we are again going to see information gain. Which one is the best? It is going to become the column number 2. So this is C1, this is C2, this might be C3, this might be C4, so on and so forth. So information gain, I hope, is clear to each one of you. Is it clear, guys? What exactly is the need of information gain? And what is the range of information gain? So range is between 0 and 1. Higher the better. Good, Pragati. Now, information gain is calculated by a term which is called as impurity. Can anybody tell me what is impurity? And are there any different types of impurities? Or shall I say formulas which are there? Very good. Impurity is nothing but a mixture of yes and no. If there is no mixture, means single type of category is present, that is a purity or the pure split. Impurity can be calculated on a certain level from two algorithms. Either it's called entropy or one is called as Gini. Entropy is a slower algorithm because it uses a log function. Gini is a faster one because it uses a square function. Entropy's range is from 0 to 1. Gini's range is from 0 to 0.5. That's it. This is all you need to know. Okay. Uh, Wherever it reaches higher value, that is the most impure thing, or shall I say the more split can be allowed. Okay. Any questions so far in the understanding? From here on, when the research data scientists started using decision tree, they saw that wow, decision tree is performing very good. Okay, but there's a red flag which came up. The model's decision tree was creating. Every single one was overtrained, or shall I say, what else? There's a different term which we use. Anybody know? Okay, you can say overfitting. Very good. Okay, there is one more term which you might not have heard so far, and it is there in like later sessions in this particular module, which is called as high variance model. Okay, we are going to talk more about it, but these can be the three things which you can say about decision tree. What exactly decision tree was doing in the hindsight was, if the data looks something like this, and there were certain different categories. If this is the data which we have, Shall I just make it something like this? Let's make it very weird. Okay. And we have different other category which looks something like this. Okay, so these are two splits. Instead of making it bit more less overfit, like ideally should have been something like this. Some of the blues might be spilling over here, some of the reds might be spilling over here. What decision tree was doing, it was making a very sharp curves. Okay, because this is how the splitting of the tree was happening. Okay, so this was the problem which was created by decision tree. uh, what was the solution over there? Why overfitting is there in decision tree? Can you explain me exact reason behind this? Yes, Priyanshu, that's what we are going to now talk about. So first of all, people thought, what exactly is happening over here? Okay, we are just making good decisions. Okay, whenever a split is happening, we are just going to split it over and over again. So earlier when the research data scientists were there, the idea which they were trying to achieve was stop the model training when all the nodes reaches pure split. Now, what exactly pure split means? I hope everybody knows about it. So they're like, just keep on building deeper and deeper models, or shall I say tree, until every decision has been purely split. Okay. Now, what happens in such kind of things? Any type of noise which is there is also captured as information. So in this kind of scenario, noise get captured. Okay, there might be a certain type of entry which is not relevant or which was just once in a while kind of thing. It was also captured on this particular row. Also the model was trained, hence it was not able to just understand the theory behind it, but it took a bookish route. Whatever is there is a source of truth. Okay, so pure split become the very much problem. And how did we eradicate it? That we say that if the impurity reaches certain point, like I should say reaches 0.1%, okay, whatever, I'm just saying it, stop training the model or stop training the model, or shall I say stop going even below. Okay, just wait over there. Now if I just go back and show you what exactly I mean is to decision tree parameters. This is one of the algorithms if I'm going to talk about. Uh, Max leaf load, max features, criteria split, max depth, max minimum split. There might be, okay, yeah, minimum impurity decrease. Okay, if we go down over here, okay, so minimum impurity decrease, a node will split if this split induces or decreases impurity greater than or equal to this value. In short, if I just go back over here and at this particular node, impurity was somewhere around 0.3, and I say if the impurity decreases below 0.4, stop right there. Okay, we are okay with certain number of errors. Okay, that becomes the point of pure split and how to stop it over there. Second was, again, overfitting was making very deep uh, decision trees. Okay, so why not add one more constraint that it can have only certain depth. Okay, certain depth means after 10 layers, means over here this is layer number 1, this is layer number 2, this is layer number 3, this is 4. Maybe I will say after 10 layers just stop right there. I don't want any deeper decision tree. Okay, that also helped. Okay, just like this there are a lot of things which can be played with. Just like over here, if I talk about over here, how much maximum depth can my decision tree have? Okay, how many splits can I have? How many samples can I have? What is the weight? What is features? How many features should I use? Okay, how many oh sorry, this is random state. How many leaf nodes can be there? What is the minimum impurity? So you can see this started helping decision tree perform much better. Okay, but what happened that one of the research data scientists, what they said, okay, I really like this idea that we are doing the pruning part, but what if I do something which is called as voting? Okay, voting in sense I'm going to train on 100 decision trees. Okay, and I'm just going to give them every possible thing, overfit on the data. Okay, but the decision is going to be out of the voting from the 100 decision trees. Okay, maybe decision tree one says that this is category one, decision tree two says that this is one, this is zero, decision three says this is one. So out of 100 there is going to be a voting. Okay, and whatever the majority vote is going to be, we are going to classify that particular thing as either one or zero. So what exactly is 100 decision tree? So when we say there is one tree, but if there are 100 trees, we term that thing or that particular place as forest. And that's how the random forest term came up for this particular algorithm. Okay, they use the, shall I say, the red flag of decision tree of being overfit into their own power. They said that overfit on like make 100 or 500 or 1000 trees, let them overfit on the data, and we are going to then do the voting, and whatever the vote is going to be there, the maximum vote, that is going to be the decision of the final output. Okay, this is what a random forest looks like. Okay, so the only thing which has been different in the decision tree and random forest is going to be this. Okay, random forest parameters. So I'm just going to go over here. Okay, so just skip for this thing. Just look at this criteria, exactly same like decision tree. Maximum depth, same. This is same. This is same. You will see all of maximum, shall I say, maximum of the parameters are exactly same like decision tree. The only thing which changes is over here, n estimator, which is nothing but how many trees, individual trees, do you want to your model to be trained on. Okay, it can be 100, 300, 500, 1000, whichever number you want to pick. Okay, if you have a smaller data set, go for higher number of decision trees. If you have a larger data set, it's safer, or shall I say it's quicker to go for lower number of decision trees. That's it. So this is the intuition about random forest. uh, Now what happened in the much more improvement in random forest, people started applying even more sophisticated way of applying how exactly different decision tree can work. Okay, minimum sample split, what's that? How many, like, okay, we are going to talk about it, Pranshu. So my data looks like this. I have column 1, I have column 2, column 3, column 4, and then in this I have row 1, row 2, row 3, row 4, something like this. uh, so they took the decision tree and the voting power to the next level. What they did, maybe the decision tree number one, decision tree number one is going to have column 1 and column 2. Okay, C1 and C2. Decision tree number 2 is going to have 1 and 3, C1 and C3. D3 is going to have C3 and C1 or C4. Okay, so what exactly we are doing, we are splitting the data even further. Even in row C1 and C2, I can also have in C1, C2 row 1 to row 10. Okay, over here row 20 to row 30, or anything like this. So what they try to do, we are going to split the data so much between the different decision tree that each of those trees are going to be closely related, but not exactly the same. Okay, this way the data is going to learn different things. DT1 might learn something very much different, which was not there captured in DT2, which was not there captured in DT3. Okay, and then we are going to do the voting technique. Okay, so this is how random forest actually works. That's why the for tree based algorithms are much more versatile in the machine learning world. Okay, after this, now we have deep learning, neural network, shall I say, attention type of algorithms, which are the very much new, like less than 10 years old. Those are the best type of models so far, which are used in LLMs. But before that, these models were very much famous in, shall I say, creating a very good classification or different type of models. Okay. So minimum sample spread, just like Priyanshu asked, is how much samples needs to be there. Okay. How much samples can be used in different categories. Okay. If you want to see the theoretical part, let's go over here. Okay. So minimum samples, yeah, the minimum number of samples required to split an internal load. If there are not more than samples, okay, just let's go back over here. Yesterday we saw that in this split there were 2 yes and 3 no. Over here there were like 4 yes and 2 no. Okay. If I say that if my total rows are less than 5, okay, stop right there. Don't go any further. Is this less than 5? No. Then it is going to even further down. 2 yes and 1 no. And it might be like 2 no's. So we can see these both are less than 5. Then it is going to stop right here. So this is the minimum sample split. Okay. So this is the intuition of random forest now. Are there any questions? And Priyanshu, was I able to help you? Just let me know. If you still want to understand, just also uh, think. Okay. All right. Okay. So, okay, let's try to give the minimum sample split understanding. Okay. Let me take example from yesterday. I'll going to open yesterday's notes first of all. Okay. Right. Just scroll down to, yeah, this is, I'm going to take this one. Yeah. So in this one, there are four different type of columns which we had, and then we have the y column. Okay, so this was y for us, and this was x1, x2, x3, and x4. Okay, the root node for us was Outlook. Okay, so Outlook, and Outlook had three categories. One was sunny, one was overcast, and one was rain. Okay, now in this I had like in sunny 2 no, 3 no. Okay, so there are 2 yes and 3 no. Over here 4 yes, 0 no. And over here there were, okay, rain. Rain play times 2, 3, 4, 5. Okay, so 1, 2, 3. Okay, so 3 yes and 2 no. Okay, so guys, what exactly this means? Over here there are 5 samples, 5 rows. Over here we have 4 rows. Over here we have again 5 rows. Okay, rows can also be termed as samples. So minimum sample split means how many minimum rows should be there to perform the further sampling. Okay, suppose my the this particular value I will say as 4. Okay, if there are minimum 4 rows, then only split. So in sunny, are there more than 4 rows? Yes or no? Yes, it is going to further down. uh, do we have more than 4 rows over here? No. So maybe I can give this as, just stop it right here. Don't go any further down. By chance, this is a pure split also, then it is a good thing. It has more than 5 rows, it is going to go down even more. Let's take one example. In down, we are going to add temperature. In temperature, we are going to say, uh, uh, shall I say, remove this. Just for this particular action, I'm going to say temperature. Temperature is hot, mild, and cool. Okay, so it is again going to split even down. One is hot, other is mild, and last is cool. Okay, so let's see in hot. We have no, no, yes. And do we have anything else? No. So no, no, yes. So one yes and two no. Okay. Now we have only 3 rows left over here. So according to minimum split 4, can I go even further down? Yes or no? No, exactly. This is where it is going to stop. Similarly, for all things, wherever there is less than 4 rows, it is going to stop right there. And my decision tree is going to start from here and it is just going to end over here. That's it. Over here, I can see there is certain impurity which is also left, which is fine by me. Okay. I have to then make a decision out of it by the voting category. Okay. That's it. This is how minimum sample split works. I hope it's understood now. Perfect. All right. So why not use this particular algorithm and do some analysis? Okay. Mm, do you guys have yesterday's script open with you? Were you able to like run it yesterday? If yes, then you can just go ahead and add the random forest algorithm. If no, then it's completely fine. You can just take it as a homework, and the algorithm is very much same. All you need to do is update pipeline with what? The random forest algorithm. That's it. Okay, and it is going to work exactly like how decision tree worked. So let me just show you. I think I have that particular notebook open. Let me just try to find it over here. So decision tree. Okay. So over here, this is how I imported decision tree. Instead of decision tree, you have to find in random forest. And over here, n underscore estimator equals to how many trees you wanted, maybe 400. Okay. You can just add that thing. And it is going to work exactly like how decision tree works. Okay. Take it as a homework and let me know what is the performance you got. Okay. If you have any questions and how to do it, or if there are any queries, just let me know. So how exactly it is done? Let me just copy it, take it to Google, and instead of this, I'm going to do random forest. Okay. So it is going to be random forest classifier. If I just scroll down, this is how you import it. Copy it, go back over here, paste it over here. Okay. Just call it this one, go back over here, paste it, and over here, n underscore estimator, shift tab, uh, estimator equals to 100. This is what you have to do. Try with 400, maybe try doing the hyperparameter tuning. How? Let me just not change it. Over here, I did hyperparameter tuning with the CC alpha and random state. I can also add things like how many trees I want to try. Okay. Okay. Do you want me to scroll up? Okay. There you go, Trisha. Just let me know once you're done. Okay, guys. Shall we move forward now? So before starting with the next topic, let's also talk about, before starting with the, shall I say, imbalanced dataset, let's take a small jump towards multi-class classification. So according to you, what is multi-class classification, guys? Any guesses? More than two classes, simple thing, right? So yeah, perfect. So what happens in binary class classification? Uh, we have two categories, 0 or 1, true or false, yes and no, this or that, something like this. But in multi-class, you can have more than two. It can be 3, it can be 4, it can be n. Okay. So multiple type of probabilities occur. Now, guys, what happens in binary class classification? Usually you get probability of 0 and probability of 1. But it works exactly like how the, shall I say, encoding works. You know na, that in one hot encoding, you remove n minus 1 column. Do you know about this rule in one hot encoding? Okay, there's one student who knows about it. Let's see. Yeah. So if I talk about a very simple example, male and female. So if male is 1, female becomes, sorry, male is 0, female becomes 1, this is 1, this becomes 0. So why not just get rid of 1, this one, and wherever female is 1, we know it's female, wherever it's 0, we know it's male. Similarly, in this probability, or shall I say in binary class classification, what we do, we only look at one probability. Okay, so in one probability, if it is 0.7, so we know that probability of 0 is going to be 1 minus 0.7, which is 0.3, right? We know about it because combination of both becomes a 1, or shall I say 100% probability. So one is this, then other is going to be 1 minus n, that's it. So that's why we only look at one probability. But in multi-class classification, this thing changes. So what happens? So suppose I have different categories, suppose A, B, C, D, E, F, and G. In this scenario, what happens? We get probability of A, then we have a column, probability of B, then again a column, then C, then D, and so on and so forth it goes. All of them get individual probability. Instead of one hot encoding, how it's done, like we remove one, over here we are going to find the max of probability, and whichever had the maximum probability is going to be the right answer. Okay, suppose this got 10% probability, or shall I say 0.1, this got 0.3, 0.6, 0.2, oh sorry, 0.1 and 0.1. All of them, if you calculate, is going to be one probability, but which one was the largest? It was 0.6. Hence the output is going to be C. This is how multi-class classification works. Any questions in this thing? Perfect. So why not just take this thing? Okay, now there's one more thing which becomes a bit more complex. You are going to learn that in deep learning module, but the activation function behind the scenes also changes. Okay, it changes to softmax. Okay, softmax looks a bit different, and it calculates individual probability, and then we get this answer 0.1, 0.36, and so on and so forth. Then the maximization function gives us the final out. Okay, uh, just note it as a point to know, but once your deep learning classes start, you are going to learn more about it, how exactly softmax work. Okay, as of now, all you need to do is how exactly multi-class classification actually gives us the final out. Okay, so now why not, let's open up our today's session. Okay, And I hope your Jupyter notebook is also ready. Going to give you 2 minutes to open up if you want to follow it with me. Okay. I'm always just like yesterday also, I'm going to paste the code on the chat window so that you can easily copy and paste it on your own system as well. Okay. You have 1 to 2 minutes. I hope everybody of you is ready now. So why not import the necessary libraries first? Okay. So step one is to import. Let me just zoom in. Import NumPy. Import Pandas. And import sklearn dot datasets. Sorry, from import load underscore iris. So I'm just going to paste it over here to your system as well. Right. Let's try to run it. So this is a like there are certain test data which is already stored in these libraries. So we are going to use one of them. Okay. We can also go ahead and now import the algorithms which we are going to use. Like I'm just going to copy paste it over here. So these are going to be all the models which we are going to use: logistic regression, SVC, K nearest neighbors, naive Bayes decision tree, and random forest classifier. Okay. If I hit enter, all of these models are also loaded in my system now. Okay. Let's also import the evaluation metrics. Okay. This is going to be the evaluation metric, accuracy score, and classification report. Okay. So once I do this, it has been now imported. Uh, Now let's try and load the data set. Load data set. How can that be done? Is by the third part, iris load data set. Okay. Uh, so if I just hit enter and if I just call iris, okay, iris dot head. Okay. Dot data dot head. No, it's not happening. Okay. Okay. If I just call x. Okay. So this is how the data looks like. So what exactly is iris dataset? Let me show you iris dataset. So iris is a flower species. Okay. And this particular dataset contains 1, 2, 3, and 4 individual variables: sepal length, sepal width, petal length, petal width. Okay. These three are going to give us the species, which kind of species of flower, or shall I say iris, is that particular species. So how exactly this looks like? Suppose I have sepal length of 4.3, or shall I say 5.1, sepal width of 3.5, petal length of this, it is setosa. So there are three categories: setosa, versicolor, and virginica. These are the three different categories. So this is my dependent feature, the species. Now, since these are the three categories, what do you think is this data? Is it a binary classification or multi-class classification? Very good, Pragati. Exactly. This is a multi-class classification. If I just go ahead and press Y, so you will see it is already, this data is very much clean. Okay, it is already cleared into the label encoding 0, 1, and 2. So my uh, classification model has to do a multi-class classification analysis. Okay, so why not first of all divide our data into training and test part. Okay, so if I just copy and paste it over in the chat window, show it over here as well. So train and test is now done. Oh, I did not import train test. Let me just import that as well. Don't forget to import this particular function. I'm just going to go back above and import it over here. Okay, so what happened? I might have to copy it again. Okay, I'm not able to load iris. Name error. Load iris is not defined. Devika, you might have forgot to import this load iris. Can you try to import this again? Run this particular line, okay? And it should work for you. Now let's try to create a dictionary which is going to save our model performance. Okay, I'm going to paste it over here as well. This particular one is going to save all the model performance. Why not? Let's start with our first model, which is nothing but the logistic regression. Yesterday, somebody was asking me about if we have a different data which we can work with. So this is what we are going to use. Okay, so I'm going to paste this whole Pragati. No, it's not only for, shall I say, each of these classification algorithms are very much well versed to handle multi-class classification problems as well. Okay. So for logistic regression, first of all, I am importing the, shall I say, this particular function, fitting the model, predicting the model, and then finally the accuracy and classification report and the model performance, the dictionary which I created. I'm going to save the logistic regression along with its accuracy. Okay, once I do this, so I can see, oh, 100% accuracy. Okay, the model was able to train a lot. Uh, Very good. The model is very good. Okay, so it was able to easily distinguish between the training and shall I say different categories, which is very good. Okay, so why not let's try the same thing with the next algorithm, which is SVC, support vector classification. Okay, so this time this is going to be the support vector classification, and I'm going to run it over here as well. If I run it, support vector is also giving us 100% accuracy. I think I chose a very simple type of data set. It is able to distinguish between the data very much easily. Let's try KNN now. Okay, let's try KNN. Everybody is giving us good results. Maybe the data is very easy. Copy. Let's try naive base. Okay. Now let's go ahead, try decision tree. is also giving us good result. Then finally, let's end with trying the random forest. Okay. If decision tree was good, I think random forest is going to exactly give us the same result. And without the doubt, all of these models gave us the best result. Okay. Uh, Now what we can do is compare all the models and see how exactly it is working. Okay. We can see all the models gave us the best results. Okay. Like 100% accuracy is there because the data set is very much easy. Okay. That's why all these models were able to distinguish between different categories over here. Okay. So I feel that the best model uh, comparison cannot be done because all the models are giving us the, shall I say, the great result. But the workflow can be understood over here. How exactly to run the code. You can run each single one of the models, see the accuracy, see F1 score or something like this. And whichever is giving us the best result, we can just simply pick that one up. Okay. If there are any questions, feel free to ask them. Yeah. We were able to complete few of the very important topics and majority of the techniques through which you can make a classification model. We have also seen how exactly the same algorithms, if shown the multi-class classification, can also classify them into a proper categories. Okay. The data which we used was very much easy, and that's why it was able to easily distinguish between different categories. That's why we got 100% performance in all of these models. Okay, which is fine. uh, we can in future try much more complex data set which might yield some different results so that we can choose the best performing model. uh, Now guys, coming to the next topic, which is going to be how to handle the highly imbalanced data. Okay, so to talk about imbalanced data, what do you think is highly imbalanced data? What can be the definition of highly? So highly imbalanced data actually looks something like this, that suppose you have 1,000 rows, and if it's a binary classification, we can easily take classification and we can take an example of transaction fraud. Okay. So we know that every second there are thousands of transactions which are happening in your credit card, or shall I say the credit card companies. Okay, people are doing a lot of transactions. So let's take on an easy basis that there are 1,000 rows which are being captured. Out of these 1,000 rows, okay, there is hardly one or maybe two transactions which look fishy. Okay, so one or two becomes a fraudulent transaction. So if we talk about the event rate over here, what do you think is the event rate? Event rate is nothing but number of ones upon number of ones upon total rows. Okay, so it is nothing going to be like number of ones. Suppose it's like one or two. So let's take two, and if we take maybe 100 rows, okay, so this is nothing but 0.02, or we can also say as 2%. If we take it like one more zero, it is going to be nothing but 0.02%, something like this, or 0.2%. Means this is a highly imbalanced data. Highly imbalanced data. In this, we have a lot of points which are indicating towards zero. If I want to show something like this, okay, and there are like lot of points which are associated with data is like scattered in a lot of different ways. Okay, and there is hardly one point or maybe over here 2 points which are fraudulent. Maybe let's take one more point somewhere over here, 3 points. How can I even fathom to make model understand that to distinguish between a normal transaction and a fraudulent transaction. This becomes a challenging part. Okay. I worked in American Express like few years ago, and I was into this particular department where we used to try and create a model which can handle, or shall I say, which can give us if a certain transaction is a fraudulent transaction. We ended up creating a very complex model, okay, with, like, I think there were at one time 1100 columns which we were using, and the data was very big, and we tried to create a certain type of machine learning model which was able to give us a very decent type of uh, result. Okay. Before understanding this, what do you think is going to be the performance metrics which we can use over here? So what if I want to use a certain performance metrics? The event rate which I have is, event rate is 2%, means non-event rate is 98%. Okay. Now, if I say that I created a model and my accuracy came out to be around 98%, is my model good? Any guesses? Model accuracy. So, since nobody answered over here, so 98% means I have a column which is called as fraud, and there are like 100 rows, 1, 2, 3, 4, 5 till 100. And what my model did with this 98% accuracy was to classify everything as zero. It classified everything as zero, and we know accuracy is nothing but true negative plus true positive upon total. Okay, so we know true negative were actually 100, oh sorry, 98. True positive were like zero because my model did not give anything upon 100. In short, it is giving us 98% accuracy. So in a highly shall I say imbalanced data, accuracy becomes a not a good performance metric. Okay, in a highly imbalanced data, we go for metrics like recall or F1 score. These become a very important factor. Okay, accuracy does not work because accuracy is this formula, and this formula is just going to give you a higher result, which is not a correct thing. Is it clear? Are there any questions? I'm going to wait for a couple of seconds because if there are any questions, I don't want them to miss. Okay, no questions. Then I hope you were able to understand what exactly is highly imbalanced data. Okay. Now, the imbalanced data, how do you exactly approach such kind of things? So, what is the approach to deal with highly imbalanced data? So this becomes a very evident, shall I say, question. The answer to this is there are three main type of techniques which can be used. Okay. First technique is oversampling. Second is called as undersampling. Third is called as SMOTE, small. Okay. Um, Apart from this, there is a, shall I say, algorithm which can be used, which is called as isolation forest. Okay. So these are three or basically four techniques which are generally used to handle a highly imbalanced data. Okay, so let's talk about the first technique, which is nothing but the oversampling technique. So if I have to show you in a graphical manner what exactly the data distribution looks like, if we have to create a 0 and 1, the distribution over here are 100 rows, and we know that there are like around 98% data which is of 1, and only small amount of data which is for 1. 98% is 0. Okay, in this kind of thing, oversampling means we are going to oversample the 1, means copy and paste, duplication of samples of 1. This is nothing but duplicating of rows. Okay, so these rows are duplicated over here so that both of the classes 0 and 1 becomes equal. If there were like 98 rows for zeros, they are going to be same 98 rows for ones. Now what exactly this is useful for is that uh, we get equal amount of zeros and ones, and we give model this particular data, and we say that okay, try to now understand, because as of now this was getting overpowered or overshadowed by the huge amount of zeros over here. Okay, in a lot of scenarios this technique works wonderfully. Okay, and we were able to see that the model performance in distinguishing between 0 and 1 was significantly improved as compared to if it was just given as 0 and 1. Okay, so this is called as oversampling. So we use the algorithm and we tell that wherever the event rate is 1, just duplicate those rows to match the amount of rows which are there for the 0. This is how the duplication occurs. Okay, if you want to see this scenario, I'm going to show it, but as of now, is the theory clear? That's what I wanted to know. Okay, thank you. Uh, Similarly, on the same context, let's talk about undersampling. In undersampling, exact opposite happens. Okay, uh, so what happens? If I just try to show it over here, if we had 0 number of rows over here and 1 number of rows over here, okay, this is somewhere around 100, and this is 0, this is 1. What is going to happen is that it is now going to match down towards equal number of zeros. Okay, the whole data is going to match down so that we have similar amount of zeros. Okay, suppose they were 1 rows were around 10, so zeros are also now going to be around 10. Okay, so exact opposite of what was happening in oversampling. Oversampling was duplicating ones, undersampling is reducing the zeros. Okay, now before talking about the cons of this particular thing, there is a specific con of undersampling. What happens that in undersampling you are removing lot of information. Okay, you are forcing uh, the model to just ignore a lot of information. Okay, there might be some very important rows which you are just simply just removing them. Okay, that becomes a very much tricky point. Okay, that's why undersampling might not be used as much as oversampling technique is used. Okay, now oversampling is also having a certain problem that it is the same data. How much can it even learn from once? It is the same thing which it is learning, right? So again, that becomes a big problem, but that's still better than undersampling. Okay, is the difference between these two clear now? If this applicables only to zeros and ones, um, like so, it is only applicable towards highly imbalanced data. Okay, it is only applicable to y. Y can have any value, true, false, yes, no, big, small. Okay, like only binary. Majorly, yes, it is only applicable towards binary, but I have never seen its application towards multi-class classification majorly. Okay. So my answer will be only binary, yes. Okay. Now, guys, this was two things. One was undersampling, one was oversampling. But there is one more sophisticated type of technique which people came up, or the research data scientists came up, is SMOT. Okay. The full form for SMOT is synthetic minority oversampling technique. So what happens, guys, if I just pick up this same question? I'm just going to copy it, paste it over here. Oops, what happened? Let me just copy it again. Okay. So what exactly SMOT does is, let's try to pick a new color over here. Okay. So what happens over here? We know these were the minority classes. The red one was the minority classes. What is this particular technique is going to do is, it's a synthetic way of generating new rows. So what it is going to do, it is going to study these three parts, or these three rows, and it is going to create certain rows. Shall I give it very different color? Let me just give it red color only. It is going to create some synthetic data set, just like the synthetic data set which we created in one of the examples of SVM, which I showed you in the starting of the class. And this is going to do exactly like oversampling is done. Okay. Instead of just making the duplicates of the same thing. Okay. Over here, this was duplicated multiple times to match this thing. Here, we are just making a synthetic data around those rows so that both the zeros and ones become the same quantity. Okay. In my own experience towards handling the imbalance data, SMOT give us much more promising results as compared to any other technique, because it is by itself making some synthetic data, and this is able to help people to make a very good predictive models. Okay. So are these three techniques clear to you guys theoretically? Become same quantity, meaning that the number of rows for zeros, if suppose it's 98, ones is also is now going to be 98 rows. This is what the same quantity means. Okay, perfect. Good question. uh, so with this, I hope the three techniques are now clear to you guys theoretically. Okay, let's try to take this particular example towards our Jupyter notebook. For this, I'm going to ask you to open up your Jupyter notebook again. And this time I'm going to handling highly balanced data. Okay. So for this, let me give you the data set first. Okay. So going to paste it over here. This is the credit card data set which you need to use. Okay. So first of all, let's import the necessary libraries. And before that, data is equal to pd.read CSV. Okay. Let me just give you the whole code. So this is the first code. So we are going to import pandas. We are going to import train test plate, cross validation score, standard scalar. Okay. decision tree classifier, accuracy score, SMOT. We are going to import SMOT, and then we are going to import Matplotlib. Let me see if we have any other library which I want to use. Yeah, I think this is the one. Okay. To show you the how highly imbalanced this data is, we are going to also import something. But as of now, let's run these two. Let me run this one first, and let me import my data set. Okay. Once I import the data set, what I'm going to do is see the data info to see how exactly my data is looking like. Okay. So we have 2000 rows and we have around 31 columns in total for this particular data set. Okay. There are a lot of features which are there. And finally, there's a class feature tells us whether this particular account is a fraud, a particular transaction is fraud or not. Okay. Let's see the head as well. So class 0 means not a fraud. Class 1 means that it is a fraud. Okay. So with this, let's try and see the class value count. I have pasted the code also. DF, no, it is data. So we can see that class 0, or shall I say the category 0, has 1974 rows, but only 26 rows are there for class 1. Okay. If you want to just plot it also, let's try to plot it as well and see how exactly the answer looks like. So you can see this is the distribution, guys. Just look at the distribution. We have 99% data, or shall I say 98.7% of data is of class 0. Only and only 1.3% of data is for class 1. Highly imbalanced data. Okay. So with this, let's try and do some analysis and try to make our imbalanced data function for us. For that, first of all, let's separate the data into train and test section. Okay. So for that, I'm going to just create X and Y. Okay. And this is being created. Uh, why not do few of the feature engineering part like by making train and test split, as well as do the standard scaling, fit and transform. So with this, we are going to have a clean data set for us to work with. Once I do this, my data set is done. Okay. If you want, I can wait for a couple of seconds. Okay. Let's try to plot our data as well. So this is going to be plotting of data and see how exactly my plot looks like. So you can see, guys, don't go with these numbers because we have now standardized our data. So after standardization, this is how the data is looking like. We can see the orange, sorry, the purple are the normal 0 category. Yellow are the ones which are having, shall I say, 1 category, means are the fraudulent transactions. Okay. You can see there's one over here, one here, two here, two, three here, couple of here. And this is how my data set is looking like. Highly imbalanced data, just like what we have created in our Blackboard as well. Okay. So as of now, we can see that the data is highly imbalanced. The yellow ones over here. I feel, can I change CMap to something else? It's okay. It's fine. So as of now, we can see that the yellow points over here are highly imbalanced. Why not? Let's try the smooth technique. Okay. With the smooth technique, what I'm going to do is paste it over here. And with this mode, I am just creating X and creating Y. Okay. This is going to create a synthetic data set. It is going to do exactly the same thing. All you need to do is give it X train SC and Y train. Okay. So with this, it is going to do exactly the same thing. Once of all, I just give it the Y train. It is going to understand, okay, whichever class is imbalanced, we are not providing it 0 or 1. Whichever class is imbalanced, it is going to create a synthetic data for it. Okay. Once I run this, what happened? Let me rerun it. Okay, it worked now. So I'm again going to create a data, and now it looks something like this. Guys, you can see between this point and this point, I can see there are a lot of data points which was created. Between this and this, lot of synthetic data points which were created. So you can see now equal number of classes are now being there. Okay. So let's see if we have y trains mod as type. Let me see what is the type of y trains mod. Okay, it's a series. So the series should be able to give me value count. So you can see both of them are now having equal number of quantities. Zeros are like 1182, ones are like 1182. Both of them are now equal. So now that your data is created, why not just go ahead and do the classification? For classification, we know that we can use many classification algorithms. Why not just go ahead and use a decision tree classifier? Okay. So I'm just going to paste the code over to your screen, paste it over here as well, run it. Now that is done. Let's try to see the accuracy. So guys, first of all, accuracy is coming out to be very good, but is accuracy a correct answer, or shall I say, is accuracy is the correct metric to look over here? No, exactly, because it is not the correct way. It is not imbalanced anymore, correct? But just like I told you, accuracy is it's still not the correct way of looking at your data. Okay, so try to refrain from using it. Very good attention to the detail, Preeti. Okay, but let's try to see how exactly my data distribution looks like with the help of a cross confusion matrix. Okay, try to look at how exactly we are creating this particular model, guys, and specifically Preeti, just like you asked me this question. At the time of training the model, I used smart dataset, but at the time of predicting of my model, at the time of predicting, I used the original dataset by test spread. I did not use the smart one. Okay. So this is how I was able to see, like over here, this is my actual data. This is not the synthetic data. Okay. And y-test spread came out to be like this. Okay. So test accuracy, which I said is 98.5. So you can see I am using the original data set. In original data set, accuracy came out to be 98%, which is not the correct mark. Okay. So if I just go back over here in the confusion matrix, look at it. This is the true label. So wherever it was fraudulent, how many non-fraudulent it was able to make zero, which is a good thing. But non-fraudulent, which was predicted as fraudulent, is still fine. Just think of it this way, guys. Suppose, and it happens, it's a very original thing, or shall I say it is a very normal practice. There are a lot of times you might also have you have made a transaction, okay, to a very different vendor for some reason, and instantly you get a call from your bank, or it can be automatic call, or it's like someone on the other side asking you that, sir or ma'am, you have just made a transaction of so and so money. Was it you, or was it like type of transaction which you are not aware of? Okay, press one, say yes, something like this. So this is like there is our automatic systems which are there, which feels like, okay, this might be a misclassification, but let's not take a risk. Let's call the person whose account has been tagged to this particular transaction and try to ask them. If they say it's not a fraudulent transaction, then you can go ahead normally. Okay, but even after this, it goes to the fraud department. They are going to manually see what kind of transaction happened, and that's it. If they still find it fishy, they're going to ask you about the proof. Okay, give us the proof why you made this particular transaction. And we are too small of people to look through these kind of transactions, because at the time when I was there in that particular firm, the I think there was a cap of $10,000. Okay, below that, certain different teams used to handle it. Ab- Above $10,000 transaction, a proper dedicated team used to work on it, because nobody takes a risk on small amounts in doing a fraud. Okay, people try to be greedy on these kind of things. Okay. So yeah, there's a different practice in different firms to handle the fraudulent transaction. So with this, I can understand that wherever the fraudulent transaction was there, my model was giving us proper result. At no time it gave us false negative. Just like I told you in COVID also, it's okay to predict somebody as a false positive, but it's very bad to predict a false negative. So if you even look at the classification report over here, okay, let me try to see if we have a classification report. Yes, okay, it's over here. Which metric over here scores the best? And is it a good metric or not? If you look at it closely, the recall is 100%. And just like I told you, highly imbalanced data needs recall as their performance metric. Even though accuracy is 98%, F1 score is 58, precision is highly only 40. It's completely fine. Un- unless, or shall I say, if recall is the good part. Okay. So it's a very good thing. If I try to show you, shall I say, the ROC AUC curve, since recall is good, recall shows us the false positive rate and true positive rate. So ROCAUC is not defined. Let me try to import it again. What happened? ROCAUC curve. Just a second. Why it's not working? Uh, ROCAUC. Okay. Okay. Let me try to remedify this thing. Just a second. Okay. So it is working now. Let me share this with you. So you will see this is the ROCAUC curve. You will see this is how it looks like, because over on the y-axis we have true positive rate, on the x-axis we have false positive rate, and we know that the false positive are 0. That's why we are getting the perfect area under the curve. This is the best model you can get in terms of ROC-AUC distribution. Okay, and with this we are now able to understand how exactly SMART works. Any questions, just let me know. With oversampling done, if there are no questions, let's talk about undersampling now. Okay, for undersampling, we are going to use a library which is called as undersampler. Okay, from imbalance data. So in this, it is going to do random undersampling. It is going to just take some random type of rows for zeros and going to only pick enough so that it is going to be exactly same like the ones. Okay. So I'm going to just copy paste it over here. Can you please reiterate on the F1 score, recall, research in the interpretation? Of course, Shisha. So, okay, over here, first of all, if you look at this confusion matrix, okay, we know that what exactly is accuracy. It is nothing but true positive plus true negative upon complete. What is recall and precision? We have already shared those formulas. Let's see, precision, recall, formula. Okay. So if you just look at this particular thing, true positive upon true positive plus false positive. Okay. So if you go back above over here, this is true positive upon true positive plus false positive. So this is going to give you only these two are going to give you precision. Recall is going to be true positive plus false negative. So true positive plus false negative. And this particular block is going to give you the recall. So let me just take this thing, go back over into the window. Okay. Paste it over here. And if you just talk about what is the combination over here. So if you just look at these two, this gives us precision. Okay. Now precision talks about how many positives were there. Okay. And how many were actually one. So we can see, oh, I think I did something wrong. So first of all, let me just take out the formula over here. There's a formula. Come back over here. And first of all, define. Okay, this is not the positive. Let me just define the positives first. Okay, non-fraudulent is nothing but 0. This is 1. This is 0. This is 1. So 0 and 0. So this is nothing but true negative. Okay, and this is nothing but true positive. Uh, this is actually actual value is positive and it is false negative. Okay, and this is false positive. Okay, so this is how the whole data looks like. Now precision says true positive upon true positive plus false positive. So actually this is the one which is going to be talked about in precision. So we can see true positive, how many are there? There are 8 plus how many? Okay, in it's below. So upon 8 plus 12. So this is nothing but 8 upon 20, and that is going to give us some number over here, whatever it was. I think it was 40% or something. Let me just go back over here. It was 40%. Okay. So if we just go back over 0.4. Now recall. Let's see true positive upon true positive plus false negative. These two is going to give us the recall. Okay. And the formula shows that it is true positive upon true positive plus false negative. So 8 upon 8 plus 0, which is nothing but 8 by 8, which is nothing but 1.00. So these are the two metrics. Okay. This particular metric precision is used when penalty of doing a 1 is high. Over here, penalty of 0 of doing is high. So if you just look at it, we were able to capture all the actual fraudulence and we did not do a false negative. We did not say any transaction which was a fraudulent and we said that it's not a fraudulent. Okay. But there were a lot of scenarios in which the transaction was non-fraudulent, but our system says that those are fraudulent. Okay. But since this one's penalty was at number 1, that's why it's completely fine and we are happy that recall is good and we are okay that the precision failed. Okay, but if the situation was other way around and we wanted maximum precision, then this might have impacted. So these two go hand in hand. If this increases, this decreases, and you play with the threshold values. What are the threshold values? Those are nothing but the ROC AUC curve. Okay, if you remember for yesterday's class. Okay, it is a trade-off between true positive rate and false positive rate, and the best model is over here where true positive is maximum and false positive is minimum. Okay, and these are the other points which we talked about in our previous class. Okay, I hope this example was able to make you understand what is the reason why the recall was given much more priority and why it's okay that precision failed, because it's completely fine that we have few transaction which were termed as fraudulent, but if the person shows the proof, then it becomes like completely normal thing. Okay, we are going to do random undersampling, and you know what exactly undersampling does is it is going to decrease the amount of zeros and so that it can match the number of ones. Okay, so let's just see the original data set. This was the original data set. Okay, over here you can see there are a lot of purple dots and very few of yellow dots. Okay, if I do this same thing over here, use a random sampler, and now I hit enter, this is how the data is going to look like. It is going to have equal number of zeros and ones, but the main problem with undersampling, guys, just like I told you, it is going to let go of lot of crucial information. Okay, it might get let go of noise, but also crucial information. Okay, there are like thousands of rows which were there, which are now reduced to only couple of rows. Okay, this is how undersampling works. So why not, let's see if my decision tree classifier works very good with the undersampled data set. Let's try it. If I run it, and now I'm going to see how exactly my model performance looks like. Okay, so I'm going to just put it over here and test it. Look at it, guys. Recall is good. Accuracy has like decreased to 81%. Okay, precision is hardly 5% now. F1 score is hardly 9%. Even though recall is good, your model is not going to take off because precision and recall has taken a very big hit. Very big hit. Let's see if I have um, the confusion matrix. Let me try to create this one over here. Okay. If I paste it. Do we have y test and y pride? Yes. Okay. Let's see. Look at this particular graph and try to compare it with what we did with the SMART analysis. Okay. I'll just going to take it over here and paste it over here. I'm going to scroll down and see over here. In the previous one, only 12 were like given a misclassification. So anything which is false positive or false negative is called as misclassified. Okay. In this scenario, only 12 of the transactions out of 1,000 transactions were like misclassified as fraudulent. Okay. And they were given call, and the whole analyst team sat with those 12 additionally because those were classified as fraudulent, which is still fine. But over here, that number bumped up to 154, which is very, very high. Suppose you are you are a data scientist, you created a fraud detection analytics team. Okay. On a single day, they were only coming 12 transactions through one model, which were like incorrect out of 20. The 20 rows, or shall I say 20 transaction, came to you to be like analyzed further to see if those were fraudulent transactions. You were like, okay, 40% rate is my success rate. It's completely fine. But now you can see these are 165, or shall I say 163 rows which are coming, and the analyst team has to sit through 163 transactions every single day to see like if out of them which are genuinely fraudulent transaction and which are like the false alarms. Okay, so you can see in this particular alarm there are very lot of false alarms. Okay, as compared to what we have seen in this particular model, there were fewer alarms as compared to over here. And if you take the ratio, it was 8 upon 163, which is a very high number. Let's count it. Over here, it's only 40%. Okay. Over here, it's 95% false alarms. Only 5% are true. How do we know that? Because we saw the whole result over here. 5% precision and 100% recall. So now you know that even if you get a highly imbalanced data set, you have to try 2 to 3 different techniques to see which one is giving us less number of false alarms. Okay, it's okay to have false alarms, but it's not okay to have too many false alarms. Okay, is it clear now? First of all, we have talked about the oversampling technique. we talked about undersampling technique, and in oversampling there's a much more synthetic type of technique which is called as smooth. Okay, synthetic minority oversampling technique. So with these three techniques, or shall I say specifically two techniques, we have seen what are the pros and cons of different type of techniques. uh, I will not say one is better than the other, but I will say that try 2 to 3 techniques, and whichever works best for your case, go ahead with them. Okay. Now there is one last type of technique which can be used in your scenario, which is called as tree, shall I say specialized tree for highly imbalanced data. All right. So in this, there are different trees, which shall I say tree algorithms, which are there, which you can easily use for your uh, highly imbalanced data set. Okay. One of the very famous one is called as isolation forest. Okay. And the other one is called as balanced random forest classifier. Balanced random forest classifier. Okay. Both of them works on exact similar structure, create multiple different trees. Okay. But balanced random forest classifier, what it does exactly like how the stratified k-fold does it. So who knows what is stratified k-fold? Any guesses? Cross validation. The Priti is correct. Shusha, no, that's not what we were talking about. But uh, you are right on that point, Susha, that in train test split, we have a parameter in which you say use a stratified distribution so that equal amount goes to different categories. Very good. So that's a good point to note. Yeah, proportion. So exactly the same principle happens in balanced random forest classifier. What it does, just like I told you in balanced the random forest techniques, is that they use individual decision trees to train on different data. Okay, different data means one can have column 1, column 3, other can have column 2, column 4. It might have different number of rows, it might have different number of rows, but the balanced approach is that this will have the same proportion of zeros and ones, which this one is going to have zeros and ones. Okay, suppose it's like a 95-5% split, it should also have 95-5% split. Okay, so this particular type of technique keeps in mind that, okay, I have this kind of data, I have to make sure that whatever type of decision tree I'm creating, it should get a proportion, or shall I say the term balanced split of data to train on. Okay, and with this thing, the voting is going to happen and then the answer is going to come out. Okay, so this was a small theory. Why not let's apply the same thing on our data set. So for that, I am going to first of all previous technique to handle uh, highly balanced set. So copy, paste it over here. This is the way I'm importing the data set. Okay. Then all I need to do is call it up. I'm calling this particular function random state 42. Okay. Let's see what are the different parameters. An estimator is 100. I can even play with the hyperparameter tuning, guys. This can be a really good homework for you. If you can play with hyperparameter tuning, is your model performance increasing or not? Okay, as of now I'm only using the default thing, whatever is given, like n estimator equals to 100 is the default number of trees it is going to make. Criteria is Gini, maybe try entropy. Okay, it is going to slow it down, maybe it is going to give you better result. maximum depth, it is not giving any maximum depth. Okay, minimum split, everything is the default which is going to be used. Once I do this, the model is prepared. Now I'm going to just try it over here. I think I missed this particular part. You can just copy it, paste it over here. Okay. And now let's see the classification report. All right. So we can see again, the F1 score came out good, which is 100%. Accuracy is 99%. I'm going to ignore it. Precision increased to 53%. With the smart analysis, it was 40%, but this time the precision increased to 50%, which is a really good sign. Okay. So why not? Let's try to show the exact same thing over here, which is the confusion matrix. Perfect. So earlier 12 misclassifications were happening. Now it is now even decreased to 7. Okay, which is very good. That the amount of fraudulent transaction alarm is happening. 51% is a true alarm. 48-49% is a false alarm, which is amazing. Like 1 in 2 transactions is actually a fraudulent transaction and 1 can be a garbage, which is completely fine. Okay, you don't want your analyst team to get stuck in the wasteful hours. You want them to work on the perfect precision. This particular thing can also improve if you try more and more techniques. Or over here you can try, go ahead in trying the different shall I say, hyperparameter tunings. Okay, for that, let's see, we tried hyperparameter tuning yesterday. Might be a basic question, but what actually is a parameter, and it varies with algorithm. Oh yeah, so parameter is nothing but, if you talk about a Python function, let's talk about over here. So parameter is nothing but if you create a define add function. Okay, a b. Okay, so return a plus b. So once you call this function add 3 4, so these are nothing but your parameters. Okay, now maybe I don't want to give anything over here. Okay, and it is just going to give a default value 2. Okay, so these are nothing but the default value. Very uh, basic way of understanding what exactly parameter is, default value. Now if we just zoom out and look at different algorithms, so tree based algorithm has different parameters in terms of what should be the maximum depth, what should be the minimum split, etc. Okay, your logistic regression have iterations. How many different models shall I try before giving you the perfect answer? Okay, SVM has a parameter which is called as kernel, or it also has C or Q. Okay, what else? Naive Bayes, do we have any? Not really. K nearest neighbor has algorithm like what should be the distance metric you can use. I can use Euclidean distance, I can use Manhattan distance, I can use Minkowski distance. Okay, so these are nothing but the term which is called as parameters. Okay, and they do change with different algorithms. Okay, okay, Priti? You're welcome. So guys, a small exercise can be done over here. Okay, uh, what you can do is take help of, shall I say, let's see if I have a good data set which you can work with. Just a second. Okay, let's see. I'll give you a good. First of all you need to do is import grid search CV. Okay. And with this, I'm going to import, or shall I say, have the parameters, which look something like this. N estimator means how many trees I want to make. Let's make it as 150, 200, and 500. Okay. Maximum depth, none 510, minimum 7, 2, 510. Uh, I can also go with criteria. What is the criteria? Random forest parameters. What all criterias do we have? Criterion. I'll go over here. So this is something beyond what I need to teach you, but this is a very, very good exercise which you can try. Okay. So let's just copy this whole. Okay. Copy this, come back over here, paste it. Okay, perfect. So this is the criteria which I have created. Uh, we can go ahead, use this. And I like verbose to be 4, show the progress. Okay. Dot fit and give me the best parameters. Fit and give me the best parameters. And that's it. Do I need to give it anything else? I think we are fine. I think in grid search, we have to show it something. I can just cut it, paste it over here, paste it over here as well. Now, in grid search CV, I want the error search. No. So this is something I'm just making it in front of you. So don't think like something attributes. Okay. Okay. So I'm just going to copy this code to you. Okay. Let's see if there's anything else. Yes. Recall macro. This is the one. So I'm just going to add it over here. Recall macro. Perfect. So I'm just going to paste the code completely to you. Now let's try to run it first. It is if it's going to work, true and false. Okay. I need to add this one over here. Copy, paste it again. Let's see if it runs. Okay. Now there are 648 totaling. Okay, I'm trying to create 3240 models. It is going to take some time. Okay. Try to run this code on your system as well. It is going to take some time. So take this. It worked for me. Maybe because of the processor and the RAM difference. My system is running on 32 GB RAM. That's why it was able to handle it. This kind of thing is not really, shall I say, very good to run on local system. In such kind of scenarios, it's better to run on Jupyter Labs or Collaboratory, Google Collaboratory. Okay, they are able to handle such kind of scenarios pretty much easily. Okay, so let's see what is the perfect answer. So we have all these things which we can use. We have to use Gini. Bootstrap is true. Max depth is none. Max sleeve is 1, and as an estimator is 150. Okay. Let's see. if I try to make this model run, so all I need to do is go back over here, copy this code, come back downstairs over here, and over here, what I'm going to do is copy this whole thing. Let's keep the random state as is, paste it over here. And I believe this is going to work fine for us. Once I do this, let's see what happened. Oh, okay. We have to remove this and make it equal to. Let's try to do this one by one. Your RAM is full, but your GPU is barely used. So as of now, we are not allowing it to use GPU because we have not used n job parameter. So once you allow n job parameter, it is going to find if you have a GPU, then it is going to start using it. Okay. Okay, let's see if I just do this as equal and do this as equal. Let's see if it is going to run. Okay, it is running now. Once this runs, I'm going to run this as well. Copy this, paste it over here, and it hardly made any difference. Hardly, it did not make any difference. Even after trying this particular technique of using all of these things, uh, we did not get any good results. But yeah, this is how a data scientist works. This is how they try to tweak the models to find if they are able to squeeze out 1 or 2% more from what they were giving from the default parameters. So I hope this practice or this particular thing is clear to you guys now. If you have any questions, please do let me know. Scoring, I think, recall, let's see if it works any good. Okay, so this is the maximum recall which it is able to achieve. I think if we try to go for F1 score, next time, instead of recall macro, maybe try to give F1 because we are already getting 100% recall. That's why we are not getting any improvement in precision. Maybe next time, if we try to aim for F1 score, it is going to work, but then it is going to definitely hamper recall, which we don't want. We want recall to be 100% at all the time. Makes sense, guys. Makes sense. Okay. This particular answer makes sense. Okay, perfect, guys. So if there are any questions, do let me know. So far, what we have covered. If not, I'm going to wait for 1 or 2 minutes. If not, then we are going to start practicing other exercises with different data. Okay. I see no message on the chat window. That means we are good to go. So guys, in multi-class classification, we try to use iris dataset. Why not use a different dataset which can help us with much more understanding and much more comparison with different algorithms. Okay. This time I'm going to use a data which is called as online gaming behavior. Going to give you like 1 or 2 minutes to look through this particular data. Okay. Uh, I'm going to also import it at my system. So if I just go through this particular data, this data contains player ID, age of the player, uh, gender, location, strategy, what kind of game genre a certain person plays, play time hours, in-app, in-game purchases, game difficulty, sessions per week, average sessions, player level, achievement unlocked, and engagement level. So guys, this particular data set, just look through it. Can anybody tell me which one over here is going to be our? Sure, I can share the data again. Okay, I hope you have the data now, Devika. So if you look at this data, I want to, for you to tell me which one of the columns uh, is going to be the dependent feature. Let's see who can answer me this. And oh, I do have a data dictionary as well. Good. So we are going to look at that also. Just copy this, paste. Was I able to paste it? No. So there's a data dictionary also which is available to us. If you just make it as a markdown cell. So in-game purchase indicates whether the player makes it in a game purchase is 0 or 1. Okay. So Pritish says that it's an in-game purchase. Let's see. It's a very good column to pick, but we are here using engagement level, Pragati. Okay, Pragati is saying engagement level because what we are trying to see is how much engaged a player is going to be. High engagement means high number of time they are going to love your game. Maybe they are going to eventually become your fan and going to purchase your game. Okay. Medium is going to be on and off. Low is going to be low. Okay. So in the multi-class classification, I'm going to use engagement level. Even in the, shall I say, this particular data dictionary, we already have engagement level, which is present for us. Categorizing engagement level reflecting player retention. How much player is retained, medium, high, or low. Okay. So as a first of all, we are going to practice to find how many nulls are there in the data set. Okay. How we are going to do it? I'm going to just simply put this one over here. And luckily we don't have any nulls, which is very good thing for us. Let's see how the data distribution for the target feature. Okay. I can see that out of all the rows, let's see what's the info first. We have 40,000 rows. Perfect. In 40,000 rows, around 20,000 is medium, 10,000 is high, and 10,000 is low. Okay, so there's a slightly skew, but still a very moderately good division of different classes. Okay, so once the engagement is known, let's try to divide our data set into the independent and dependent features, X and Y. So we can see that we are using the target feature, and then we have created X, followed by we have created the Y. Let's do some label encoding. Okay. Why? Because we can see over here in our data set, the game genre is in string, location is string, gender is string, game difficulty is string. Why not? Let's convert them into the label encoding. Okay. You can go for one hot encoding. You can go for label encoding. Okay. It depends on you and or how many values are there. Okay. Label encoder is not defined. Why not just import that particular field? Let me give you the whole library. These are all the libraries which you can import. I'll do the same over here for me as well. Let's try to read this again. Okay, So the label encoding is done. Okay. Why not? Let's look at the heat map. Okay. Heat map is going to show me if there are any possible high correlation between the features. So I can see, first of all, the color matrix over here shows that anything which is dark blue is least correlated. Anything which is in dark red is highly correlated. According to this particular map, I can see that there is hardly, or shall I say, no correlation which is present between the features. Or in other words, I can say that there is a weak correlation to be even considered over here. Since there is no correlation, I don't have to pick or drop any features. Let's go ahead with what all features we have. Okay. Let's split the data into training and test set. Okay. The same practice. Done. From here on, guys, let's do one more thing, one last thing, which is the standard scaling. All right. So guys, I have xtrain underscore sc, xtest underscore sc, ytrain and ytest. These are my features which are ready with me. Okay, guys. Now all you have to do is the script you created for iris dataset. I want you to use exactly the same script. You can go ahead using the logistic regression. Then you can go ahead using SVC, KNN, naive Bayes, decision tree, random forest. Okay. If you have any problem, do let me know. But let me try to copy it for myself. Okay. First of all, let me just try to copy the whole cell if I am able to. Copy cell. Okay. Paste cell below. Okay, perfect. Now what I'm going to do is first of all use xtrain sc over here, xtest underscore sc, ytest, ytrain. Okay. Once I do this, let's hit run. Okay. So logistic regression gives us 82% accuracy with 84% F1 score. Okay. Let's do the same thing. SC, SC. Support vector is taking some time. The data is 40,000 rows. And just like I told you, support vector takes time in such kind of scenarios. Okay. You can see over here, I am not giving any parameter. You can try to run it with RBF. You can try to run it with different kernels. Okay. That's completely on you. And it is going to take some time. I should not have run this, I guess. Let's see what the answer comes out to be. All right, the model is complete. 89% accuracy, better than logistic regression. Very good for us. 91% precision recall. Okay, let's try KNN. KNN, 100% accuracy. No, no. 74% accuracy with 76% F1 score. KNN is not performing good, guys. Okay, let's try naive Bayes. Let's see if the Bayes theorem is any good for us. 84% accuracy, 87% F1. Let's see. Still, so far, SVC is the winner. Okay. Let's try decision tree. 83%, 86%. And finally, we have the random forest. Again, all these models uh, are run on default parameters. Okay. You can try and just do multiple hyperparameter tuning to get much better result. Oh, and the winner, we have the winner. Random forest is the winner. Let's see what the answer is. So the final model comparison shows that logistic regression 82%, SVM 89%, KNN 74. The biggest loser is KNN. Naive Bayes is 84. Decision tree is 82, and random forest is 90.98, means 91% accuracy. And that's it. This is how, as a data scientist, you are able to pick the best performing model in this particular equation. Okay. And this is a multi-class classification problem, guys. We don't have to specify anything. It is able to deduce it by itself. So this is a very short way of performing this particular multiple model approach. There's one library which is given to you guys. Okay. Shall I say this particular module 4.2? It goes a bit deeper on how exactly you can even go further, like using the ROC to view how exactly a model performance is looking like. Let me see if we have anything to show you over here. Just like this, you can see ROC curves, and this is on the different classes. Okay, for certain model. If you go to any other model, you can see for which particular model this is. Let me see. It's a naive Bayes model. Naive Bayes model performs something like this, much better than the other model, so on and so forth. So I will recommend go through this particular notebook as well. It is much more of theory and less of practical. Okay. Can you please share the label encoding code snippet? Of course I can. Let me just. Did I forget to share that thing? Okay, there you go. So I feel we have completed what we wanted to complete for today's class. There's a small reading homework, which can be a very good thing, which is called as multi-label classification. Okay. It's a very small topic and very niche type of case studies comes out of it. Okay. Uh, as of now, what you can do is just read about it, because multi-label classification, even though comes in classification technique, uses a high advanced algorithms like deep learning algorithms, like text classification into a positive text or a negative text, image classification, a cat, dog, something like this, or maybe different names. In these, you need deep learning algorithms, even though it becomes a classification problem, but it becomes advanced classification problems. So it's better that you just read about it. Okay. There are 3 links which are given to you. Go through it, and it's like a good knowledge to have. But in future classes, you're going to study bit like more and more advanced topics like this. Okay. Maybe not in this module, but in your next module, which is going to be definitely about deep learning.
And with that, we have come to the end of this course. If you have any doubts or questions, you can ask them in the comment section below. Our team of experts will reply to you as soon as possible. Thank you and keep learning with Simplilearn.